Hello, everyone, and welcome to the Future of Data-Centric AI. I am Aarti Bagul. I'm a machine learning engineer at Snorkel, and I am thrilled to be your host for today. Thank you so much for joining us. We're thrilled to have you. So we have a very exciting day planned for you today. We have a number of speakers as well as panelists talking about the shift from this model-centric approach to a data-centric approach of building machine learning applications. So we have experts from academia, research, as well as industry talking about these real-world challenges as well as ideas and solutions to make machine learning practical. So as I said, we have a very exciting day ahead of us here today. Here is a quick look at the morning agenda. Wrong side, which you can see here. You can also find it on the agenda tab at the top of your screen. And let's get going. Before we get started, I'd like to make a couple of housekeeping announcements. First of all, this event is being recorded. Second, we have closed captions available, which you can access using the CC button at the lower right of your screen. We have a code of conduct that is posted on our website. We have all agreed to the terms and conditions when we signed up for this event. You can just go back to the website to take a look at that. A lot of you have already started posting in the chat, loving the activity there. Please update your profile at the top right of your screen so people know, where you're from, what you do, things like that. And a lot of you are active here already, but we'd love to make this event as interactive as possible. So we have this chat functionality. In the public chat, you can reach out to other attendees. If you meet attendees you'd like to chat with, you can also DM them and video call them. Just to get the chat rolling, I think I see here we have somebody joining us from India. Shaima, welcome. We have Brand joining us from Virginia. So please take a moment to tell us who you are, where you're joining us from, and what you're excited to hear about today. Again, we're thrilled to have you. Thank you so much. We also have a help chat at the top under the chat as well. So if you have any audio or video issues, just try refreshing your screen. But if that doesn't work, you have a direct line to our producers in the help chat there. Next, we have the Q&A tab next to the chat. We will be doing a Q&A session at the end of the Q&A at the end of each session, and I will be monitoring this and picking questions from that list. So please feel free to comment there. For example, Vu already said, are the talks recorded? You can also upvote, as you can see, which has 7 votes. And yes, the talks are recorded, as I just mentioned, and we will make the recordings available at a later date via email. It will also be on the website. We will also have polls that you can see. So these will be at the end of each session, asking you how you're enjoying the conference, how the day is going for you. We also have some polls in the poll section on the right, asking you about your experience in data-centric AI. So if you could answer those, we will make the results available subsequently after we release the recordings. So the more people that answer, the more informative the results will be there. So again, as I mentioned, we have the chat, the Q&A, the poll. Please participate. We love to make this interactive. We will also have lounges. We have 2 lounges available. One will be at 12:30, which will be our short break, as well as at the end of the day. We're virtual. We can't be in person, so this is kind of the best thing to meet other attendees. So take the chance and leave today not just with ideas, but also other people that you can interact with. So again, a really exciting day coming up ahead of us. Here's the agenda again, the morning agenda, which will show up on the screen. Should get used to this. You can also find it on the agenda tab at the top. And again, please feel free to chat. Also, the event hashtag is #data-centric-AI. So use this to share any insights that you have on any social media channels, so other people can also learn from you there. As I mentioned, we will make the recordings available. We will send the link. And now, without further ado, I'd love to introduce our first speaker for today. Our first speaker earned their PhD in computer science at Stanford, where he started and led the Snorkel open source project. He's an assistant professor in computer science at the University of Washington, and he's also the CEO and co-founder of Snorkel. Please welcome to the stage, Alex Ratner.
Hey everyone, how's it going? I'm already seeing some familiar names and some new ones in the chat, so it's incredibly exciting and humbling to have all of you joining for today. And hopefully this gives, and this talk in particular gives a little bit of an overview of some of the themes that we hope to propagate and to bring up here, as well as some of the work that we're doing at Snorkel and over the project over the last couple of years that has led us at least to this perspective. And we're so excited to get to present and also hear from all of you, why you're here and how your experiences and current trajectories relate to this big shift that we're talking about. So without further ado, let's jump into the slides. Awesome. And so today I'm going to have these first 30 minutes just to give an overview of some of our perspective on the broad trend that is this data-centric AI development shift, as well as some of the work that we've done around it, both to provide context on where some of the Snorkel folks that you'll hear from today get their perspective, as well as to give an example of a data-centric AI system and approach. But again, super excited to hear from all of you and from all of the wonderful speakers. So just to give a little bit of a preview, I won't run through this all, but we have a ton of really exciting perspectives. This includes things on methodological advances, self-supervision, multitask learning, transfer learning. Includes applications in real-world practice, system design considerations throughout the machine learning lifecycle. So lots of exciting stuff, and you can check out the agenda at future.snorkel.ai, as well as lots more of data, lots more in terms of resources on the Snorkel website. Okay, so I'm going to start with a what might be an apropos topic, which is, what does data-centric AI mean? In particular, it might sound a little bit tautological if you think, well, AI, or at least what we often refer to as AI these days, which today largely we mean machine learning, is all about data. It always has been about data. So what do we mean by this being a shift or a new focus? So I'll start by contrasting with where AI and machine learning specifically has been from a development perspective for many years. And this is what we often refer to as model-centric development. And in the model-centric development world, which often I like to refer to as kind of the Kaggle challenge or ImageNet world, you're largely considering the training data that your model is learning from. And today we'll largely, at least in this talk, I'll be talking largely about supervised learning. So imagine some data points with labels. Imagine some contracts or chest x-rays or network flows with some label that you want to train a model to predict. So your training data is in the supervised paradigm is a bunch of data with the kind of ground truth label, and your machine learning model or your, though they're not at all synonymous, what's largely used synonymously today, the AI model, is going to fit to that or learn from that labeled training data. And so this is a little bit caricatured, but in the model-centric AI development approach, you're largely treating the training data as exogenous from your ML development process. It's something that you download as a CSV file when you start your Kaggle competition, or you start your academic experiments against one of the benchmark data sets like ImageNet. And then you're largely iterating via changes to the model. And I use model in the broad sense that includes feature engineering, algorithm design, bespoke architecture design, et cetera. So you're really living in the model and treating the data as a static artifact. And often there's a kind of sense that the data set is something that is outside of the AI development process or before the AI development process. And we'll touch on that again. And one thing I want to emphasize throughout this talk is that this shift from model-centric to data-centric AI development is as much a kind of shift in the focus of the ML community and culture as it is a technological or methodological shift. It's about viewing this data as a more central figure and first-class citizen of the development process. So skipping over why exactly this has happened, which we'll get to shortly, but just going right to the what. Data-centric, in contrast, basically means that you're spending more of your time in a relative sense on the data, labeling, managing, slicing, augmenting, curating. And the model may also be under development, but is often relatively fixed. And in this data-centric world that we're increasingly seeing out in the space of AI applications, the data is the key differentiator or arbiter of your success or failure. And it's therefore the key focus of iterative development. And so that is a very high level sense of what we mean by data-centric AI development. And of course, it's very important before I jump back in and proceed bombastically with extolling the importance and virtues of data-centric AI, to say that it's of course not an either or. Successful AI development requires both models and data, obviously, and it requires iteration on both. But rather what we're bringing folks together to talk about today, and what underscores a lot of the work that you're going to hear about both from me now, but today throughout the summit, is that this relative shift to data being the core bottleneck and the core focus is a real fundamental one, even though it's a relative one, and it really changes how we develop and deploy AI and the systems and techniques we use. And before I jump in, I'm going to go through what will serve as an outline for this overview talk. And what we refer to as kind of principles of data-centric AI. And originally, circa 2015, 2016, when we were starting a lot of our work, in particular the Snorkel project, which again, lots of resources if you want to dive into some of the technical underpinnings or the theoretical underpinnings, lots more stuff on the resources page on our website or Google Scholar. But at a very high level, these principles back when we started at the Stanford AI Lab were really hypotheses. And so whether you think of them as hypotheses or as principles, there's three that we'll focus on today. First is the one that I sort of already covered, which is that AI development today increasingly centers around the data, the training data especially. The second hypothesis or principle of data-centric AI is that if data is the fulcrum point, is the center of AI development workflows, the interface to it needs to be something better than just manually labeling and curating one data point at a time. In other words, there needs to be some kind of programmatic interface to actually driving this data-centric development if it's going to be practical and feasible in real-world settings. And finally, data-centric AI, i.e. AI development workflows that revolve around the data, actually have to include the people who know about the data and know how to label it and know how to sample it, know how to construct the relevant subsets of it or slices of it. And we'll refer to these folks as the subject matter experts. And obviously the subject matter expert and the data scientist can be one person, but we'll refer to them as two separate folks because they often are, and their collaboration is central to data-centric AI actually functioning. Okay, so we'll go through each of these three principles or hypotheses and talk a little bit about why they're important, what they really mean, and how they change the way that you actually go about developing AI and the platforms and systems you use to do that development and deployment. So again, just to dig in a little deeper about what ML development still is in many settings where it makes sense, but increasingly was the dominant mode, this model-centric development cycle. And again, in this setting, the data is largely something that is thought of as outside of or before the core development process. And instead, you're often just, you're spending most of your time iterating on the data. I guess I should phrase this in proper kind of, population statistics terms. So what we mean by, previously being model-centric is if you went to a ML team in industry or in some production setting 5+ years ago, and you said, what is the primary thing that you spend your time working on? 5+ years ago, 95% of people would say the model. And in particular, they'd be working on things like feature engineering, which is selecting, the specific attributes or features of the data that the model is actually looking at and learning weights or parameters over. It's the model architecture design, so the actual structure of those weights or parameterizations of the features that get fed in as input. The algorithms for training these bespoke model architectures. And all of these pieces were the subject and still are the subject of vast amounts of research, but they were, they are the primary kind of toolkit and focus of a development when you're thinking in this model-centric development perspective. So what happened? Well, one of the big trends that's caused a sea change in how machine learning is done is this shift from models that are largely based on manual feature engineering and that, in other words, don't learn their own representations to representation are often, this is used synonymously with deep learning models of today. And without going into depth there, the big shift in a practical sense, and I'm really going to stay high level in this talk and really talk about practical imports and themes, is that today's models are much, much more powerful and much more push button because they take in raw data largely and they learn features or representations themselves and they get new state-of-the-art scores. But they're far less easy to directly modify, and they're far more data hungry. And that last one is important, and without going into some of the theory that is still being repaired by their emergence and adapted to some of their new emergent properties, at a very high level, these models have hundreds of millions of free parameters that need to be learned from data rather than thousands, and therefore they're commensurately more data hungry, and they need that much more labeled training data in general to get peak performance. It's also worth noting a really exciting trend is that these model architectures are increasingly convergent and commoditized or accessible. So if any of you have been following ML Twitter and seeing the latest variants of everything is a transformer in the latest paper submissions, whether it's a transformer or some other architecture, an increasing diversity of tasks and data modalities are all being handled by an increasingly small and stable set of model architectures. And again, what this means is that these model architectures are better supported. They're more push button. You can run one of them in a line or two of Python these days, thanks to some of the great efforts of both the community and various companies in the space. They're far more accessible, in other words, but they're also far less practically modifiable. In other words, it's very difficult as an AI practitioner to sit down and say, okay, here's some error mode that my model is having. Let me go and make a tweak to the third multi-headed attention unit to correct for that. They're kind of black boxes, amazing, powerful, well-supported and well-engineered black boxes, but very difficult to directly modify. And of course, back to that second thing that was mentioned, they're increasingly data hungry. So the training data, the volume, but also the quality, the management, the distribution and sampling is increasingly the arbiter of whether they're successful or not. And you can even see this reflected in the state-of-the-art literature. You often see the progress these days on state-of-the-art benchmark tasks is more about creative ways to collect more data, to augment or transform or boost it, to utilize other sources of signal more effectively versus a new model architecture. So in other words, if you look at ML development today, a lot of the key operations that you used to have in your toolkit and used to be the mainstay of what you actually did as an ML or AI developer, feature engineering, model architecture design, training algorithm design, are really not what you focus on or what's highest leverage to focus on, or even what you can practically focus on to iterate. And instead, what ends up taking up all of your time because of this commensurate need for lots and lots of labeled training data is everything around the data, training data collection, labeling, augmentation, slicing, management. So to return back to that statement earlier, if you go to an average ML development team today, what we're seeing, at least from our perspective in the space, is that an average team will say, we're stuck on and we're spending our time on the data, much more so than the models. And so data is both the key bottleneck, but also really the emerging interface to how you actually iterate on and develop AI today. And obviously all that was high level, but again, I'm giving a preview for some of the great, more in-depth talks that you'll hear throughout the day today. Also, it looks like there's some connection issues, but I'm sure those will be taken care of in the chat and we'll be able to share this afterwards if not. Okay, so second principle is about data-centric AI development needing to be programmatic, or in other words, higher level than just manual manipulations and curation of data points. And this is underscored by a reality that is increasingly known throughout the industry, which is that a lot of AI progress is blocked by needing to label and curate and manage training data. So in some settings, you see this problem being tackled by employing armies of human labelers. Think in the self-driving world, labeling stop signs or pedestrians with lots and lots of manual effort, clicking on one image at a time. But for the majority of the use cases that are out there where AI has an incredible promise, where all the tools, the teams, the models are kind of on standby, it often takes entire quarters or even person years to go through and label and manage data to actually be ready for machine learning development, especially in settings, as we'll get to later, where data is very difficult or expensive to label. So I'll give one example about this. This is a bit old, but it's one of my favorite ones because it's a great use case we partnered on back in the Stanford days with the Stanford Radiology Department and the VA healthcare system. And without going into the details, the task here is classifying medical modalities like, say, chest X-rays for whether they need to be urgently triaged by a human or not. So this is an analyst assist or a human assist ML deployment, not replacement. And it's also motivated by, for example, low resource hospital systems where, there is a limited supply of human attention to go around, so it needs to be prioritized correctly. Anyway, if you're curious with the details, again, you can check out the resources and see some of the papers around this. But I want to pull out just a few quick stats that are very exemplary of this data-centric bottleneck in reality today, which is that our collaborators in this project spent about a day or two trying, I think, 5 or 6 of the state-of-the-art image classification model architectures at the time. And again, it really only took them a day or two, under a couple hundred lines of Python to try all of these out. And they found that there was under a point of difference in the score we were optimizing for between, the top of the leaderboard and the fifth model on the leaderboard. In other words, the difference from the model architectures, which all actually performed quite well, was fairly minimal. In contrast, the data, the labeled training data to actually get this model to perform well was immensely impactful. It took 8 to 14 person months of Stanford radiologist time just clicking one by one on data points. And the difference between a little bit of that data and the full data set was on average 10 to 100x greater than what model architecture you used. So again, this just underscores this theme that while obviously the model in an obvious sense is still the star of the show and still critical, the leverage, the highest leverage point is usually in many applications today, the data, how much of it, how it's labeled, how it's managed, how it's partitioned and augmented, et cetera, versus what particular model architecture you use. But getting that labeled data, as we kind of hinted at in that example, in most real world settings is very difficult. Real world use cases generally require subject matter expertise. You need a legal analyst or a financial analyst or a doctor or a government analyst or a network technician, or the list goes on, to actually do this data labeling and curation. So it's and often these people need to be specially trained for the data set and use case at hand. So they're often people inside your organization that you have to beg for some of their time, not just people that can be hit via an API. Real world data is often highly private and can't just be shipped out to anyone to go label. And real world data and objectives for what you want to model with that data often change rapidly. So often both the data distribution coming in and the modeling objectives that you're actually building your model for on the output side are changing multiple times, anywhere from every day to every week or every quarter. But either way, you're constantly having to relabel data as a result. And so in these settings, which again describe most verticals, most settings in the real world, manual data labeling and curation is really just a non-starter, even for the largest organizations in the world that we've had the amazing opportunity to partner with. It's also, and this is really important to note, and I've actually been having recently some great conversations with folks both on the enterprise, but also especially on the government side, where this is really coming into key focus. There are many ethical and governance challenges that are really exacerbated by an AI approach that relies on manual labeling of this central data set that the model learns from. Questions like, how do we inspect or correct for biases from human labelers? How do we actually govern or audit a data set of hundreds or thousands or millions of hand-labeled data points? How do we actually trace the lineage of some model error that we observe back to where in the training data set it originated from? In other words, where the model learned it from. And these are all critical challenges that, when you're dealing with a pile of, usually a massive scale pile of manual labels, is technically a problem that is as hard or harder than the original modeling problem you were trying to solve. In other words, it's not unapproachable, but it's something that in practice you can't really do. You can't deal with these biases. You can't govern and audit. You can't trace lineage when you're dealing on a fully manual approach to data-centric AI development. So one of the approaches that we've taken, and now I'll shift from a broad spectrum view to an example of a data-centric AI system. As you could have guessed, given my T-shirt or the logo that's plastered around this talk, I am indeed going to talk a little bit about our platform Snorkel Flow, but again, less about the specific details. If you're curious, please reach out, and more about the reflection of the principles we're talking about. And I'm going to skim through pretty quickly just so we can get through on time. But in a nutshell, the key idea is to try to raise the abstraction level with which users can interact with this new center point of development, in other words, the data, and raise it from labeling and curating and slicing and augmenting this data by hand to doing that programmatically. So you can think of, as an example, asking a subject matter expert to write some keywords or phrases or pattern matchers for a document as a really simple example to label, rather than just labeling one by one thousands of documents by hand. And as a quick note, this was and still is a project out of the Stanford AI Lab, lots of great government and industry funding and partnerships and deployments and collaboration, about 50 plus peer-reviewed publications. We'll see how the NeurIPS deadline goes this afternoon. But if you're curious, you can go and check out the stuff on the resources page of Snorkel.ai. At a high level, Snorkel Flow, our platform that we're building here at Snorkel, is an instantiation of this idea that data-centric AI development is all about rapid iteration that centers around modifying and labeling and managing your data as the first-class citizen of the platform. So there's 4 basic steps that Snorkel Flow supports. And again, broadly 4 basic steps that we think are really important to have in a data-centric AI development loop, whether it's Snorkel Flow or some other approach. First is some way to actually label and manage your training data, and to do so in some programmatic fashion rather than just by hand. Although obviously hybrid approaches are something that we support as well and have published about and are often very powerful as well. Second, finding some way to clean up and manage this data. And in the Snorkel Flow setting, specifically cleaning up this programmatic input, which is often messier or weaker as a form of supervision, even though as it's far more efficient and practical. Then using this to train models, and finally closing the loop to actually analyze where are there errors in the model that can be corrected by going back and modifying the data. And so the idea here is not about some push button auto magic shift from having to spend person months labeling data to getting to press a button and do nothing else. It's still a fundamental human in the loop process, but it's about having that loop be minutes or hours of time spent labeling and managing data rather than person months of manual labeling followed by some model-centric development at the end that often can't solve the underlying data problems. And just to skim through very rapidly, at a high level, this labeling, the core abstraction inside Snorkel Flow is this idea of a labeling function. And I think my indentation got messed up, but I normally do actually know that indentation is important here. But basic idea is, have a subject matter expert or a data scientist express some piece of knowledge, some pattern or heuristic or external source of signal as a function that labels data rather than purely individually labeling data points by hand. So in Snorkel Flow, this can be done both via a no-code UI as well as through a Python SDK. And I'll come back to this point at the very end of why this no-code UI is a very central piece of making data-centric AI collaborative, as I mentioned in that third principle or hypothesis. This essentially serves as an abstraction layer for taking in all sorts of signal types, not just patterns or heuristics, but cross-checks against databases or ontologies or knowledge bases, application of heuristics or legacy systems, other models, other manual labeled data sets that may be somewhat applicable but noisy or slightly offset. All of this stuff can get dumped in through this abstraction of a labeling function and applied. Now, once you've done that, once you've shifted from manual labeling to programmatic labeling, you get all the commensurate benefits. You can create a training set that is quite large in minutes or hours. You can actually go back and, as you do with any other kind of code, audit and govern and modify and reuse. And in general, have a much more practical and data-centric way of actually doing your AI development. But on the other hand, your programmatic inputs, your labeling functions are likely going to be noisier. They're not going to be 100% accurate. They're not going to cover all the data. This is why rules-based systems are challenging, why we're talking about ML in the first place. Key idea that we worked on a lot on the academic side, again, I'll just skim over, is the idea that you can actually take in these programmatic or what are often called weak supervision signals and automatically figure out how to reweight and combine them without separate ground truth. And this is building on many, many years of theory in this area that we made some incremental progress on top of, and ends up allowing you to actually write these labeling functions, dump them in, and have the system take care of figuring out which ones are more or less trustworthy, how to adjudicate disagreements, and how to deal with this more efficient and more practical but noisier form of interfacing with your data. Then I'll be quicker through the rest, but you can train models. You can now train the latest data-hungry model architectures. You're training them on your data versus some generic data set that may or may not match your actual inference time or test time conditions. These models can take some amount of the data being labeled and generalize beyond them. So there's an idea here that is, I won't have time to go into depth about, but of actually taking some programmatic labeling of some portion of your data and then provably being able to generalize beyond it. So in other words, taking some of the best of what direct specification or rules-based approaches can do. In other words, being precise, but struggling to cover the long tail of diverse unstructured data, and bridging that with what machine learning does better and better every day, which is generalization to more diverse data patterns. And one of the cool results also that has both empirical and theoretical work behind it in a lot of our publications over the years is that you can now actually scale at asymptotically roughly the same rate as adding more labeled data, but with unlabeled data. In other words, you can dump in more unlabeled data and take advantage of the volume of unlabeled data that's often present. Think hundreds of thousands of documents or chest x-rays or network signals that are not labeled and are too expensive to label, but you can put them through these programmatic labeling approaches and actually get similar scaling benefits in terms of model performance. And finally, as I mentioned, a big focus in our actual platform development work with Snorkel Flow is actually being able to be guided prescriptively to, where is my model making some mistake and where in the data can I go to iterate and correct that? Since often there's a place in the data that actually corresponds to that error mode that you can just iterate on the labeling functions around and correct. And this is not just for initial development, but it's also very crucially for adaptation to the inevitable changes that happen all the time in production, both with respect to input data set shift or distributional drift, as well as output objective shift. The line of business team on that you're building the model for decided they need 10 classes instead of 5, and you don't want to have to relabel all of your data by hand. Pardon me. And I'll skip over some of these results, but just citing a couple, 3 peer-reviewed publications with some teams at Google, Intel, Stanford Hospital, the one I mentioned, as well as a couple of anonymous customer case studies where the impact of this transition from manual labeling to programmatic labeling saved person months to even person years, or 7 to 8 figure sums of spend, and that's just on a single modeling problem. So I'll skip by some of these examples, and I'll just briefly note we definitely don't have time for this today, but as you may hear about in some of the talks today, data-centric AI is much more than just labeling. And so even if you just look at some of the work that we've done and that you may hear about from some of the extended Snorkel team today, it's not just labeling, it's also transforming or augmenting data. It's slicing and dicing data into the more difficult or important subsets that the model needs to fit to, and all of these other central operations that actually drive progress forward. Okay, and since I'm running low on time, I'm just going to very briefly touch on this last point, but it's extraordinarily important. In fact, this is actually the very first DARPA funding that I think paid for me to be working on this odd thing called Snorkel back at Stanford, which is that the SME, the subject matter expert who actually knows how to label and curate the data, has to be included in the loop. And again, I'll note that the kind of old model-centric development way is often this kind of throw it over the wall model, where we actually have this very decoupled API between the subject matter expert who's labeling the data and the data scientist who just receives some XY labeled tuples anonymously with no interaction between the two. And again, this has been tremendous for model-centric development and development of models, but it's tremendously impractical and even dangerous in the real world. And so in Snorkel Flow, we try to make there be a very synchronous workflow between the data scientist and the subject matter expert, as you'll hear from Roshni later today. Another perspective that I'll mostly skip over, but is the idea that a data-centric approach allows you to actually just take direct subject matter expertise and inject it right in the model, rather than essentially playing this game of 20,000 questions where the model is trying to reinfer features or heuristics that the expert knows. And we can even leverage structured forms of knowledge like ontologies, as we published about, or other knowledge bases directly to train models. So again, I'll wrap up there. I'm at time. And really excited for all of you to take a look at the great talks and content today. Really humbled to have everyone joining us. I see Anima up next. Thank you, Anima, so much again for your time today. And again, if you want more details on the stuff that I covered today that's Snorkel specific, check out the resources page.
Thank you so much, Alex. What a great way to kick off the day. And thanks for the introduction to data-centric AI as well as Snorkel. Really wonderful first session here. We have a bunch of questions piling up. Unfortunately, we will not have time for those for this session, but please continue adding questions. We will be asking them for Anima. And let us know what you thought about that session and how you're enjoying the conference with this quick poll here today. Thank you. And without further ado, I'd love to introduce our next speaker. She's the recipient of the Alfred P. Sloan Fellowship, the NSF Career Award, Young Investigator Awards from the DoD, and holds faculty fellowships from Microsoft, Google, Facebook, as well as Adobe. Please welcome to the stage Bren Professor at Caltech and Director of Machine Learning Research at Nvidia. Director of Machine Learning Research at Nvidia. The accomplishments are so many, I was trying to read them fast. Please welcome Anima Anandkumar.
Thank you, Aarti, and it's a pleasure to be here. And I'm really glad there is now so much focus on data-centric AI. So today I'll give you a few projects we've been working. Primarily, these projects have been at Nvidia, looking at how to deal with imperfect data, imperfect labels, right? There are so many challenges when we're trying to apply AI in the real world, and so much of it has to do with the imperfections in data. And I'll give you some ways to get around that, design better, robust methods. And this is indeed, right, an endeavor that will keep on going as we see more of AI in the real world. So indeed, if you think about real world data, there's all kinds of challenges, right? There can be domain gaps. What we train for is very different than what we encounter. And the biases in data, this is something now, thankfully, there is a lot of awareness compared to when we were just getting started with AI a few years ago, especially the aspect that many underrepresented communities could also be the ones subject to societal bias. So having models that haven't seen data from underrepresented communities is a huge problem, especially when used in problematic scenarios like law enforcement, which could mean life and death in many situations. So these are things we need to be very careful about. I mean, if the data we collect has inevitable imbalances, how do we design methods that can overcome that? And indeed, there is also the noise, right? And the noise can be in so many different ways. It could be through occlusions, different kinds of clutter, or even just ambiguity of what is in the image, right? And that's something that current labeling techniques are not really designed to handle. And that comes to the aspect of labels. The way we label images, it's considered a right mundane task, a laborious task, but something that's not given as much care as we should be doing. And that results many times in label noise, right? So you can have ambiguity. And there are also cultural issues, right? Different cultures may label the image in different ways. And it's also laborious, trying to label the entire segmentation here of this complex image would be hugely laborious if done by hand by humans. And for applications like autonomous driving of long videos, this becomes untenable. And so this data hungry revolution is also challenging now, because having humans label that volume of data is extremely expensive. So now the question is, can we overcome, ideally with even no labels, right? Can we do unsupervised learning or semi-supervised learning in different scenarios to overcome these issues? And so the trinity that we see at NVIDIA is to think about three aspects, right? Like, how do we deal with inexact supervision, right? So that you may have label noise, and also incomplete, so you don't get the supervision of everything, but only partial labels. And it's also inaccurate in many ways. So, how to overcome the uncertainty due to partial supervision and potentially wrong supervision? And indeed, there are many different techniques that have been designed to get around this problem of imperfect labels and lack of enough label data. Self-supervision has been very popular over the last few years, where we're creating supervision based on invariances in data. You can do different kind of essentially data augmentations, right? You can crop the image, you can add different kinds of noise, you can transform the image in different ways. And if we know that the label is invariant to those transformations, we've now created supervision just based on these invariances. And this aspect has been really useful in many scenarios. In fact, self-supervised learning has even beat supervised learning in classification tasks. So this shows the power of having capture these data invariances through augmentations. And there's indeed a lot of work also on what kind of structure in neural networks should we design, what kind of neural network architectures. And I'll show you some of the latest transformer architectures makes a big difference in being robust. Even though transformers are data hungry, I think having the right design can overcome some of the issues and also provide better inherent robustness. And that's also a form of regularization, right? And you can have explicit regularization of different forms to overcome the issue of noise. And even like inductive bias, in some scenarios, we've seen how thinking about angular distances, right, rather than the usual L2 loss can be much more robust. And also understanding the domain, if you are thinking about autonomous driving, what kinds of objects could occur, what kinds of noise could occur, are things that we can incorporate rather than designing for every possible kind of corruption. And lastly, synthetic data is still in its infancy, but will become hugely important in future. We already see its importance for testing systems such as autonomous driving or in robot learning, where on the physical robot, you can't possibly create billions of runs. So in these extremely data limited scenarios, synthetic data becomes important. And so methods that can do synthetic to real adaptation will be very critical, because there is huge domain gap, but how do we overcome that? And so the first work that I'll show you, what we call Disco Box, what you can see here is it only has box supervision, right? So we do not have supervision of these instance segmentation, but you can see here, in fact, it's not even trained on this video. This is just directly evaluated by our trained model. And you can see really good quality segmentation of people, even though it's not been trained with segmentation labels. And so that's why we call it Disco Box, because it's only using box supervision. So this is the only label present in the image, but we can output the instance segmentation. You can see these refined segmentations, and also the correspondences. So like ultimately, we want is 3D correspondences, right? So how do we do this with just limited supervision? So I won't get into the details here, but the main idea is we can create now self-supervision based on positive and negative backs, right? So if you have this box, you can create positive backs within the box and negative backs outside the the supervised box. And based on this, we can do multiple instance learning for instance segmentation. And then for correspondences, what we can do is having a self-ensembling with a structured teacher. And the whole idea is we can look at multiple images, right, through a memory bank, and have the refined instance segmentation based on our trained model. And then on top of it, we can also create a differentiable Hungarian matching loss to create correspondences across images. So now we are having these dense correspondences of how these images in objects in one image correspond to objects in the other. And so this mechanism helps us get this rich information with just having box supervision, right? So for some reason, this is not playing, but we can also show this on AV data. You saw the earlier videos, so we can get these refined segmentation, instance segmentation, and correspondences using just box supervision. And this is where we see lots of examples of correspondences, right, across images, and being able to do it with no supervision. So this will appear in ICCV this year. So I encourage you to go check out online for more details. This is already available online. So the next aspect I want to quickly give you some insights is how to make use of all the synthetic data and adapt to the real world. And the first aspect for this is we need to think about uncertainty estimation, right? Because inevitably, when we are going through such big domain shifts, we have to worry, at least if it fails, it should fail in a graceful way. And that means we should give the right uncertainty of failure. And this is a problem with standard deep learning methods, right? So even when it's failing, it could fail with very high confidence. So this is a problem, and there have been several measures that have been proposed to overcome this. A simple one is temperature scaling. But temperature scaling is not so effective when we have a domain gap, right? So when there is a domain gap, you're not as good with handling the temperature through temperature scaling, the lack of uncertainty calibration. We've also explored angular distances as a more robust way to get reliable estimates. There's also Bayesian deep learning methods, but they tend to be heavy, right? They tend to be expensive. So the one that I'll quickly give an intuition is what we call a distributionally robust learning method that has its foundations in statistics. But the main thing to really think about is, this would be the standard classifier here. In addition, what we have is a density ratio. So what we are measuring is how different is the likelihood of this data point under source distribution versus the target distribution. So in this example here, the source distribution is synthetic data, right? And the target distribution is real data. And so what we have is now another network looking at a particular image. How likely is it to have come from the source distribution? How likely is it to have come from target distribution? So you're really measuring that ratio of densities. And to do that, all we require is a binary classifier. So what we are doing is classifying each image, whether it belongs to training set or test set, that is source set or the target set. And by doing so, what we are able to glean is how far is this image from the training data. And so images that are far from training data will be down weighted here because this density ratio will be small and hence will have lower confidence. And so this now becomes an end-to-end training here. So we can train both the task network, if you're doing a classification task, you can train it jointly with also training now a binary classifier, which will assess how far is this current test data point from the source training distribution. And so having this be jointly trained means we can also get now good uncertainty calibration along with good classification. So we use this to do domain adaptation of synthetic to real. This is the distributionally robust method. Getting better accuracy, we also got better calibration. And this method here, what we did was to combine it with self-training. So in self-training, you're looking at uncertainty of your uh, classified labels, right, from your task network at test time. And you're only looking at the confident labels and retraining your network. So this is being self-trained on the pseudo labels generated by the current model. And so we need to be very conservative and train on only those pseudo labels where the confidence level is high. And we need to have calibrated uncertainty to be able to do that. And that's what we see here, that by using the distributionally robust method, where we are training for uncertainty through this density ratio estimator, and that is simply a binary classifier of training and test data, we are able to get good accuracy estimates of domain adaptation. So uncertainty estimation is an important step in this self-training, and having good uncertainty estimates ultimately helps also in domain adaptation. And the other aspect that's important is interpretability, right? So we need to make sure that the images that have lower confidence are also something humans think are also harder, right? And that is clear here, right? This train here, there's less clutter, right? In a way, shape-wise, it looks similar to the source training. But here, this one has a lot of clutter and hence is harder. So the density ratio can also be a way to quickly filter out the hard examples and maybe get additional labels, maybe make sure the model, if how it's able to do on these harder images. So that's the other aspect that's important, interpretability. And so indeed, I quickly talked about self-training as a way to do domain adaptation. So ultimately, what we want is good representation learning, right? And if you're only training on synthetic data, that tends to fail. You tend to have collapsed representations because there isn't the natural diversity we see in real images. And so what we've proposed is methods like contrastive knowledge distillation that essentially balances between training on the synthetic source data and also on the right a frozen, say, ImageNet or some backbone that we begin with. So that way you're making sure that you're keeping this rich real representation while also training on the labeled data that we have in the synthetic domain. So this balance between keeping rich representations from real data but from a, say, different task, and having synthetic data for the current task, but it doesn't have the rich representation and there's a domain shift. Balancing the two becomes important, and this form of contrastive learning helps us keep this rich representation. And the other aspect of representation learning that is very challenging is when we are doing reinforcement learning, right? So visual reinforcement learning is hard because it's high dimensional. So we are directly going from pixels to actions. It becomes very challenging, as in this example here. And so to be able to train not just for normal scenes, right? So at test time, you can have all these unseen weather conditions, unseen, right, road conditions. So to be able to handle this, what we require is data augmentations. But this is very popular in self-supervised learning, right? So we can put all kinds of data augmentations, train the model, make it very robust. But with reinforcement learning, that is not possible because optimization is going to be untenable. So essentially, you will not have your agent be able to make improvements if the augmentations are too strong. So instead, what we did was to have a student-teacher model. So the teacher, right, or the expert learns the policy, but only on weak augmentations. Because with strong augmentations, it just can't learn the policy from scratch. But if it is only trained on weak augmentations, it will not be robust. On the other hand, what we do is imitation learning with the student, right? And the student now has strong data augmentations, but it is getting the supervision of the action from the teacher. And this becomes very useful for it to now learn also the strong augmentations. So this kind of two-stage approach helps us beat the optimization issues that arise in reinforcement learning and still get robust representations that can handle all kinds of visual issues, right, that are unseen during training, and still be able to do good in test time. So the last part, which I don't have a lot of time, but I want to quickly show you is what we call SegFormer, which can give you very rich semantic representation, right, for segmentation, but also be robust to all kinds of corruptions that are not seen during training. So This you can see here is the sec former being able to handle all kinds of different noise here, right? So once the noise is there, because the other model, which is very, kind of sensitive to unseen noise, whereas SecFormer in a zero-shot way is able to handle noise. And what makes this possible is this lightweight. Let me go directly to this architecture here, right, is the lightweight decoder architecture that is just all MLP. But the encoder has this hierarchical transformer in a pyramidal structure and doesn't have positional encoding, so it is lightweight. So overall, right, the main idea is these are lightweight and principled approaches to architecture design, and that provides not just the state-of-the-art results in terms of segmentation, but also zero-shot robustness to all kinds of corruptions. So so in conclusion, I showed you Disco Box. Having just simple box supervision, we can translate that into refined instant segmentation and dense correspondences by doing self-supervised learning. I showed you different ways to adapt from synthetic to real data, and the role of uncertainty calibration there is hugely important. And it's also really important for trustworthy AI, for people to be able to interpret how likely are these methods to fail. And the last aspect I showed you, the state-of-the-art transformer design that enables zero-shot robustness to all kinds of corruptions on challenging segmentation tasks. Thank you.
Thank you so much, Anima. That was a great talk, and we covered a lot of ground and a lot of real-world problems from like using synthetic data, auto-labeling, calibration. So we have a lot of questions popping up in the Q&A chat here. Pooja has a question for us. She said that you mentioned temperature scaling doesn't work well when there are domain gaps. What is an example of a domain gap?
Like synthetic to real, right? Or being able, training on ImageNet and then using that classifier for real world images.
That makes sense. Yeah. And the techniques you outlined, it's not just using synthetic data, it's just real world. Anytime you deploy something, the distribution might change. And so these are quite widely applicable techniques.
Exactly.
Pooja has another question. Does calibrating uncertainty deteriorate the model's performance on the target task?
No, it doesn't, because we get the state-of-the-art adaptation, right? Because uncertainty calibration, in fact, is a step in doing domain adaptation in many of these techniques.
That makes sense, and actually gives you more information when you actually deploy it. Like, should you actually trust the model, and is actually more real-world useful, I guess, as a model. Makes sense.
Precisely.
Yeah. Vashisht has a question for us. He says, for uncertainty estimation, are we relying on the domain classifier confidence as a measure of the uncertainty?
Yes, we are. But the idea is, and even there we could further refine it, right? But the idea is, when you have such a big difference between your target and the training data, right? And then that's what we care about, right? We care about the extremes where we know there is a big shift and we should lower the confidence. So in that sense, you can still trust the domain classifier.
That makes sense. Thank you. We have a new question from Sebastian that's gotten a bunch of upvotes as well. It says, it seems it's easier to make label invariant transformations in image over text. If you agree, what are your thoughts on the future of synthetic data or data augmentation on text data or text tasks like summarization, paraphrasing, NLU, etc.?
Yeah, I guess with text, we have tons of data, right? So, I mean,
Right.
not label data, but, the generation task, we can have all the text we want. But the problem is, again, curation, right? So, what kind of biases are already built into this, and they're all very complex. And, how do we determine if this is factual? Because some of, say, the gender bias could, in fact, right, be factual, like women are paid on average less than men, right? There is a pay gap. So yes, that is a difference in gender, but that's a factual one versus something that is discriminatory, right? So how do we say, do this at scale? That is the real challenge. So in that case, it's not about the lack of raw data, but given also these models are already trained and we can't afford to retrain them all the time, is there post hoc, can we do something to overcome these biases? And that's a big problem.
That makes sense. No, that a wonderful point there about like text data already have a lot of data, but need to sort of curate it better or analyze the performance. Unfortunately, we are out of time, so we won't be getting to the other questions. There was a question about what happened to the previous questions. We will be forwarding them to the speakers. We might be also addressing them in the chat. So a huge thank you to Anima. Thank you so much for joining us and for sharing your expertise with us here today.
Thank you, Aarti.
For our audience members, please let us know how you're enjoying the conference using this quick poll. Always get the wrong side that has popped up here on the screen. And please join the Snorkel community to stay in touch. The link is in the chat. Roberto has been posting about it. And you also get cool socks and stickers. So please join. Up next, excited to introduce our next speaker. She completed her PhD from Cornell University. She was named Forbes 30 Under 30 in Science and 30 Under 30 Rising Stars in AI. And also JP Morgan Early Career Outstanding Faculty. Wow, sorry. She currently serves as assistant professor, University of Wisconsin-Madison. Please give a warm welcome to Sharon Lee.
Thank you, Aarti, for the kind introduction. It's my great pleasure to be here at the Future of Data-Centric AI event. And today I'll be sharing with you some of our recent work on uncovering the unknowns of deep neural networks, and I'll be talking about some of the interesting challenges and opportunities in this problem domain. And so now let's dive in. I would like to start the talk by showing you this video. And this is a model trained on the Berkeley Deep Drive 100K dataset, performing bounding box tracking on the road. And needless to say, deep learning has achieved pretty remarkable success in many exciting areas like this. And I personally feel very fortunate to witness the many breakthroughs since I started my research journey many years ago. And today, instead of adding more praises, I would like to encourage you all to maybe take a step back and have a more critical look at the methods and technologies that we've built. And hopefully by the end of the talk, we can see things in a more well-rounded perspective. I know there are many experts in statistics, machine learning, and AI in the audience. So let's think for a second how you would approach building and deploying such a self-driving car model. And so the typical process is to start collecting some training data with corresponding labels. And so here I'm simplifying things a bit. And then train on your favorite machine learning model. And the output typically contains some predefined categories such as pedestrian, cars, and trucks, and so on in this case. And of course, there are thousands of other details to sort through. But let's say once you finally have a model with decent performance and you think it's ready to deploy, more unexpected work has just begun. And why do I say that? Because the classic assumption that you've learned from Machine Learning 101 is that the training and test data distributions match each other. And this assumption rarely holds true in reality, which was also covered in the previous talk from Professor Anima. And so in the real world, it's closer to this open world setting where a lot of unknowns could emerge. And so for example, we took this image from the MS COCO dataset and run through the self-driving car model that we just trained on the BDD dataset. And you see that the model can actually produce quite overconfident predictions for this unknown class, cow, which was never exposed to the model during the training time. So in other words, deep neural networks do not necessarily know what they don't know. And this has raised significant concerns on models' reliability because algorithms that classify these out-of-distribution samples into one of the known classes can be catastrophic. For example, think about in healthcare, a medical machine learning model trained on a certain set of diseases may encounter a different disease, and it can cause mistreatment if not handled cautiously. And this issue is prevalent not just for high-stake domains I just described, but also in many other scenarios where machine learning is being used on a day-to-day basis. So this is another example that I really like. Imagine you're developing an app of a food image classifier so that a user can go to a grocery store and snap a photo to get some recommendations on the recipes, which could be very useful. And for those of you who have worked extensively with users' data, you would know how diverse and unpredictable it can be, right? There could be a lot of images other than food. And this is precise the type of messy but fun data that I spent quite some time working with back in industry. And so my time working with this real-world machine learning models and data has given me a firm belief on how important this following problem is. How can we build unknown-aware deep learning models for reliable decision-making in such an open world? And one important step towards this goal is to be able to detect out-of-distribution data. And so what is out-of-distribution data, you might ask? Let me first provide a simple view on this. And so let's say we have our training data distribution that is a mixture of two Gaussians for a class label y equals to 1 and y equals to -1 in this case. And so our in-distribution Pn would be the marginal of this joint distribution defined over the input space x times the label space y. And now during the deployment time, these orange dots could emerge, which are out of distribution from an unknown class that is other than green versus blue, and therefore you don't want the model to predict this to be either y equals to 1 or -1. And so to translate this toy data into some higher dimensional images, you can think of, for example, CIFAR 10, which is a common computer vision data set as in distribution, and SVHN on the right side as OOD, which have disjoint labels. Well, you might think that this OOD is way too obvious to us human beings, but I'm going to show you how such an easy setup could trouble these state-of-the-art neural networks. And later on in this talk, I'll discuss how we can go beyond such simplified definition. And so for now, let's stick with this simple view. And so SVHN is just one of the OOD that the model would encounter. And there are, of course, many other unknowns on this complex data manifold. And this is an image from a recent talk from OpenAI, which I think really nicely illustrates this complexity of the problem. And so out-of-distribution detection is indeed a hard problem. And let me explain why before we attempt any solution on this problem. And so the first challenge is the lack of supervision from unknowns during the training time. And so typically the model is trained on the in-distribution data only. In this case are the green and blue dots using our favorite empirical risk minimization. And so you can't really anticipate where these orange dots could emerge in advance because there is a huge space of unknowns, especially in the high dimensional space, right? So what we're showing here is just in 2D. And you can think how complicated things quickly become as you move to this high dimensional space. And so this problem is further exacerbated by this high capacity neural networks that we're working with nowadays. And so in this plot, if you look at the decision boundary, which is right in the middle, which tries to distinguish between two classes, orange versus blue, you can see that the decision boundary undesirably includes and covers some of the OOD data, which is in red dots here, right? So it's on the same side as these orange dots. So it would be classified as orange during inference time, which is undesirable. And you might, ask, why don't we perform density estimation using deep generative models? And it turns out there are unique challenges too. For example, the generative models could be quite difficult to optimize. And even if you can train it to converge, there's a very interesting study by Eric Nellis-Lake showed that OOD data can, in some cases, trigger higher likelihood compared to ID data. So at least for now, the performance of generative-based approach often lag behind the discriminative approach. And so for this talk, I'll stick with the discriminative-based approach. And so over the years, there has been really a lot of exciting progress made on OOD detection, in particular for deep neural networks. And here I've highlighted a few representative ones and also including some of our recent contributions in green. And so the earliest work adopted this post hoc approach for OOD detection. And let me give you a method overview. And so typically the model is trained on the in-distribution data, say CIFAR10, using empirical risk minimization. And now let's take the network as it is without modifying its parameters. And so during inference time, for any given input, we're going to devise a scoring function, S of x, for OOD detection. If it's below the certain threshold, we're going to reject this input. And otherwise, we produce the class prediction as usual. And so the advantage of post hoc OOD detection is that it doesn't really interfere with the original model or the task, especially if it's already been deployed and running in the production and so on. And so an obvious baseline is to use the softmax confidence score, which is the largest posterior probability, P of y condition on x, among all these classes. However, it doesn't really work well because, as we saw earlier, neural networks tend to produce quite overconfident predictions, and therefore you see this, areas that is heavily overlapping between the in-distribution versus OOD, right, concentrating on this, the high confidence region. And so our early work on OOD was one of the first to address this issue by using the temperature scaling and input preprocessing. And mathematically, we can show that a large temperature has a strong smoothing effect and will make the softmax score distributions more separable between the two types of data. So here denoted in green versus gray. And so you can see this effect on the left side. And so in hindsight, what OOD really tries to do is to push these confidence score back to this logit score. And I do want to highlight here that the score produced is no longer probabilistic, which is desirable for OOD detection, but may no longer be meaningful from a calibration perspective. And so that's two different tasks I do want to kind of highlight. And in our recent NeurIPS paper, we took this one step further and proposed an energy-based OOD detection framework, which leverages the energy score derived from the output logit of this neural network for detection. And so now I would like to dive a bit more into the details here. So energy-based model has been around for a while. And so to give you some background, an energy function takes an input x, say my cat, and corresponding label y. And then it will produce a scalar called energy. And this function can be non-probabilistic. And if you want to turn this into a probability density, you can do so using the Gibbs distribution. And so again, this is the same equation that I just showed. And if you look at this denominator, which is also known as the partition function, which takes the integral over all the possible y's. And by equalizing these two sides, we can derive the energy E of x for any given input in terms of this formula. That is the negative of the log partition function. And so this notion has been around in physics for a long time. And so how is this energy-based model related to neural networks? It turns out a neural classifier can be interpreted from an energy-based perspective. And so, for example, let's consider a neural network, in this case, producing output logits f1x, f2x, and so on. And after softmax, it would produce a normalized probability density, P of y condition on x. So here is the definition of softmax, which you're already familiar with. And so now if we define energy function E of x comma y to be the negative of the logit output, effectively this turns into something that we just saw earlier. And so now recall this is how free energy is defined. In the context of a neural classifier, this free energy replaces the integral with the summation across k discrete classes. And now for every input and a pre-trained neural network parameterized by theta, you can calculate this very conveniently using the log sum exponential operation. And so in this work, the key idea is to replace the softmax confidence score with the energy score for OOD detection. And so with energy scores, the distribution now become much more separable. And in particular, the in distribution no longer have the spiky distribution that we saw earlier. And notice that in the x-axis, we flip the sign to use negative energy score, which, to align with the convention that larger score indicates in distribution and vice versa. And to evaluate our approach, we train, in this case, a model on CIFAR10 as in distribution and evaluate on SVHN as OOD. And so here we measure the performance in terms of FPR 95, which is the fraction of OOD that is misclassified as in distribution when, let's say, 95% of in distribution is correctly labeled. And so we want this metric to be as low as possible. And so if we use softmax score, this FPR is roughly around 48.87. And in contrast, using energy score can reduce this FPR substantially to 35.67. And so we tested thoroughly on more data sets and consistently observed a significant improvement. And so this is again on CIFAR10, and the blue bars are softmax score versus energy score in gray. And I do want to highlight that this advantage of energy score is it's very easy to use, and it doesn't require any hyperparameter tuning whatsoever. And going beyond this empirical performance, we also provided some theoretical explanation for why softmax score is suboptimal for OOD detection. And in order to explain this, we can first look at the training dynamics of neural networks in terms of how they change the energy state of the output. And so here is our standard cross entropy loss for classification. And you can take the negative of the log probability corresponding to the ground truth label. And now we can derive this gradient of the loss with respect to the parameters. You can skip all the details, but what I want to highlight is that the training dynamics essentially push down the energy for our training data, right? So E of X is going to be lower for in distribution. And so now if we look at the softmax score, or precisely the log of the softmax, it can be decomposed into two terms, the energy plus the maximum logic. And recall that the first term is going to be lower for in distribution, and the second term is going to be actually higher for in distribution. And so this summation overall results in a biased function that is no longer aligned with the data density for OOD detection purposes. And so if you're interested, you can check out our papers for detail. We also have a work coming out that bound the performance more rigorously. And so another interesting, nice thing about energy-based framework is that it not only works for the multi-class classification, but also other family of machine learning tasks, such as multi-label classification problem. And this is the recent work in collaboration with Sharon, Weitan, and Alex. And so to motivate the problem, previous studies have primarily focused on this detection in the multi-class setting, where each sample is assigned to one and only one label. And this can be quite unrealistic in real world. For example, if you look at the photos on your phone, most likely, each photo can have multiple objects of interest, right? And also in the medical domain, multiple abnormalities may be present in a medical image. And so the main challenge in the multi-label setting is how do we estimate uncertainty by jointly leveraging the information across different labels, as opposed to just relying on the one dominant label. And in the case of multi-label, you can't really even tractably estimate this likelihood because it requires a sampling combinatorially across different labels. And so this problem is actually harder than multi-class. And so we proposed this novel scoring function that takes into account the joint uncertainty across labels and also provided some mathematical interpretation from a joint likelihood perspective. And in particular, joint energy takes the summation of label-wise energy score. And you can imagine having multiple dominant labels is indicative of in-distribution and vice versa. And despite its simplicity, we show that joint energy can be surprisingly effective and also has this joint likelihood interpretation. I'm not going to the details here for the time being, but just to maybe quickly highlight on the experimental side, the joint energy actually works quite competitively compared to the previous baselines. So I would like to use maybe the remainder few minutes sharing some of the parting thoughts. So in this talk, I've talked extensively about post-hoc OOD detection methods. They're quite powerful, but I think there's a need to move beyond that. They're not sufficient to mitigate this problem of OOD because they don't fundamentally change how the model is trained, right? So if you think about existing learning algorithms, they're primarily driven by optimizing the accuracy on the in-distribution data. And so you can see it as in the middle plot, the decision boundary can actually overshoot and produce overconfident prediction, even though it can discriminate among the three classes pretty well. But they're ill-fated for OOD detection purposes. And therefore, we need training time rigorization to explicitly account for the uncertainty outside the in-distribution data, right? So the ideal decision boundary should be something like maybe the right side, which is more aligned with the in-distribution data density. And so one way to achieve this is using our proposed energy regularized learning, which have this dual objectives during the training time. One for classification, using the standard cross-entropy loss. And so this minimizes the risks on the known data set. And the second term is intended to minimize the risk for the unknowns. And so this regularization essentially shapes the energy surface explicitly using the squared hinge loss and tries to make the energy, as separable as possible between the two types of data, right? So we have this, the first margin, the first loss tries to pull down the energy for the in-distribution data, and the second term tries to push the energy to be high for OOD. And so the result of this training is stronger separability measured by the energy score, as you can see on the rightmost plot here. And in contrast, the left two plots are based on the post hoc methods. One uses softmax score and another one uses the energy score. And both are derived from the pre-trained neural networks. And you can see that the performance gain is actually substantial, reducing FPR down to 1%-ish. And so here I just want to show, evaluation more comprehensively on different test data sets. And the orange bar is when we, employ this regularization during the training time. And our work is also open source. Here is the GitHub link if you're interested in building further and create, even better, stronger solutions on top of it. And moving forward, I think there are great future opportunities when it comes to learning algorithm design. For example, as I mentioned, we really need algorithms that essentially tries to learn a more compact decision boundary that not just care about the in-distribution data, but also the potential risks associated with the unknowns. And you can think of, for example, in this figure, that this black dashed line tries to, wrap around our in-distribution classes while performing the in-distribution classification. And this is the recent work if you're interested in, checking out our papers. And aside from learning algorithm design, there are also great opportunities to think about how we, consider and evaluate a more realistic data model. The current evaluation, as I mentioned, can be too simplified to capture some of the nuances of the problem in the real world. And I'll give you an example here. And so, for example, a lot of the existing work, are evaluated on the common benchmark, CIFAR-10, which contains low-resolution images of size 32 by 32 with a handful of classes. In these methods that work well on CIFAR-10 may not necessarily translate into a real-world setting where we have a lot more visual categories. And as it turns out, OOD detection performance can decrease quite rapidly as with the number of classes increase. And this is because, again, the decision boundary quickly becomes a lot more complex. And so our recent paper develops a group-based OOD detection framework that tries to bridge this gap. And so as you can see that in this plot, the blue curves are using our method, which scales more effectively to the large-scale data sets, say ImageNet with up to 1,000 classes. And as part of the paper, we also released this new benchmark based on ImageNet. And here's the link if you're interested in, creating even better solutions on top of this. And so I think we're almost out of time. I just want to maybe keep this part short. Another interesting research question to think about is how do we actually formalize this notion of, OOD, right? And I think some of the previous speakers has kind of talked about there could be a lot of issues in our training data. And one is, potential bias and spurious correlation in this case, where, the bird species is often correlated with the background. And so what we found is that, when the model is trained with this bias that crept in, it actually would manifest in the downstream OOD detection. For example, the spurious OOD that have the same or similar background information, but with a different semantics, can be really difficult and challenging to be, detected. And so it's important to model this data shift by taking into account both this invariant feature as well as the environmental features. And just to quickly recap and summarize, so today I've started my talk with the post-hoc OOD detection methods, and we've covered some of the common OOD detection score, including softmax score, ODIN, and so on. And energy score further improves on the previous method, and which is also very easy to use and hyperparameter free. And moving forward, there are opportunities of moving beyond these post-hoc methods and thinking about how do we, regularize the learning to minimize risks on both the knowns and the unknowns. And lastly, I've also talked about opportunities for more realistic OOD detection tasks, such as moving beyond CIFAR-10 to larger benchmarks. So with that, I would like to conclude my talk, and thank you all for listening and being here. I'm happy to take questions if there's any, and if we have time.
Thank you so much, Sharon, for that wonderful presentation. Such an important topic, and it's widely applicable. People enter stuff in chatbots, usually out of distribution or could be out of distribution, as well as, of course, medical imaging. And it's really important to catch these cases such that you can reliably deploy your models. So very, very important topic. Thank you for sharing your expertise there with us.
Thank you, Aarti.
Unfortunately, we don't have time to get to all the questions. We'll just stick with the one that got the most upvotes. But again, we will be making note of these and then sending them to Sharon, as well as addressing them in the chat if you have time, Sharon, to stay on. So the top question is from Sebastian. He says, out of distribution detection seems like it's a great way to detect useful data to label. Do you think those high confidence misclassified classes highlight the limited generalization of current models, or how are those two concepts related?
Yeah, that's a really great question. Thank you, Sebastian. As I mentioned in the second part of my talk, I think this fundamental issue of neural networks producing overconfident predictions on this potential OOD data is rooted in how limited the current training objective is, solely focusing on optimizing the classification accuracy without really taking this explicit account of unknowns. And so that's why I think it's very important for the research field moving forward to think about how do we design a training algorithm in a way that factors in both the risks for the known part, which is in distribution, and also unknowns. And so we need that dual objective in this learning algorithm design.
Makes sense. Thank you so much, Sharon, for joining us today. And we will be sending you the rest of the questions that unfortunately we won't have time to get to. But again, thanks for taking the time.
Thank you.
And for our audience members, as always, please take the time to let us know what you think of the conference and how it's going so far, or event in the poll that has showed up here. And again, we will be clearing the Q&A, but please keep adding questions. We will be addressing these in the chat or forwarding them to the speakers. So we will get to these. And now I couldn't be more excited for our upcoming panel. We will have a moderator and two speakers on the panel. Please help me welcome our next panelist. So before joining Snorkel, he worked on Apple iOS as well as various teams within Siri. He's also worked at Microsoft on Visual Studio, which a lot of us use, as well as SugarSync on file synchronization. At Snorkel, he is leading our efforts to support the entire lifecycle of building a machine learning application through our platform, Snorkel Flow. Please welcome Charles Trisuwana-Nukorn. And Charles, I'll leave it to you to introduce our esteemed panelists for today.
Great. Thank you for the kind introduction, Aarti. I'm really thrilled to be with all of you today. What a great audience and lively discussion that we've had so far. And I'm also really excited for our panel discussion on the role of data-centric AI in oversight and control. Today, I'm joined on stage by Darío García-García, who is the director of ML research at Netflix, and Skip McCormick, who is a data science fellow at BNY Mellon, both of whom bring deep experience and unique perspectives on bias and fairness in AI. Darío and Skip, would you please introduce yourselves? Let's start with you, Darío.
Hey, thank you, Charles. Thanks for having me here. It's really a pleasure. So I currently am the director of machine learning research for product at Netflix, where I'm lucky enough to lead a team doing a lot of great research in many fields of machine learning, from causal inference, recommender systems, and computer vision. Before that, I spent a few years at Facebook working mostly first on computer vision and how to make it widely adopted, and then on user modeling and understanding. And before that, I worked in retail banking for a little bit, and then industrial applications of ML before that.
Great. Thank you, Darío. All right, Skip, can we, would you mind introducing yourself?
Sure, no problem. I'm Skip McCormick. I run the data science infrastructure at Bank of New York Mellon. I've been there about 3 years. I'm building the ground truth environment, the actual modeling and data feature engineering environments, both in cloud and on-prem, driving several projects, everything from forecasting trade failures to client attrition, revenue forecasting, forecasting, trade balances, the whole gamut, all the normal stuff. But there's a lot of projects. It's a very exciting opportunity for me. Before that, I was in the federal government. I did predictive analytics, forecasting global instabilities.
Great. Thank you, Skip. Really glad to have you both join us today. So our conversation today will revolve around the topic of bias and fairness and user control, and if data-centric approaches to AI can be effective ways to achieve oversight and give end users more control. Skip, let's start with you. Can you tell us more about the impact of bias in regulated industries?
Absolutely. It's currently sort of the big thing. You can read about it in any article about AI or machine learning. Unfair bias, unfair prejudice, the explainability, that whole set of issues with especially machine learning ties to this idea that you're doing your machine learning on data that's historical data that's based upon previous bias. And the concern is that you're going to take the previous bias and your model is going to carry it forward and add to that a sort of a patina of authority, like, hey, this is an AI model, it's reliable, we can do what it says, but it's just perpetuating an existing bias, and it's a real concern. I think it gets a lot of press because it's sort of the Terminator view of the future instead of the Star Trek view of the future. I'm personally more on the Star Trek side, and my response to that and the firm's approach is there's bias in all data. Every training set has bias in it. Just expect it, embrace it, measure it, build a systematic enterprise-wide ground truth and metrics foundation, so you know exactly what the bias is. So when you get called on the carpet, and every one of us will, and someone says, "Hey, how come your credit model gave a higher credit rating to men and then women?" I mean, that happened last year, right? The answer to that needs to be, we know exactly why it did that, and it was intentional. It's based upon these features. Oh, and by the way, you're cherry picking an example like the Steve Wozniak example. I would like to point out that Safra Katz, who's a female, got a higher credit rating than her husband. It had nothing to do with the gender. It had everything to do with who was the breadwinner, right? Oh, and by the way, if we don't like those results, we have all of the data right here. We can intentionally adjust that bias out if we determine as a civilization and a society that that's unfair and we don't want to do business that way. But that means you do data science. That means you embrace the data, you include it all, and you measure everything you expect it to be there, and you include it in your analysis, and you give a full pedigree and lineage backwards so you know exactly which training data gave you that outcome. So for me, it's a data science problem that you have to, science away and measure and know.
Great, thank you. So just a quick follow-up on that. What kinds of regulations, system checks, and oversights have been effective and can be applied to solve this?
Well, in the banking world, there's a lot of banking regulatory authorities. We have a constant set of bank exams. It's the way we protect ourselves from problems, whether they're intentional or accidental. Bank of New York Mellon is no exception. We get those exams. So far, we've been doing very well on them, and a big part of that success is that we have a systematic enterprise-wide view. We know exactly what's going into the models. We know exactly what's coming out of the models and how they affect every kind of segment you could group the affected parties by. And so you address it with data and solid data science, and that means you have to have a big investment in the infrastructure that supports it. And but that's how we're building our systems. I'm actually quite proud of them. Looking forward to when those questions come, because I view those questions as opportunities for marketing. It's a chance to demonstrate that we know what we're doing, and we can react. We're fair and ethical, and we know what's going on. And if we're surprised, we can fix it right away because we can understand what's going on. Hopefully that makes sense.
Great. Yes. Thank you, Skip. I'd like to maybe take one question from the audience here. Abid Aliawan has asked, what solutions do we have or have you seen for addressing feedback loop biases on machine learning models?
Is that for me, or does Darío want to take it?
I think either of you can handle that one.
I feel like I've been doing all the talking. Darío, you want to take it?
I can talk a little bit about this. I mean, it's definitely a really hard question, right? And I think the point is that not all feedback loops are the same. So I like what Skip mentioned, that many times biases are unavoidable, and measuring and being reactive to them is key. So I would say that this is no different, right? And if I come from the perspective of interactive AI experiences, recommended systems, etc., feedback loops are pervasive in a variety of different shapes and forms. One of the most basic ones being popularity biases, and read gets richer. Others are a bit more complex, like what we can call a simplification bias, right? Many times if a user is very complex, a model that is simplistic would try to look too much into a particular part of the interest space for the user and give them more of that, which in turn may have an effect in actually making that user appear more interested in that. So each one of those different types of feedback loops can be addressed in different ways. But the first thing is acknowledging that they are there, measuring them, keeping track of them, have metrics that can evaluate how good we are doing at addressing them, etc.
I think that's an excellent answer. The only thing I can think of adding is expecting them, right? If we look back at the Google flu trends from a couple years ago, it should have been obvious that by reporting that Google's forecasting flu based upon queries about the flu, it would have been obvious that, oh, this is going to cause a lot more queries, which is going to bias our model. There's going to be a feedback loop. So there's some of it is just experience, having it not be your first rodeo. You know what's going to happen.
Awesome, great. So Darío, let's actually switch gears a little bit. We'd love to hear your thoughts on the impact of bias in AI-based consumer experiences.
Yep, thank you. First of all, I would like to talk a little bit about the word bias because it's very loaded these days, right? I think that, not just machine learning, but learning in general cannot really proceed without bias as a general concept. As the principle of induction, we know that since Hume, right, in the process of collecting observations and making claims based on those observations, there always need to be some type of constraint that we can make how we are coming up with those hypotheses. But I think that nobody or most people don't have a problem with those type of inductive biases, as we call it in machine learning, right? Like, I'm going to use a restricted function class, I'm going to use a linear model, et cetera, et cetera. But then when we go to the next level of biases, we end up with some of the ones that have a clearer regulatory impact, the ones that Skip was talking about, things that are already codified in our law and in our customs as a society, and we want to make sure that our algorithms respect those same customs. But then going even beyond that and thinking from the point of view of AI experiences, there is a whole other set of more insidious but maybe less bad types of biases, which were the feedback loop, as the audience asked about, presentation biases, etc. And I think that many times that's a combination of an algorithmic question and experience design question. Sometimes we design experiences and then we add an algorithm as a black box on top of that to make the experience better. But by definition of the experience, we want to maximize people engagement, etc. That's going to set us down some very particular path. So it's not just the algorithms that introduce the bias here, it's the whole experience. And many times also the way we go around measuring those experiences. If we think about challenges like polarizing content on social media or clickbait, et cetera, I don't think that it's about people making deliberate choices to make that content more prevalent. I think it's just there is a bias towards the measurable for good reasons most of the time. But sometimes, what we can measure effectively in the short term can have unknown effects in the long term. And I think that for humans, it's particularly hard to reason about those type of things, right? I do this thing that seems to make sense, looks good in the short term, but then I set something in motion, some type of chaotic chain of events, and I end up in a world that it was totally impossible for me to predict. So I think that there the key is to be very vigilant, assume that biases are going to be there once again, question every previous decision that we make, because every decision that we make changes the world. So maybe we were making the right decision for the world of yesterday, but maybe it's not the right one for the world of today. So holding ourselves too close to our past opinions, to our past decisions, can have bad effects in this type of insidious biases that are algorithmic and through the experience created and manifested on users. So yeah, I think that ability to be very self-critical is key. And once again, when we are thinking about the experience, accept from the beginning that they are going to be driven by an algorithm and take that into account in the way we design the experience itself, so that the data that the experience provides back to the algorithm is high quality. We have the smallest amount of presentation biases and things like that. And yeah, let's keep this virtuous cycle between the algorithm, the user, each one of them helping each other as clean as possible.
I agree. Stay a fox, don't become a hedgehog. Right? The whole science part of data science means you try to disprove your hypothesis, not try to prove it. Because every model's wrong. Some are useful.
I see. So building on your comments about the experience and making sure to design the experience, if bias is to be expected, and a common problem is that we focus on the things that are measurable and miss other things that make it in front of customers. Uh, what do we do to mitigate that? Like, to what extent is explainability the answer to users, and to tell users and customers, like, this is why the model's making this prediction? To what extent, like, do we need to give users the ability to report problems back to us as we develop models?
Well, my experience is explainability, even if you can do it, is very hard to communicate because it's so complicated. So I lean more on trends. I want independent third-party metrics and a set of an ontology that everybody uses the same terminology. So if I say the precision and the recall and the Breyer score and the data stability, these things have specific meanings, and I have independent third-party metrics I can say. So I can say this model says this. Its precision is 82.5. Last week it was 81. Its recall is 55.6, and last week it was 63, right? And then I can show them that trend. To when you're talking to normal human beings, you sort of approach it like a weatherman. You say, here's where the hurricane is, here's the cone of where we think it'll go, and here's how accurate we've been over time, right? If they say, well, can you explain the weather model to me? It's like, yeah, there's meteorologists who could explain it, but that doesn't mean you'll understand what they're saying. That it boils down to experience and a trend of metrics. What do you think, Dario?
Yeah, I agree. I would add that yeah, giving users the ability to provide feedback is very, very important. And on top of that, that there is always, I think that in almost every aspect of life, a trade-off between robustness and efficiency. So I think that we need to be very aware of that, right? If we try to make our experiences the most engaging, et cetera, we always lose a lot of robustness. And this is related to the point of optimizing for the world of today versus optimizing for the world of tomorrow, right? Evolution in some way is based on a certain level of exploration, being ready for eventualities that maybe have not manifested themselves yet, but may happen. And I think that when we design a complex system that is meant to be used for a long time, we need to draw some inspiration from that, right? And always hedge our bets, don't go too far, have enough exploration, enough randomization, and yeah, acknowledge that our understanding of the situation is limited. So over optimization with imperfect information is not really a good thing. We need to be aware of that noise level and our own limitations as designers of algorithms and designers of experiences, and don't go too far, right? It's the same as if you are measuring something and your ruler can only measure up to millimeters, but I give you 5 decimal points of precision. I think I'm giving you a false sense of security, and that's something for all of us to avoid.
Yeah, I love that analogy. Thank you, Dario. I'd like to switch over to some of the audience questions again. We have one by Sebastian Derry. He asks, assuming that more data leads to better prediction, how do you weigh the incentives of making a better prediction, for example, credit score or movie recommendation, with the privacy of users? Is monitoring a necessary evil?
I guess I don't consider monitoring an evil. In my business, monitoring is a practical reality. We want our banking institutions to be effectively monitored. We want transactions to be safe. We all want our money to be safe. We don't want crime to take place. But I think when we're talking about privacy, just because the monitors need to see the transaction doesn't mean the whole rest of the world needs to see it. And I think I'm seeing this same question occur in large in the whole cryptocurrency realm as well. It's like, yeah, the transactions are public, but the details need to be private. But the right monitors need to be able to see it. So I think it's a matter of appropriate visibility by the appropriate parties, and there needs to be the appropriate controls on inappropriate use of that data. At BNY, we leverage a lot of data masking strategies and a lot of tokenization strategies. A lot of the models you can build without having to know the specific clients. You just need to be able to correlate them, and you can get the right answers. In fact, that's our forecasting Fed eligible security trade fails was done that way. It works perfectly well. So, yeah, I think there's a balance, and I think that's the hint, the essence of the question: is there a balance? And that we have to pay attention to balance as a all together.
Great, thank you. Speaking of balance, we have another audience question here from Marcus Marlou. How do you balance features that mitigate user feedback loop bias but increase overall engagement? Is there an example you can share?
Yeah, so what I would say is that in general, you want to look as much as you can into long-term metrics, because feedback loops, etc., typically they are things that look good in the short term, but then they have unintended consequences in the long term. So the longer you can run your experiments for, or the better you can be at forecasting future behaviors based on short-term trends, the more resilient you are going to be, and the better equipped you are going to be to make the good decisions. So I think that Netflix, for example, has a very thorough culture of looking into the results of experiments. It's not just a very simplistic, it's green, some metric is better than yesterday, so we launch it. There is a lot of discussion, a lot of slicing the data. So far, I would say that there is no substitute to a lot of human judgment and oversight and many eyes looking at the data and asking hard questions about, yeah, these are the numbers that we are seeing, but what's behind these numbers, right? What kind of phenomena are behind this? Are we increasing engagement through mechanisms that are not sustainable or are against our principles and values? I don't know if someday we will be able to automate that. What I like to think is that we will all, as an industry, become more and more mature at knowing which decisions are easy to automate in the sense that they don't carry a lot of risk, and which ones of them are the big ones, and make sure that we put a lot of collective brain power into the big ones. And to be able to do that, we need to automate the others, right? So being very diligent into automating what's reasonable to automate, and not even try to automate things that we are not properly equipped to do so, is the key to some of these questions.
Great, thank you. All right, one last question for both of you. What opportunities does data-centric AI present to improve oversight or to give users more control?
Sorry, I didn't hear the question.
Oh, sorry, can you hear me now? What opportunities does
Yes.
data-centric AI present to improve oversight of ML models or give users more control?
Well, we've been talking a lot about transparency. I think coming up with common expected transparency and expectations of the ability to see the metrics and validate sort of the modeling organizations, at least in the banking world. That's a big part of it. I think it's one of those things that after 2008 we got used to validating quant models and we built controls there. I think we have a similar process here.
Darío, any thoughts?
Yeah, so from my perspective, when we get to the notion of control in my business, is typically a bit about letting the user really have a voice in the experience. And I think that a critical thing to understand there is that control needs to be actionable. And that not giving lower and lower level access to things actually is a good thing, right? In an extreme example, I can give the user access to the weights of a neural network that I used to recommend them something, but what is the narrative that they have about the connection between the actions that they take and the results that those actions have? It's unclear, right? So a lot of it is about designing control mechanisms in a way that are understandable for the user, that they feel empowered to really produce the outcome that they want, because most of the times, the details might not be that relevant, etc. So it's like finding this balance between what was typically the Silicon Valley ideal of experiences that are totally seamless. You don't need to ask the user anything. They just go into a state of bliss and you give them everything that they want. And a world of totally high friction where the user needs to find exactly what they want, right? There is a middle ground that I think that we are all converging into, where we take the good things of the algorithms and the ability to process a lot of data and extract really good patterns, while also preserving the voice of the user. I think the notion of data-centric AI, even ideas like labeling functions, probably we can think about those at a slightly different level of abstraction and just use them as tools for the user to express preferences in richer ways than they can do so today in customer or in AI experiences world.
Okay, great. Well, thank you so much to you both for joining us today, Darío and Skip. It was a really great, insightful discussion. I think it's pretty clear that fairness and bias in AI is both a really important problem that we need to tackle as an industry, but also a data problem. And as a data problem, it requires data-centric tools and data-centric platforms to address them. And it requires a lot of balance, as we've said multiple times today, to make sure that we address them in the right ways. All right. Well, thank you again to you both. And back to you, Aarti.
Thank you so much, Charles, for that wonderful panel. And thank you so much, Darío and Skip, for sharing your insights here with us today. For those of you just joining us, we have a wonderful, exciting day planned for you today. So please post in the chat, introduce yourself. We have over 300 attendees right now, which is quite exciting. And I've been looking at some people's bios. We have people joining us from academia, research, industry. So we'd love it if you could just give a one-liner on yourself. People can DM you as well later to reach out to you. So we hope that you leave with not just new ideas, but new connections. So this is our way of trying to make it as interactive as possible. So please introduce yourself. We'd love to hear from you as well as other attendees. Let us know what you thought about that session using the poll. I think I've gotten the hang of it. That just popped up on my right. So if you could let us know, that'd be great. A quick ping also for the polls tab, which will be on the right-hand side of your screen, where we have polls about your experience in data-centric AI. We will be releasing the results of this poll at a later date. So if you could vote, the more votes we get, the more informative those results will be for you as well. So, and again, thank you so much for joining us today. As a token of our appreciation, we'd love to offer a meal voucher for the attendees wherever possible. So please DM John Marini, and we'll spell his name out in the chat shortly. And you can DM him to get a meal voucher for this event. And so without further ado, I'm really excited to introduce our next speaker for today. Our next speaker has co-founded 4 companies based on his research in machine learning systems, Samba Nova, as well as Snorkel, along with 2 companies that are now part of Apple, Lattice, which was Deep Dive, and Inductive, which was HoloClean. His research contributions have won him the Best Paper or Test of Time Award in premier venues in multiple areas, database theory, database systems, as well as machine learning. He's also won the MacArthur Foundation Fellowship. Currently an associate professor in the Department of Computer Science at Stanford. Thrilled to welcome Chris Ray.
Awesome. Thank you so much for having me. I'm really excited to be here and really excited to be part of this exciting growing community with data-centric AI. It's really early days, but I'm really excited to see all the diverse set of folks who are here and diverse set of ideas. And I want to share with you today some of our work on our journey to data-centric AI and why I'm so excited about the topic, even though it's really early days. So I can get started. So one of the things about data-centric AI is that data isn't new in AI. People have known that data was really critically important for 30, 40 years at this point to a lot of the things that we're going to build. But one of the things that's really changed is that in modern machine learning and AI, our systems and models have gotten really powerful, and they've basically been able to learn a lot of the things that we used to have to tell them manually by hand. Modern deep learning models don't require very careful featurization, where engineers used to encode tons of different bits of domain knowledge. And so in some way, all of the domain knowledge in the world is migrating right into that data. And so often in a lot of the modern AI applications, and increasingly going forward, data is the primary encoding of domain knowledge. So data has now this kind of renewed prominence inside AI. Now, as I mentioned, this data-centric AI thing is something that we've been talking about for a little while. It's amazing to watch the community kind of spring up, and all kinds of folks are contributing. So I thought what I would do is share with you kind of my winding road to get here, the pieces of technical work that I'm sort of most excited about that we did and kind of informed our thinking. And also, if we have time at the end, some of the things that candidly kind of worry me about the next phase of data-centric AI that mean we have a lot of work left to do. So as was mentioned in sort of 2016 with Alex and some other folks, we started noticing this trend that, although models were everywhere and we were really excited to write models, but there's a lot of teams that were really successful because they were looking at the data. And we realized actually the data was being neglected as everyone was so excited about building these, huge models and systems that, frankly, we couldn't have dreamed of building a decade earlier. So we started working on Snorkel back then as a Stanford project. And as mentioned in 2017, I also was fortunate that the first company I co-founded, which was part of my tenure project, Deep Dive, basically took us to Apple with some folks. And what I learned while I was there was that there was still a lot of folks who were struggling to encode their information, their knowledge about a problem in the model. And we kind of coined this kind of ridiculous phrase, new modelitis, to talk about the fact that people were consistently trying to write new models and then kind of failing to get their point across to the AI system. In contrast, those folks who measured the data, who looked at the data, who tried to understand that encoding of the problem more deeply, they were succeeding. And so we started trying to write papers and understand exactly what was going on. Now, on the academic side, we were helped by some unbelievable industrial collaborators. And they realized what our ideas were, even though they were raw and in early stages. And they kind of raced us all the way through research papers, which we wrote, but also all the way into production. So things like Google Ads and YouTube and Gmail all started using ideas that were based on this. In some cases, things like Snorkel Drybo directly related to the kinds of systems that we were building. And so it was a really interesting switch that it happened really so fast, right? It just kind of was one day in the lab, and then it felt like the next was kind of in some ways all around us. And it was kind of really shocking. And so we started to look, as was mentioned, at how else could this impact various different companies and things that were out there. We started looking at how it would affect AI hardware and software, a company called Samba Nova, pioneered by Kunle and Rodrigo, who really recognized that AI was going to be about data flow. Fundamentally, it was about data moving, and that changed the way you build those systems. Snorkel, which you've heard a bunch about how it's about managing the data and the knowledge to build AI applications. And then Inductive, which was about using AI to clean the data. And so as you can see, we've been kind of obsessed with this trend that what's going on at the intersection of AI and data. And now playing around with folks in industry and startups and other places, I started to realize actually there are some very common principles that are coming out in these systems. And I don't claim to know them all, or I don't claim to certainly have invented them all, let alone know them all. But they're these data-centric ideas that are the foundation of long-lived AI systems. And I started to think why these things are new. And one of the reasons they're so new is we really didn't have long-lived AI systems in large numbers even a couple of years ago, right? It's not just an application that you build, but something you're living with in your enterprise every day. The same way you live with a custom CRM or your ERP system or any of your data systems that are your backend. Those long-lived systems, about how you maintain them and work them over time, they just didn't exist, in large numbers. And so this is why I feel like data-centric AI is kind of the right time right now, because people are starting to really deploy these techniques and live with them over time. So now let me give you this kind of high-level story. Now let me tell you my own personal technical story. And, I'm a professor, so I'll rattle on about all kinds of technical stuff. It's kind of what we do. So apologies in advance. Okay. So if you think about a machine learning application, it really has three pieces. There's a model, there's some data, and there's hardware. And what's been really exciting is the model and hardware have gotten really great over the last couple of years. And indeed, state-of-the-art models and hardware are available like never before, right? It's easier to get access to these things. People know about hardware because of the cloud, but also things like modeling. Great folks like places like Hugging Face are putting up these models and you can download them right away. And they're commodities. Everyone's using effectively the same set of modeling resources. But when you go after your particular problem, the data, the training data, well, that's not a commodity. And in some ways, it really can't be. And the reason it can't be is because it's that encoding of your problem. Your problem is not a commodity. It's encoded in all the data that you want to give to these systems to be able to understand the world. Okay? So in some way, it's very difficult for this to become commoditized and downloadable in the way that the others have. Now, when I first started talking about this actually seemed like kind of heresy, because when I teach machine learning, the first content-filled lecture we have in 229 at Stanford is there are X and Y pairs. There's some vector points and some labels. Where did those X and Y pairs come from? Well, we never tell you. It's like they came from God herself. They fell down from the sky and they landed in your lap. And that's when machine learning takes over. But in all those interactions in industry and building applications and scientific things, that was never my felt experience. Instead, I was always in this situation where I was dealing with data not which was given as a static set, but as the result of a dirty, messy process of different sources of data and quality. Now, what, together with Alex and some other folks, we started thinking about was, could you build a mathematical and system structure for this messy process to just make it a little bit less awful? Now, that little bit less awful, by the way, is a huge advance because it was where we were spending all of our time inside these AI machine learning systems. I'll go one step farther than this and argue if you've been paying attention to the machine learning research, supervision is where the action has actually been over the last couple of years. So it's not just that it's important kind of practically or pragmatically, it's also important to push the envelope in the state of the art. And what I mean here is not to suggest that data is more important than models or models are more important than data. I don't need some artificial hot take. These are two important pieces of the pie. But if you look, I would argue modeling differences have been vastly overrated because people like to write models in various different ways. But data differences, because they're in some ways harder to quantify, are vastly underrated and they're sort of bespoke to your application. And so as a result, there just needs to be, we are arguing, more appreciation paid to data. And I think that's really, to me, the core of data-centric AI. What are the foundational techniques, both mathematical, abstractions, that allow us to pay more attention and get better data? Okay. Now, I'm going to tell you a story about some application work that we did with some folks here. Alex and Jared did a bunch of the work and with a bunch of physicians at Stanford. And this was back in 2019. As you'll see, folks were really excited about classifying various different radiographs by AI techniques. Okay. So basically, we were trying to look at these kinds of radiographs that look like this and classify them. And Jared and others spent an entire year basically creating clinical labels, evaluating the effect of label quality, and publishing their work in a clinical journal. When they finished all that, they ran all the models that were available to them. And they found that models like DenseNet, for example, which are very popular, CVPR best paper in 2017, indeed performed the best. Very, very exciting. Okay. Now, those models that are at the top, those are old classical models. Those are models you could have comfortably trained in something like 2010 to run on top of your problem. And the differences in points was only 2 or 3. It wasn't a huge amount. So label quality and quantity, that turned out to be much, much more important than our model choice. And this started really getting me thinking about this process. How can we make that label quality and quantity dramatically, dramatically better? Okay. Now, it's not just there, it's even in the benchmarks. Data augmentation is absolutely critical. If you look across benchmark data, putting those right set of augmentations is one of the secrets of getting high accuracy on almost every model that's out there. And again, this is not to say that this is more important than modeling. It's just saying it's a very understudied and extremely important and not commoditized chunk. It's where you're encoding your knowledge of the problem in some sense. So I just want to point out that this has been something that folks in Snorkel and other places have been active for a long time. And we've been trying to summarize some of this work. But if you look, for example, at things like auto-augment that's out there, very exciting. Well, actually, the first learned augmentation paper was from Henry and Alex, who were doing all kinds of really exciting work in this space. And one of our former postdocs, who's now a professor at Wisconsin, trained this huge model at Facebook with a ton of collaborators, where she realized that using a ton of weakly supervised data allowed her to build the most robust model and the state-of-the-art model on the well-known ImageNet benchmark. So Sharon wrote a great set of blog posts that were on the SAIL blog post, which is a Stanford AI lab about this, and captured a snapshot of kind of where we were a couple of years ago. And this is an evolving area, and I'll talk about later how to capture that evolution in the community in a minute. Now, my point with that is there's many things that you can do in data-centric AI, and it's not a set of tricks. It's really foundational theoretical progress that's being made by the community, and that's what makes this so exciting. I want us to talk about one particular bottleneck that goes on, and explain why there's an opportunity to do something that's even better than what we've seen, kind of in conventional hand-labeled systems. So when you think about training data as a bottleneck, you realize that it has 3 properties. It's slow, it's expensive, and it's static. And that may sound a little bit strange, so let me unpack them for you. So manual labels are slow. Your first label and your last label take about the same amount of time. Humans don't appreciably grow with scale. They're expensive. We were looking at these cutting edge AI problems where we were looking for a phenomenon in videos with radiologists where only about 1 out of 50 people had the abnormality. For them to watch those videos, that meant that they would have to watch 50 videos to find even one positive label. That's a hugely expensive task and just kind of outside the realm of what's possible with manual labeling by orders of magnitude. And a more subtle but more important problem is that you often get the specification incorrect the first time you build a machine learning model. You may think that you want something like positive or negative labels, but actually you realize after looking at the application, you really wanted neutral labels. And unfortunately, the state of the art with hand labeling is just throw away all of those labels and start from scratch. So there are many approaches to this problem that seem compelling and interesting, but I'm going to talk about one that was, foundational for Snorkel and is this idea of programmatic labeling. The idea is that we're going to write a little bit of code and we're then going to be able to write and label tons of things with labeling functions. It's going to be cheap because it's going to run at machine speed, not human speed. And importantly, it's going to allow us to treat the data with some sort of software engineering and data engineering tools that allow us to be dynamic, that allow us to reconfigure the schema and be able to get that out there in a quicker way. Now, all this good stuff comes with a trade-off. And the trade-off is that these programmatic labels may be noisier. They may have correlations among each other. And we're going to have to figure that out. And that's where statistically, we're going to have to make a big set of leaps to figure out that information. And I'll show you that by example. So I want to pause here because there's something really important to me. What we were doing in Snorkel, the academic project, was formalizing things that had gone on for decades. These ideas are not new. The ideas of creating silver standard training examples with the data, which is a core data-centric AI technique, goes back at least to the 90s. Marty Hurst had wonderful talks about this, or wonderful papers about this. We talked about things like distance supervision, using a knowledge base, the Jurafsky-Mintz paper, that take a knowledge base and used it for supervision. Wonderful paper that inspired me. Augmentation I spoke about earlier, topic modeling, third-party models, crowdsourcing. All of these are ways of getting lower quality information, humans who are not experts in the field, to give you feedback. And what our observation was is that these were used in ad hoc and isolated ways. And that was what was holding back progress. How could we take all those different sources that are available to you and combine them? And then the sum of the parts, the whole is greater than the sum of its parts in this situation. It's something that we can build and deploy and really change how you build AI applications. So the goal of Snorkel originally, the academic project, was to replace ad hoc weak supervision with a formal, unified, theoretically grounded approach for programmatic labeling. The company has since grown in different directions to hold the entire workflow and apply this point of view, but I want to talk about where it started. Now, of course, I'm a professor, so I don't really do anything. I just talk like this in little, places like it. The people who do the real work are on the slide here: Stephen, Braden, Henry, Alex, and Paroma, who also, are deeply involved in Snorkel AI. Okay? And they did the real work, and so it's a pleasure to be able to talk about what they did. Now, let me give you a toy example of why I think their ideas are so cool. So what I want to do is something very simple, named entity recognition. I want to go over my document and I want to know which are people and which are hospitals. Okay, so which is tagged as a person and which is tagged as a hospital. So here, Dr. Bob Jones is a person, and St. Francis is not referring to the actual saint; it's referring to the hospital by the same name. Okay? So how would I use weak supervision? And again, this is a super toy example, but it will get across the kind of the main ideas and hopefully inspire you to see why this is a powerful idea. So we're going to look at this, zoom in on the St. Francis example here. So we could use several sources of weak supervision. One is we could have a little Python function that says, well, I have an off-the-shelf classifier, and it says St. Francis is a person because, well, it's capitalized and so on, whatever the classifier that's trained to do. Right? It's our existing classifier. I could also refine that existing classifier and kind of combine it with some extra rules. Unfortunately, both of these things are wrong. I could also use my database of hospital names, which is my distance supervision technique, and label it as a hospital. Say, oh, it occurs there. And the point is, and the problem is, these sources are noisy, they're imperfect, and that's okay, we want them to be. What we're going to do is some smart machine learning to correct them, to decorrelate them. Clearly the first and the second are obviously correlated. And what seems like magic, we're going to do all of it without requiring any hand-labeled ground truth. Okay? And that was the theory that we were looking at. That was what we were trying to do. So this was a flow. People would write labeling functions in the open source. They would then combine them in a model with these noisy things, and we would use probability theory to optimally combine all the information we had about the sources and the functions. And then we would generate probabilistic training data that we could feed to absolutely any deep learning model. And we show you can modify pretty much any of the state-of-the-art techniques to be able to accept data of this form and improve, which is awesome. And the key idea was we wanted, as an art project almost, to say that if we did this, you didn't need to have hand-labeled data. How far could we go? And if you think about the way labeled data is done in industry, it's crazy. You write down a specification, you give it to somebody else, a month or two later, it would come back. And then you would only then start your process. Here, the developer is in that loop. And that's what got us really, really thrilled and excited, that you could get kind of going from the start. And that iteration time we were betting was unbelievably more valuable at a conceptual level. But we have this problem. How do we estimate all those accuracies? And I'll give you a little hint. So it turns out what we've been doing is basically the theory underneath that for years. Here's some recent results. Of course, the first results are 2016. That said, can we learn the accuracy of these annotators without labels? And yes, we can do it now, and with the most recent results, all the way to the information theoretic limits. And if you're not an information theory nerd, like, it's awesome, you should learn about it. Maybe you think it's boring, but I think it's great. Okay. May and Fred did a lot of this work. May is a great student at Stanford, and Fred is a professor at Wisconsin. We asked, could we learn the correlation between annotators without seeing labeled data? And the answer is, under mild assumptions, yes. We don't have any labeled data. You can still provably recover even their correlations, how correlated those functions are. You don't have to tell me in advance. Could you optimally debias? If you know there's particular bias that's difficult to express programmatically, could you do it with labeled data? And it turns out that yes, you can do that in an optimal way from a recent paper from May. Okay. So this is just a sampling. There have been 30, 40 papers published about this by our group, and then there have been workshops and other things. If you're an ML theory nerd, what we're doing here is we're showing how you can learn structure and do estimation for what are called latent graphical models with new results. And in fact, some of the wonderful results of May and Fred even improve the standard supervised case that people have been using, for the last 30 or 40 years, because we've been able to make some really deep connections to results in geometry. So I'd love to talk more about this, but I think I would get the hook from the organizer. So I'm going to move on. Now, when I say all that stuff, and basically my regular demeanor, you'd probably think like this is a bunch of Jokerville stuff, who's going to use it? But what was crazy to me is that in 2018, not only did people start to use it, they started to put it into production. And so these aren't just research papers, these are descriptions of production systems that you've seen and interact with, ads, Gmail, YouTube, that talk about how this changed the way they built the systems. And this was very, very quick after the first papers came out. And as you can see, the Google papers titled Snorkel Drybell, it's very clearly on this system design that we're talking about. Okay, so this has been really fascinating. It's also the case, as I mentioned, that in real industrial systems, even if you have these high resource or low resource kinds of systems, people are using huge amounts of weak supervision in these systems. It's not a kind of afterthought. It is the way that people are constructing them. And that's really thrilling to me, because it means that idea that I was talking about earlier, that we could change the iteration cycle, looks like it's happening in some cases. Super excited about this. Now, it's also in science. I won't bore you with all these details, but I'll just make a couple of quick comments here. The first is that the ideas that were pioneered in the Snorkel, the project, that is the research thing, are around you. It speaks to the utility of these ideas, not how great the execution was necessarily, but that, hey, this focus on the data that we're all excited about, it can have meaningful impacts. There's technical progress you can make that unlocks new capabilities. And that's what I'm, as an academic, most excited about. As Snorkel, the company, recognized that this is actually a much bigger idea. This isn't just about that one pre-production step that allows you to do it. That's important. That's where people are blocked today. That's the most important thing to solve first. But it extends to every other part of the workflow. How do you monitor what you're doing over time? How do you understand the quality of these workflows? How do you get subject matter experts on board? How do you take that domain expertise that's throughout an organization and bring it to bear on your problem? And that's the things that I've been so excited that the Snorkel team has just been building and deploying. And fundamentally, that's the idea of data-centric AI, is to try and figure out, as data is this record of the problem, how do we give you tools to better reflect, to give the best reflection of what you care about inside that data? And there's really good technical reasons, I think, that that's a promising approach. Now, I mentioned earlier that we don't have a lock on this area, and indeed we don't. And so one of the things that we've been creating with others, and this will certainly be out there, is a GitHub by Karan and others, who are looking basically at trying to get a community around all the great tools. You can see all these different topics that are available. And they're talking about, what's going on in these different areas, and it's community contributions that just sprung up. There are going to be workshops and other things that are springing up about this in addition to this one. There's a blog post on sale right now about it, the Stanford AI Lab. just talking about, hey, we're so excited about this, and we recognize so many people have been sharing this idea. We want to try and build a community, and we're really open to suggestions about other ways to drive that community. And I'm very excited about it. It's an open and welcoming bunch, and that's what you need for any kind of these communities. We also just put up a blog post today, which I'll make sure to link out to, which is linked off that GitHub, about what a data-centric AI is not. And I think there's a little bit of confusion because people hear that and think, oh, is this some another wave of data? And it's true, the pendulum swings back and forth between data and machine and kind of model in importance over time. But it's not the case that data was not important and we just recognized it. It's really a foundational claim that the tools of data and statistical distributions are going to play an outsized role in the next phase of building these long-lived AI systems. That's what we're really excited about here. It's a shift in what people have been doing before, but it doesn't obviate all the stuff that came before. It's just a new approach, and it's kind of early days that we've made some of these foundational bits of progress. Now, I want to give you one challenge because I'm an academic. I feel like I'm obligated. I've given you kind of the optimistic take, and I'm an optimist by nature, I'll admit it. But I think there's some things that have worried me about the data-centric AI viewpoint that we have to address as a community. And one is a beautiful problem called hidden stratification that the community has made an unbelievable amount of progress on. Okay? Same cast of jokers, okay? Physicians and ties. So we're looking at that problem again, recall, where there's too many of those radiographs. And we were looking at, if you remember, at those labeled data sets, and there's various different models. And the thing that started to really worry me is, are those 2 or 3 points meaningful there? Is it really better? Is it overfitting to something and that we can't really detect? Because these models are pretty sophisticated. And I got super nervous about it. Now, what do these eyes have to do with it? Just give me a second. So when I started to worry about machine learning, one of the things about machine learning is that, if you could write a perfect Python program to be able to write down your problem, you should do it 100 times out of 100, okay? That's what you should do. You're using machine learning because it's too difficult or expensive to write down. And so what you would expect is that that model is picking up on unintended signals that you can't perfectly describe. These more powerful models, they pick up on more powerful signals. So if we look at these eyes here, one of the interesting bits is that people were trying to classify them as gender, male or female, based on looking at the eyes. And the punchline here is that basically what they were doing was picking up mascara. Okay, that's a pretty crazy signal to pick up with. You would never write that down explicitly. Okay, so it started to make me really worried. Do we know how well these models are performing? Now, it turns out it's not just those eyes. And these folks here, some great radiologists and Jared at Stanford, started to look at this problem. Okay, so here are some melanoma, some surgical marks. What you're seeing is the grad cam. That is where the machine learning model is kind of looking, where it's focused on intensely. And you see that here, in this case, it's focused on the lesion in the slide. Here are 2 purple dots. Those purple dots indicate you're going for surgery. The machine learning's smart. When it sees the purple dots, it says you have cancer. And the reason is it completely ignores, as you can see from the grad cam, the lesion entirely. It's not just those lesions. This is something that Jared published and noticed. Folks were really excited about looking for collapsed lungs and radiologists inside these things. And then they look at these things and they're like, oh my gosh, we have superhuman performance. Awesome, everyone's excited. Who wouldn't be excited about that? We can start deploying this. It's cheap to deploy, it's awesome. Well, there's a problem. The problem is one of these images has a drain and the other one does not. Okay. Now, I can't tell the difference between these two. I'm a machine learning person and I find the human body disgusting. But I'm told one of these contains a drain. And the problem is a drain indicates that you're being treated for the condition we're looking for, same as the surgical dots. There were so many of those images with drains that if you remove them, it's about 1/3 of the images. The model went from superhuman to, as Ben Recht, who's a budding internet troll and Berkeley professor, tweeted out, no better than a first-year resident. Okay. Huge gaps by not looking at the data. Okay. Now, the issue underneath we called hidden stratification. I won't bore you too much with the detail. Basically, a strata says that within a class, there are many individual subclasses, and we want to make sure that we separate them out and see how well we're doing. So we try to develop a theory of this, and I'll leave you with just one interesting idea from these folks. It turns out that those big models actually underneath the covers are doing better. So the model stuff is fantastic, and they're actually separating out those interesting cases that are underneath the covers. And there's been a huge amount of work. And these are some friends at Stanford. That's Tatsu, John, Chelsea, and Percy, who have done amazing work. Check out their Wilds work on robustness. And this has really been something that over the last 2 years, the machine learning community is all over. And I would consider this kind of a core data-centric kind of idea. Now, there's a bunch of other things that are on that blog, that GitHub. Please check them out about declarative systems, how we deal with structured data. But what I want to conclude with is just one simple thing. Thinking about the data has foundational advantages in the theory and algorithmic. And that doesn't mean advantages that are disadvantages in models, but we have tools from statistics for 100 years to do with data distributions. Those are powerful tools. We can use that to analyze the data. That's difficult to analyze the code of a machine learning model. Okay. There's a community that's on the SAIL blog that's starting to talk about some of these ideas. We would love you to contribute. It's an open place. We don't own any of these ideas. And Karan has a weekly show on MLSys that he talks about some of these issues and many others with folks. With that, thank you so much for your time and attention. I really appreciate the opportunity to share this work with you.
Thank you so much, Chris, and thank you for outlining, how we got to data-centric AI, the theory, and a lot of the like how Snorkel came to be, a lot of the theory behind that as well, and just a wonderful presentation, very informative. Thank you. Unfortunately, we don't have too much time for Q&A. We do have a lot of questions popping up, so maybe I'll just pose one of them for the sake of time. Connor asks, can you use the same techniques that you talked about in your talk to predict the accuracy of annotators without labels for pseudo-labeling or self-training?
Yeah, wonderful question. And yes, there's a bunch of connections here. So self-training and self-supervision is really a form of weak supervision in some way, and you can fuse the two. Actually, there's some great work by Hoifeng Poon from Microsoft Research that really makes this formal connection very, very precise and is building upon the Snorkel framework in that way. And this is something also that inside the Snorkel team, they're also doing and providing. So yes, you can bring those two pieces together. They're kind of different pieces of the pie. The challenge with self-training is, it's really an amazing thing to build great representations about common kinds of issues, like the common patterns that you see. But when you have some specific domain knowledge about your problem or some way that you want to treat that data specially, you kind of have to put that in a labeling function. It's not something that a model can learn just observationally from the world. You may also have structured data that you need to be able to measure it that's not in the unstructured data that we don't know quite how to do with self-supervision right now, or multimodal data that you need to fuse. And so self-supervision and weak supervision together is super exciting. And it's a section on the blog that we're talking about. And I'm going to be teaching a course about self-supervision stuff in the winter and hopefully data-centric stuff maybe in the spring to try and explain some of those really foundational connections. But your intuition is directly the same as mine.
Thank you so much, Chris. I'd love to encourage the audience to go check out the blog that Chris mentioned. And thanks again, Chris, for taking the time. Lovely presentation and great to see some familiar faces also on the presentation.
Yeah. Thanks so much for the time. This was a blast.
Of course, thank you. For the unanswered questions, again, we would ask Chris if he could take some time to answer them in the chat. They will disappear after each presentation, but again, we are taking note. And so those are not getting lost there. And again, please share what you thought about this presentation and if you'd recommend this session using the quick poll that pops up on the screen after every talk. Also, please join the Snorkel community to stay in touch. This is where we'll send you updates about what we've been up to. So the link will be in the chat, and also you can get free stickers and socks and all the good things. So again, love to introduce our next speaker. Our next speaker serves as the adjunct assistant professor at the University of Pennsylvania. He received his PhD in computer science from the University of Colorado Boulder and has over 40 plus peer-reviewed publications. He holds over 50 patents with over 100 patents pending. Wow. Please join me in welcoming the principal AI scientist and the director and founder of the machine programming research at Intel Labs, Justin Gottschlich.
Great. Thanks, Aarti. First of all, thanks so much for having me here today. And it's wonderful, actually, to follow right after Chris Ray, especially based on the stuff that he was ending on, which is focusing on self-supervision, because that's actually going to be one of the topics that I discuss in the talk that I'm going to give now. So let's go ahead and dive right in. The quick overview of what I'll be presenting on is broken down to, I'll give a little bit of an insight into machine programming research at Intel. Then I'll, as per always, talk about the 3 pillars of machine programming. And then we'll move into the bifurcated space of MP. And then we will give some examples of the emphasis of machine programming systems at Intel. And then we'll walk through just one concrete example, which is the self-supervised system called Control Flag that we recently built. And we've got some exciting data, I think, to share with all of you today. So for some of you that may not be aware, machine programming is different than machine learning. It's principally about the automation of the development of software, and as a byproduct, the automation of the development of hardware. And MPR, Machine Programming Research, which is the group that I oversee, is a new pioneering research initiative at Intel Labs. Well, what that essentially means is that Intel has made a commitment to this research area for the long haul. And the long haul in this case probably means several decades. Is that we have a very aggressive and a bit audacious charter that I'll talk about in just a second. And we think it's going to take quite a bit for us to achieve all those things. But as we'll see today, that there are incremental improvements that we can make along the way that I think can be viable systems used in industry starting immediately. Very similar to what we're seeing like with Snorkel. So the goals of the two core tenets of MPR really break down into time and quality. So as we are working toward automating the development of software and hardware, what we want to do is achieve at least 1,000x improvement in programmer productivity, or oftentimes I'm now referring to these as software creators, because my belief is we'll move away actually from traditional programmers in the sense we're writing code, and we'll start doing more advanced things that allow people who can't code the ability to create software. Similar to some of the stuff that you're seeing with GitHub Copilot, where you can use natural language in the form of comments, and then out pops a synthesized program that fulfills the semantics and the intention of those comments. So this is the time aspect, is to reduce the overall time it takes by 1,000x. But if we're just synthesizing a bunch of software and the quality of the software that we're creating isn't maintaining some level of bar that we have, it's probably not helping us too much. So simultaneously, as we're focusing on improving the time it takes to develop software, we want to ensure certain quality characteristics that are going to be based on the domain for the software that's being constructed are at some quality level. And so some of those things are performance, correctness, security, maintainability, so on and so forth. And while it may seem as though this idea of reaching these two things, essentially getting 1,000x improvement in our productivity, and then simultaneously achieving superhuman ability in the quality may not be possible, we actually have early evidence that shows that this can be done for some constrained spaces. So for example, if you look at Ahmad's work that was published just a couple of years back on automatically translating image processing libraries to Halide, what you see is that using a fusion of various machine programming techniques that are both stochastic and deterministic in nature, which we'll get to in a second, they were able to achieve a transpiled system that had a geometric mean speed up of 3.36x, which basically means they saw a 200%, so on and so forth, improvement for these transpiled systems. And it was done in an order of several hours in terms of, instead of what one might expect if a human were doing it, that might take potentially months, maybe years. So the three pillars of machine programming now, to switch gears, is kind of the basis of all of the work that we do in machine programming research. And this is a joint work that we published in 2018 with our colleagues at Intel Labs and MIT. And the three pillars are in front of you here. I'll quickly describe them, and then we'll talk a little bit more about them throughout this talk. The first is intention. Intention is principally concerned with the idea of finding novel ways or simplifying the existing ways for humans to express their ideas to machines. And this is really important if we want to get this productivity boost, right? If we can express ourselves to machines in a faster, more productive way, we'll probably become more productive. Intention is also concerned with lifting the semantics of existing code. For example, in the data that I just showed you from the work from Ahmad, they're actually taking existing code, finding a way to lift the semantics in a higher order lambda calculus, and then once the semantics are lifted, then they're able to transpile that to another form and make that code hyper efficient. So intention is principally concerned with these two things. Once intention is known, we move into what we call the invention pillar. Invention is really oftentimes not inventing too much. In many cases, what it's really doing is taking these existing components and it's combining them in novel ways to fulfill whatever the user's intention is. That being said, there are a couple cases that I've seen in the literature where invention is actually inventing what I believe is truly novel. And what I mean by this is it's inventing something that historically the human race, at least what's been documented, hasn't been discovered. And one example of that is potentially the autoperf system that we published at NeurIPS 2019, which is able to automatically synthesize performance regression tests that are able to identify parallel performance bugs that many of the other existing systems couldn't. So if they couldn't, an autoperf can. The idea is perhaps autoperf is actually inventing something that's truly novel. Now, once you have invention captured, and keep in mind, invention, what we generally want with inventive systems are a higher order representation of the program. We want it to be devoid of system level details. And this is fundamentally important because if we miss this aspect, then those systems tend to be hard to maintain. They tend to lose their portability. And they also tend to restrict the machine in the way that it can explore solution spaces and algorithmic rewrites when it moves into the adaptation pillar. So you have a higher order representation from invention. And now we move into adaptation. Adaptation then is principally concerned with taking that higher order data structures and algorithms and then adapting it to various hardware and software ecosystems. So for example, if you were to implement a sort that's going to sort like a couple kilobytes of data on your mobile phone, you might implement it one way. But if you're going to write a sort that's going to sort maybe several petabytes of data on a data cluster, that sort is probably going to be implemented in a very different way. And so this is why it's very important to have sort of the separation of invention and adaptation. But as is apparent with all the other talks that are given today, the fourth sort of hidden pillar in the three pillars of machine programming is all about data. And in fact, as Chris was describing and the other speakers were describing, I think Alex captured this very well, is data is sort of the essential element for all of these machine learning systems. And in fact, for machine programming, which is a space that I've been working in for probably the last 6 or 7 years, there's not a single machine programming system that I'm aware of that's able to do something interesting without some form of data. So we'll talk a little bit about how we can get around some of the issues that we have with data, and there's a lot in the space of machine programming. Now that you have a sort of general understanding of what the three pillars are, I think it's important to talk just briefly about what we describe as a separation of concerns, especially with separation of intention. And the idea here is when we separate intention from invention and adaptation, we restrict the programmer or the software creator from over-specifying details that can then be confusing to the machine to think that they are actually part of the semantics of the program. For example, if you're writing a program and then suddenly you want to do some sort of optimization for like x86 or ARM or something of that nature, and you embed that into the intention, suddenly now that code becomes a little bit more challenging to be portable, to do algorithmic rewrites. So what we want to strive for as we move forward is looking into advances in what we refer to as intentional programming languages, because we believe that these types of languages will help us in many ways. First, it will likely improve our productivity because we're only specifying intention and not the other lower level algorithmic and data structure details or system level details that are specific to software and hardware ecosystems. But in addition to that, it frees up the machine to then more thoroughly explore different types of solutions that if you overspecified those details in the intention, it would likely be bound to that and it wouldn't have the freedom to more exhaustively explore this. And the example here is if you look at Adobe Photoshop version 21, the example that I showed previously with this data is they're doing just that, is the halide programming language and verified lifting, which are the two core techniques that essentially allow them to get this speed up, are both very intentional by nature. So verified lifting is trying to extract out the semantics in a formal way, and then halide is trying to separate out what the algorithmic details are from the scheduling details. And if you're interested in learning more about these things, I encourage you to take a look at this paper. And I think that it's very inspiring on seeing some of the results that we can get when we separate intention from these other pillars. Now, one thing that I think is very important to understand when we think about machine programming is not a rebranding of machine learning. And it's also not ML for code. So I have lots of colleagues that are at various academic institutes and in industry, and some of them will say to me, oh, well, Justin, at Google, we call this ML for code or whatever. And that's great. I think that there is certainly an ML portion to machine programming, but there's also a deterministic side. And this is the side that uses things like formal methods, SAT solvers, SMT solvers. And what we tend to find is that historically in the space of program synthesis, if you don't have deterministic systems, you can't necessarily guarantee correctness the same way that you would be able to if you just built a stochastic system. So oftentimes what you'll see in today's MP systems that are purely stochastic in nature, like GitHub Copilot, is it will give a recommendation on what it thinks the code should be based on the natural language you provide, but it needs a human in the loop. A human must be there to then verify that. However, with the formal methods, the deterministic side of things, it tends to not require that because it is going through some formal mathematical proof, like the work of verified lifting, is that it's doing the semantic lifting to a higher order lambda calculus. It then formally verifies that those semantics are representative of the original program. Now, in this talk, we're going to principally focus a little bit more on the stochastic side. And I think that as most of the audience is aware, when we build these stochastic systems, machine learning or machine programming, they tend to improve with more IID data, independent, identically distributed data. And so if we can look at this a little bit more as we look at the concrete example, but I want to now show you one concrete embodiment of what a new type of approach for machine programming looks like that takes these stochastic and deterministic systems and then gives them a concrete embodiment. And one example is neurosymbolic research. So Armando Solar Lozama, a professor at MIT, recently launched a new 5-year NSF Expedition Center called Understanding the World Through Code. And principally what the center is about is taking these two sides of machine programming and fusing them together. That one embodiment of it is you'll have a neural side, which is shown here on the left, using traditional machine learning techniques with a machine learning neural network that's actually generated from some large amount of data. And then simultaneously, it will fuse what is more of the classical systems using program synthesis techniques in the symbolic space, is that it will take perhaps significantly less data, use a formal synthesizer that has some sort of verification on it, and then out pops a program. And what I'm seeing in the literature, which is really exciting, is that a fusion of these two systems simultaneously lead to some really exciting results. So hopefully now you have sort of an understanding of what machine programming is, what the 3 pillars of machine programming are, and then a concrete embodiment of what I mean by the bifurcated space of machine programming. So at this point, I can go to some of the efforts that we're working on at Intel. I only have time really to talk about one, but I want to give just a little bit of an overview that machine programming is really taking off at Intel. We probably have hundreds, maybe thousands of people working in this space today. For my team, we're principally focusing on debugging, profiling, and productivity. And so those first 3 systems you see there, Control Flag, MISM, and AutoPerf, are all systems that we built out of our lab. And we'll be talking a little bit more about Control Flag, but there's other efforts that are going on. I want to make a quick call out to Intian, which is a new venture that's being led by Intel. I think it's wholly owned by Intel at this point. And they're also working on machine programming systems that are doing things different than some of the historical ML solutions that are doing things like neural programming, where the neural network replaces the code. Intian is still using machine programming and is still using machine learning, but the output is not a neural network. The output is actually code. And part of the reason for that is, as some of the prior speakers noted, is understandability can be often really important. So interpretability. When we have a neural network, sometimes it's challenging to understand. But if we have human readable code, instead of like retraining a whole model, because when we have a bug, if we have code, we could potentially go tweak one line of code and then suddenly everything's good. So this is just a short list of some of the things that are going on, but machine programming is definitely being embraced at a very large scale at Intel. Now, going back to Alex Ratner's introduction, I want to just quickly draw attention to the MISM system that we recently built. MISM is a code semantic similarity system that basically has both a stochastic and a deterministic component on it. The deterministic component is we invented a new structural representation to lift the semantics out of the code that we call the context-aware semantic structure, or CAS for short. Is very much inspired by the fantastic work from Berkeley and Facebook on their Aroma system. But it also has a stochastic component, and the stochastic component is it has a neural engine that then allows it to learn based on the repository that it's being trained on to augment the way that it generates a similarity algorithm. And that part is really important. What's interesting, I find, with MISM, to sort of reinforce the importance that I think Chris Ray was making and Alex was making, several others have made, is that the more data we have, we tend to see better results with these stochastic systems. So in the first line, you see that when we had MISM compared to the state of the art, we were able to get approximately 2x better accuracy across about 400,000 programs. And these were all labeled. So going back to the idea of the need for labels, obviously something very important. The second analysis, which was done independently by IBM and MIT in their CodeNet project, is they showed that MISM compared to the state of the art was actually up to 5x better, but their data set more than doubled. And so we haven't done a deep analysis yet of these results, but our sort of knee-jerk intuition is that one of the big factors here is that the data size has doubled, therefore it's giving MISM more information to learn from, and then that is likely to be one of the fundamental reasons why MISM's accuracy continues to improve, whereas the other systems don't have that stochastic element, and so they stay sort of at this baseline level. But now I want to talk a little bit about what Chris was getting into, is what can we do without labeled data? And this is a new system we built called Control Flag. We published this paper earlier this year at MAPS, the new machine programming symposium. And it's principally about helping us in debugging. So to first quickly motivate why we think debugging is valuable is if you look at a study that was done by the University of Cambridge back in 2017, they break down the cost of software development, and they effectively show that 50% of software development is debugging. Now, these numbers here, the 1.25 trillion, this is back in 2012 or so. We did a sort of back of the envelope calculation, and we believe that it's approximately around 3 trillion today. So that means about $1.5 trillion are being spent in debugging software today. So if we can reduce the time it takes to debug software, we're likely going to have a pretty good impact. So let's dive in on how you might start to debug systems using machine programming. Well, one of the areas is we can do pattern recognition. And essentially, we can try to identify when we find anomalous code segments. And anomalous code segments, in many cases, will lead to stylistic differences. They could be potential defects. They could be security vulnerabilities. And all of these things can delay the delivery of your software, result in loss of customer trust, and so on. A concrete example of what an anomaly looks like is we ran control flag on curl, which is a piece of software that's been around for 30 years. And supposedly, according to the curl team, it's been in, I believe it's used over 1 billion times a day. So we were really surprised when control flag was able to flag this line on 360, which says, this S keep on is greater than true. For those of you who are programmers in C and C++, you probably know that the value false is 0 and any non-value is true. So if any non-value is true, what can be greater than true? So we then reported this to the curl team, and you can see sort of the interchange we had with them. At this point, we hadn't disclosed control flag, so we didn't tell them how we found it. But they confirmed and said, actually, yes, this is not right. Let's go ahead and fix this. And they came up with their own solution, and now that has been integrated into the mainline. Now, there are existing code anomaly detectors that are out there, and different ways that we can detect these things. So oftentimes we'll do things like unit tests, various quality assurance type of engineering. And then there are these static analyzers, compilers, and linters. And we've used these pretty effectively. In Intel, many of the industrial partners we work with, Microsoft and Google, so on. One of the limitations, though, is first, they require that a human manually write these rules, which I think is something that Alex hinted about, how this whole idea of writing rules can be problematic as you want to scale systems out. The second is the manual effort can potentially be error prone. So even if you are writing the rules and you think you've got it right, you might actually get the rule wrong. So how do we overcome this? Well, we overcome it by, at least one potential attempt is with control flag. So in front of you is a very high level diagram of how control flag works. It's a self-supervised anomaly code detection system. And the core idea is that with only using a small amount of metadata in the repositories that we're mining on GitHub that give us some confidence level of whether we can trust them, we then send control flag out to then learn about control structures in these programs. It essentially is given no guidance in terms of there are no fixed rules. We don't tell it what anything means. We just tell it what a control structure looks like and that it should learn what it sees as normal and learn potentially what it finds as abnormal. The takeaway of its design is essentially twofold. First of all, it's self-supervised, so it doesn't require any labels, which is really nice. This is one way we're sort of circumventing the lack of labels on code that exists today. The second is it's self-evolving. So as we throw more data at it, it continues to get better and better. We took control flag, which we invented, I think, last fall, and we had the Neurogen, I think, had the first prototype done in the early spring. And we trained it across 6,000 GitHub repos, trained it on slightly over 1.1 billion lines of code. And then we tested it against a number of open source repositories. And what's interesting is that even the ones that we think are very hardened, like Git, for example, it was able to still find some anomalies that had been overlooked. And thus far, we haven't reported each one of these anomalies just due to lack of bandwidth. But every anomaly that we've reported to the open source community, they have acknowledged that it is a defect, and then they have corrected it and then pushed it into their mainline. But we're also looking at proprietary deployed code. So this one I think is of particular interest. What you're seeing here is control flag. This is obfuscated code. I can't tell you where this code came from, but what I can tell you is it's proprietary and it's deployed. There's actually 3 different bugs in here that control flag was able to identify. The first is very simple. It's a copy-paste error on line 11 and line 12. This is basically just if you updated line 11 or 12 and they're not perfectly in sync, you'll have a potential bug. That's not really that big of a deal. The second is on line 14. I can't go into too much detail of it, but basically, if the value that's being stored in this array is 2, it will pass the mod 4 check as a non-zero value, which will go into that P32 assignment. Because it's doing a pointer 16 offset by 1, it'll jump by 2 bytes. When you dereference the P32, you'll get a 0, and then that'll crash, segmentation fault. It's unlikely for this to occur, but it's still a crash bug. But the third is a bit terrifying. The third is a security vulnerability in line 11. What's happening in line 11 is that's not actually a fixed array. It is a dynamically allocated array from a pointer, but there's no bounds check on that index. This has been confirmed by the group that owns this proprietary software, that we realize that this is a legitimate defect that could be a security vulnerability. It could jump to confidential data. You could actually root a system with this. If I'm a smart programmer, I can get it to jump to a specific location that will then execute my own code, and I can take ownership of your machine. So this is one concrete example of some of the things that Control Flag was able to find. If we take a larger look at that first repo, we scanned this number of files. It took approximately 3 hours. Control Flag is highly parallelizable, and it found 104 confirmed anomalies. We looked at a second repository across 10 million lines of code. It was able to detect 191 anomalies. And according to sort of like these back of the envelope calculations, it's our belief, based on working with these partners, that we are saving on the order of hundreds of millions of dollars because these are in deployed pieces of software. So in conclusion, what I briefly spoke about today is sort of make you aware of the machine programming research charter that we have at Intel. We talked a little bit about the 3 pillars and how separation of intention and lifting semantics from code is important, that we think that the future is intentional programming languages, things like Halide and SQL, which are declarative or maybe slightly intentional, but we expect to see more of that. We tried to go over the bifurcated space of machine programming to talk about how it's stochastic and deterministic. It's not just stochastic, it's not just ML for code. That deterministic part is super important. And then we also look at one example that we worked on called Control Flag, which is a self-supervised system for machine programming. I also would quickly like to blame Alex Ratner. Hopefully, Alex, you're on the line. Alex is a good friend of mine. I've been working with him for several years. I've been trying to get Snorkel to build out support for machine programming to do automatic labeling for at least 2 years, and it still has not existed. So I was forced to invent Control Flag to overcome the lack of labels, and it's my hope that Snorkel folks will work with me to get support on the labeling that we're looking for. So this is my little jab at Alex, and hopefully a slight encouragement to the Snorkel team that we love weak supervision. We don't have enough labels, and it would be wonderful if Snorkel could support automatic semantic labeling for code. And then lastly, my team is hiring. So if you have a PhD and you're interested in this space, please let me know. We will be teaching machine programming fundamentals at Berkeley and MIT this fall. Actually, MP has been taught for several years at MIT already. And then lastly, if you're interested in this stuff, you can stay current with our machine programming website and various YouTube channels. And then lastly, we'll be talking about machine programming in the Intel Innovation event on October 27th. And with that, thank you so much. Back to you, Aarti.
Thank you so much, Justin. That was an amazing talk. Great to learn more about your work. I think a lot of us have heard of like Codex, and it came up in the media recently. And it was really great to learn that it's not just stochastic approaches, but the deterministic approaches as well. So that was definitely a new learning for me. And for our attendees, Justin has discovered a new way to get the entire Snorkel team's attention. Just come be a speaker and ask for support from the Snorkel team. So that's something you're interested in. Please volunteer to be a speaker at our future events.
My goal has been achieved, Aarti.
Exactly. I think a lot of people did pick that up. So we have a lot of exciting questions that have popped up in the chat that I'd like to ask you. So Samdan asks, is it possible to fix the bugs automatically since you're also just, detecting them?
Yeah, absolutely. So right now, Control Flag is both stochastic and deterministic, but we don't quite have the verification that we believe is necessary for the deterministic side in to do the automatic mitigation of those defects. Our goal, though, as this question asker quickly, gets to the heart of, is we do want a closed loop system, and we provide recommended fixes today in control flag, but we still require human verification. Once we add the formally verified component, it's our belief that we can then start to automatically mitigate those. So then it'll identify them, it'll root cause them, and then it'll fix them without any humans.
Wow,
Excellent
that'll be
question.
really exciting and bring down debugging time very effectively. So really excited to see more there. Next question we have from Parth. He asks, wouldn't it be more beneficial to also consider the intent of the code to identify bugs rather than just the irregularity? Or is it the case that 80% of the bugs are just identifiable by irregularity independent of the intent?
No, so whoever asked this question, I love this question. And the truth is, what he or she is suggesting is a much harder problem, but is what we're trying to do. So our next step is we want to fuse control flag with MISM, because MISM can lift semantics. And then we'll be able to gain understanding of the semantics of the code and then see if the semantics then deviate from what would be expected. So control flag is doing, in some sense, this sort of very basic, naive analysis of things, which I think this question asker noted, and that the future is really what he or she mentioned, that we want to be able to do this analysis on a much deeper level, try to understand the semantics of things, and then find much more complex bugs. We're just not quite there yet.
Makes sense. Lots of exciting future work in the area. This seems that a lot of our question askers have picked up on as well. Next question we have is from Vashish, who asked, how costly is it to label, I suppose it's 1 million examples, examples for MISM?
So the truth is yes, this is a great question. I don't actually know the answer. What we did is we used several open source projects that had automatically been labeled. And I think some of them came from some of these coding contests. So one of them was POJ 104. I think that had several 100,000 labeled examples. Another was from Google Code Jam. That also had, I think, maybe upwards of millions of examples. And then the new one is Project CodeNet from IBM and MIT, and they've done the labeling. The truth is, we think that the manual effort to do the labeling, especially because we anticipate the semantics are going to be at various levels, is likely to be massively time consuming. So the idea of doing it manually seems basically intractable for us.
Hence the call for support for Snorkel. It all adds up and makes sense.
It all makes sense now, right, Aarti?
Well, thank you so much again, Justin, for taking the time to be here with us today and teaching us so much about machine programming.
Thank you so much for having me. Yes.
Of course. So again, we'd like to get your opinion on how you thought that session went with this quick poll. Please vote. It'll help us improve our future sessions. For those of you who are just joining us, please enter some info about yourself in the chat functionality. You get to meet other attendees. For the next session as well, we'll be taking a number of Q&A. Number of questions for the speaker to answer. So please enter that in the Q&A tab, also on the right of your screen. And if you are having any issues, there's also the help chat functionality. With that, I would love to introduce our next speaker. So this is our final morning session before we go into a short break / networking session where you will get to meet other attendees. Our next speaker is leading the data-driven network operations with AI in Orange, a telecommunications company in France with 10 plus years experience in smarter networks. And she has a PhD in telecommunications networks from Pierre and Marie Curie University. Please welcome the AI-empowered network program's tech lead at Orange, Imen Grida Ben Yahia.
Hi, everyone, and thank you for inviting me to this very exciting day on data-centric AI. I'm very thrilled and happy to be here today. And thank you for the introduction. So my presentation is on the telco use case perspective that are leading to the, let's say, the transformation of the network toward the data-centric or the data-driven network operation. So this is how we are referring to this movement in the telco world. So to get started, why data-centric driven network operation in the network and in the telco domain? So To show you this, first of all, I would like to highlight the pillars. The network is what we have today and to having this remote, let's say, session on remote conferences, because we have worldwide interconnected equipment, interconnected internet, and this is why we are able to deliver services on top of the network. So the day-to-day life of the operator is to ensure that these services are good quality, that the services are accessible, that the customers are happy with their services, and these are delivered as they were described in the granted SLA. So our pillar for the network transformation, that the network was so much technology centric, we are now moving the network toward the data-driven, transformation, and it is coming also to the network part. So our pillar here today are the automation and AI, and here it will take into account the processes, the information that are coming from the network, from the services where we have our customer expecting the best quality, and also to have, smarter services that will be context following the context of our customers. So the three pillars that we are using here is, as I said, automation and AI, cloudification of the network data. We have per day, we have more than 700 terabytes per day of data, which is only for the network part per day. So it's really huge amount and volume of data. And to do make use of this data in the right way and make of this data enrich our management system in order to bring insight into the network operations, we are relying on AI and automations. So our objective, I said, is to have greater operational efficiency so that we can deliver the services that we are promising. We reinvent the customer experience in order to have our customers satisfied with their portfolio of services, and that they can get, of course, new ones, and have smarter networks, as I said, that will be following the context of the customer and answering their needs and business. So this presentation is more oriented to the use cases that are in the telco world today requiring the AI. And then I will zoom in the last part of the presentation on how it looks like a network data and why the data-centric AI will be a game changer for us to move forward and and accelerate the AI in the network. So let me show you what it looks like today when I talk about operation of the network. It means we are detecting failures, we are detecting incidents, we are detecting customers that are impacted and that they miss, for example, their connectivity. So the operation is all the portfolio of tasks that we as operator, we ensure to make the services available and resilient to our customer. So today, the previous way of doing is that we had different network segments that are segmented by technology. So the access technology of a network, like the base station, the radio aspect, the transport, it's, for example, the IP interconnectivity, and the core network where we have the control plane and the session. So I don't want to enter into the definition of all these network segments and their technology behind, but the network is technology centric. It was built like that. And to be managed correctly, we are putting in place what we are calling the OSS, the operating support system. And when we started the early journey of AI, the mission was to enrich the OSS with machine learning models or with optimization models or whatever smart algorithm that will enable us, for example, to ensure energy savings, to detect congestion, to identify the root cause. So it was incremental enrichment of these management system in order to make sure that we are controlling the network and making the services resilient and available to our customer. This approach that were not at all data-centric, it was technology-centric. It was, as I said, segmented by network management. It was we had a lots of data sources that are disparate and duplicated. So if I want, for example, to make sure that my service that is built end-to-end is working correctly for my customers, I have to take into account data from the access, from the transfers, from the core, and I have to ensure smart correlation there in order to see if my services are going okay, or have degradation, or I have failures, etc. So the fact that it is segmented, it's impossible to have, smooth correlation of data. and ensure this root cause identification or ensure the resiliency of the service. We also, when we are working in siloed mode, we had limited compute and storage. So this was also complex in order to add new data sources to enrich the analysis. So it was not enabling the improvement of the data quality. So the technology-centric in the telco world were, let's say, a bottleneck toward having a data-centric approach, toward having better quality of data. What we are now doing, this is the new move of the paradigm shift or the transformation of the network is toward a network that is more and more software oriented. So what you see here as network segment is now in the movement to be in the cloudified, especially for the access network. So we have, for example, ORAN, which is an open a consortium worldwide that is working on the standardization of the new radio or the new function, while taking into account all the benefit from the cloudifications and the cloud features. So here the shift, as you can see, is that we will be able to collect the data cross network segment. We will still have some let's say management services on premises, but much of the work and much of the analysis will be on the cloud. So in order to have this logically distributed data lake where we will have the data available cross-domain, and this data will enable us to have the end-to-end view in order to be sure that we are monitoring the quality of our service. We know if our customer are, say, impacted, if there is a degradation or not. We anticipate the problem from happening. And of course, we quickly put in place corrective actions if there is an incident or failure. So my take here to share you is that the data-driven operation is to overcome the siloed network segment that were separated by technology, is to make, let's say, advantage of the cloudification and all the advances in the cloud for transforming the network data and building insight for the network management. And of course, the possibility of serving the pipelines in the cloud or serving the pipelines on the management services inside and on premises. So the important part of the slide is to say that we were technology driven and we are now moving to data driven. And with this data driven, we will be able to put in place the data-centric AI and improve the operational aspect that we were dealing with. So in the next slide, I will show you a global view of what I was saying in the previous one, but just to show you the big differences, let's say the three main differences that are ongoing. So we are going beyond use case centric approach for AI and networks toward what if scenario, because we will have lots of data available on the cloud. And from this data, we will be able to correlate. As I said, the network is a big graph of interconnected equipment. And from on top of this equipment and network, we are building a lot of services, communication services to our customers. So the data is disparate, and we have lots of sources of data that we need to take into account to ensure data fusion, data correlation in order to be able to ensure the operation of the network. The second important aspect is that we were rule-based. It means that we are monitoring the network with threshold, with open which, for example, we have service degradation. We have rules to say that if, for example, the connectivity is, for example, at night or during the day or during the summer or during holidays. So here we have threshold based also on the time period and also the events. All these rules are, as you may imagine, static. But today, these rules are, let's say, the core of the management system that we have. But as you can see, this is a very bottleneck approach because it's static. It has to be maintained. It's time consuming, and it is not suitable to the dynamic aspect of the network itself. So the shift that we are taking in the network operation is that we are going to more to the self-learning threshold and proactive detection of deviation. So instead of having the reactive mode, we wait for a threshold to be passed, and then from there we will detect. We will have lots of alarms. We will have lots of alerts, and then we will be in reactive mode trying to overcome the problem and correct the problem. So the goal is to go more and more to proactive management, to anticipate the deviation that we can have in our key performance indicators, and from there we will be able to notify our customer and also to correct the problems in the network as soon as it appears, or in anticipation mode if you are able to forecast it from the beginning. The other aspect that is also changing now in the telco world is that we had the IT part, the network skills, and as I said, fragmented by network domain. The more the network is moving to the cloud and the more the teams are more hybrid. So we have the network expertise, of course, but also more data-centric skills that are helping the network expert teams to build their operation based on the data. So these two slides were to show you that the network is moving from this technology centric approach to the data centric approach. And here the data centric approach is at the level of the architecture, the level of putting all the data together on the cloud, so that we can build the next level that you are talking about in this conference, is the data centric, to move from the models to the data centric operations and approaches. So let's go to the different use cases. So here I wanted to show you how it looks like the operation in the network with AI. So this first use case is on the operation of the transport network. So for example, it could be the IP networks. And in this IP networks, if we have failures in the network, we can analyze the log of our equipment. We can analyze the logs of our PCs. We can analyze the logs of whatever IT systems or telco system in order to detect if what was the problem, or to anticipate the problem. So here we built with different colleagues and experts on the network and experts on data science and engineering in Orange, a pipeline in order to analyze these logs and make sure that we can help the operational team to identify the root cause in less than 5-minute detection. As you can see in this pipeline, there's, let's say, big steps that are, I would say, quite common in different data transformation, but the most important part that plays a role in having let's say, identification of the root cause is the preparation of the data, is all the smart parsing that we did on these network logs and event, in order to be able to apply later several models, because we were consolidating this part. So we had we put a lot of effort here in this preparation of the data before pushing toward the processing of the processing with machine learning and the detection of the outliers. So here it's all millions of network logs that were analyzed, and we have less noisy alarms because of this identification and analysis of the logs. And we build the pipeline on GCP, which is a platform that is also data oriented, and helped us to build the pipeline quickly. So in this use case, the main message is that to analyze the core network flow logs, much of the work was done in structuring this data and cleaning this data, so that we can build the machine learning and identify the root causes as we should be. In the next use case, it's also on the fixed network. So in the fixed network, to help the network technician, to be able to repair to diagnose the problem, or to repair what is the incident in the network, we put in place the AI-assisted field intervention for smarter diagnosis. And this consists of having machine learning models that will identify the root cause and analyze all the information, so that when the technician will go to solve the problem, he has already the probable problem, so that he can ensure the recovery actions quickly and with accuracy, without, let's say, going without any information and without any assisted diagnosis. So so here, sorry, I think I went too fast. Yeah, this one, sorry. Yeah. Oh. Okay. So for the use cases I showed here, it's based on different network data. So it is, for the first one, it's the network logs, the network events. And in the second one, you will have alarms, you will have key performance indicators, you will have the past incident and the historical incident. And the action point, or the most bottleneck that we were facing, is how to bring all these data sources together in terms of temporality, in terms of spatio-temporal analysis, and also in terms of data quality. So here it was a lots of work on the data fusion and data correlation for the second one. And in the first one, it was more spending time on improving the data quality and cleaning the data so that you can process from it the root cause and the problem in the network. So let's discuss on the data-centric AI, and in particular the data labeling in the network data. Yeah, so here, as I said in the previous use cases I was presenting, today we are having thresholds, we are having timers in the network, we are having average, for example, with respect to the latency, or average with respect to the time response, and all this information are rules that we are using to be able to make sure that the quality of service is respected, that our KPI are in the normal mode, and our service level objectives are maintained. So all of this, as you can imagine, are static, and are time consuming to maintain, and also are technology centric. So this is, for example, how it looks like a network data. This is an example of network logs. And here, when you look to this data, it's impossible to go to the millions of lines, as you can expect, and also to the sequences of logs to see if this corresponds to a normal behavior of my network or not. And if even we spend time on the annotation, this annotation is static and also expensive and slow, because it will take time, millions of logs, it's huge. And also, it's not even for the network expert, this is hard to understand if the sequence is corresponding to a normal behavior or not. We need other sources of data to be able to say that. So it is slow, expensive, and static. And this is quite common to several use cases in the network. Another example, so it's also about the key performance indicator. So here, for example, we have voice services, or we have internet mobile services, and here we have key performance indicator that you are following. And these key performance indicators key performance indicators for a given service, we may have some degradation on the service. And when we, for example, put in place anomaly detection models, and then we ask the network operator, the network operational teams to annotate for us, it's difficult to do this for the different shape of distribution, because we don't have one KPI, we have thousands of KPI for a given service. And also going to the annotation of all these points that the anomaly detection is building to, figure out how false positive we are detecting, how false negative we're detecting. So going through this approach, it's not helpful, and it's not easy. And this is to highlight that the data labeling in the network is hard, and the static approach of that is based on the rule is not simplifying, let's say, the operational of the network. So in these two facets, let's say, of the data labeling, we are having with Snorkel teams trials on network data that are very complex. One is on the anomaly detection for key performance indicator, and the second one is on the detection of the classification of traffic to avoid any intrusion, to put in place intrusion detection systems, for example. And we started to have really good results. So let's do that in the next data-centric AI presentation. But this is promising result that we're getting, because we are moving from a completely non-supervised approach where we don't have the labels, and the annotation is just impossible to do, because there's lots of lines to go through, and also lots of sources to take into account in order to label. So this brings me to the conclusion of my use case oriented presentation, that we have the shift on the network operation from the technocentric to the data centric. And there is the shift on the AI operations from the model aspect to the data centric approach, in order to have more, let's say, data quality, and also improve the model, but while improving the data quality. And in the network, this is a must have, because The network data, it's complex, and if we don't have, let's say, the data quality, we don't prepare it, let's say, quite well. It's completely different from, image recognition or NLP, because this domain, it will include textual data, it will include time series data, it will include structured data and non-structured data, and all on the same time that we need to put them in place. So it's very hard and very rich domain where the AI is expected to shift from the static and rule-based toward the pattern detection, with, of course, lots of focus on the data. So our focus is now on the data labeling. This is a problem that is coming to several use cases, and we are exploring the best way to have this automated and put in place, and also cross-domain, as I said. But also in the network data, we have to put in place, the detection of bias, because the network data, it's also about our connectivity, about the customers, about the service. So we need to have, let's say, to put it in the right way, to build the feature matrix with respect to the to the paradigm of responsible AI in general. So this give me conclude my talk, and thank you if you have any questions.
Thank you so much, Imen. That was such a wonderful presentation. Learned a lot about network data. I've personally been working with network data for the first time recently, and just the scale that you work with, it's so large, I guess, because a lot of our attendees / even us, like, mostly on text, but with network, even for analysts or security analysts, it's really hard to label and constantly changing new attack types. So we have lots of questions, exciting questions in the chat. I guess George just joined. So do you mind talking just a little bit about, like, what is network data, or what are some of the characteristics of network data, just for people who may have joined late?
Yeah, so in the network data, we have sources of data like trouble ticket. So the trouble ticket is where we will where we will, let's say, put the information about the incident, about, let's say, the time to repair for this incident, the level of impact, it's a critical incident, it's major, it's informative. So we put all the levels that are required to know. We also put in place the root cause, because when you have an incident, you have a problem, but you don't know what the problem is. So you have lots of columns with the ID of the incident, the time to repair, the possible time to repair, the severity, the description of the problem that were outputted, and then you will have the root cause once it is identified. So it is a live data, this trouble ticket, that cover all the cycle of the incident management. So this is one type of data. So it is a structured data, but in this structured data, you will have a column with a textual data. So you will have, let's say, categorical data with respect to the severity, but you will have to use text and NLP techniques for the analysis of the description of the incident. So it's a combination all the time, just for one source of data. Another source of data is the alarms, and the alarms is all what the equipment are, let's say, are generating when there is a problem. And here again, you will have the severity, you will have the equipment ID, you will have the timestamp. So it's time series data, and the alarms are real time generated and also collected. And this is also structured data with columns that could have these categorical features with the severity, but also the spatiotemporal aspect, because you have the timestamp and you have the geographical location of where the problem or from where the alarm is coming. And the major common type of network data is what we call key performance indicators. So it is of time series type, and the time series type here, it corresponds to, for example, the number of calls on a given service. For example, the voice on 4G or 3G. So you will have the number of calls, you will have the number of successful calls or the number of failed calls. So you will have lots of statistic on different key performance indicators that are standardized today. So we have a different standard working on the KPIs for different services. And from these, let's say, time series type of data, we can build, for example, forecasting, we can build anomaly detection or classification of these network key performance indicator. So if I summarize, you have the trouble ticket, you have the alarms, you have the key performance indicator. Majorly, it's structured data with timestamp and spatiotemporal aspect. And with respect to the logs, the syslog that we can have in any IT system, it's more non-structured data that we need to clean and prepare to move forward. So
Yeah, thank you for outlining that, Imen. I think network data is a new field or at least for a lot of us here in the data science field, and it's exciting to see it like becoming more prevalent. And thank you for outlining those. And just to add to that, yeah, you might have all of the use cases that Imen mentioned, or any cybersecurity use cases where you're trying to also do like hack or threat detection. You also have network data, IP ports information from different machines. Just to add to all of this, George had a follow-up question that these are all labeled data, is it not? So usually, or is it?
Yeah, the problem is that we could say that this data is labeled because, I mean, from an external point of view, we say, okay, we have the indicators, we have the failure, we know the incident, so we are able to label the data. This is the theoretical view. But in reality, you will have the key performance indicator, as I said, coming from, built on top of several equipment. So it's not only one KPI, but thousands of these KPIs. And then you have the alarms. The alarms will be also coming from different equipment that you have to correlate. And then you have the incident management, where you will declare the trouble ticket. When you would like to bring all of this work together, it's difficult to have first the common, I would not say the ID, but the common point that will bring all of this together, because sometimes you have a delay between the alarms and the trouble ticket, the incident detection. And sometimes you will not have all, let's say, the KPI that you need to know, because the ones that will really lead you to identify the root cause are not taken into account. So it's difficult to label. So I will say that we are usually let's say in a noisy labeling, because we can label, but we are not sure if that's really the right labels. We are in use cases with partial labeling, so we have the ground truth, but not for all the data. And for major cases, we don't have the label because the mapping is quite difficult.
That makes sense. Thank you for outlining that, Imen. And also we've seen, like, especially for cybersecurity or network data, you have to use your own network. You can't use other people's data sets generally, because it doesn't generalize. You definitely have to do it in-house. So
exactly.
Yeah, and lots of
and also I would like to add that in the network, maybe for computer vision and for NLP, there is open data that makes the innovation easy in these domains. But for the network, we cannot put the data publicly. It's not our data. It's the network service and customer data. So it's really, with all this privacy aspect, the innovation is, it's slower than in the computer vision and the NLPs also.
That makes sense. Let's take a next question from Mridula. She asks, is the movement restricted to network ops, or also in the way that traffic is perceived and used? That is, in the analysis of the data seen on the wire itself in terms of core traffic KPIs.
Not sure I get the question, but yes, the movement, it's not only on the network operation, it's also for the traffic, if I get it, for the traffic analysis or the, the capacity planning of the network, for the FTTH, as I said, so for the fixed and wired networks. Yes, it is a movement not centric to the mobile, but also for all the network segment, because as I said, it is a movement toward the cloudification of network function. So it is widely a paradigm shift in the network and for the service platforms, for the traffic level. So it is more wider than the mobile part. Yeah.
Makes sense. And then we have a question from Seth. I think that's more directed towards the Snorkel team. So we will have the Snorkel team follow up there. And with that, thank you so much, Imen, for taking the time and for teaching us so much about network data and data-centric approaches there.
Thank you.
And for the audience members, I think you're used to the drill by now, but if you could take a quick second to tell us what you thought of the session and how you're enjoying the conference so far in the poll that will pop up next to me in the screen, that will be really great. It would help us improve our future sessions. And you may also have seen the notification pop up which says Lounge Open. So right now we're going to take a quick break to refresh. We've had a very exciting morning teaching us, about data-centric approaches, how we got here, all the innovation that led us here from both Chris and Alex, also explaining a bit about the Snorkel approach, what is weak supervision, things like that, as well as other approaches in data-centric AI. Justin did a wonderful job telling us about, machine programming, which is a field that I learned about for the first time. It was very exciting to also hear about deterministic techniques. Imen, thank you so much for telling us about, network data, and again, a field that most of us might not be familiar with. Also, Sharon and Anima did some really great deep dives technical deep dives into very real world topics, which is like, how do you deal with out of distribution or calibration of models, things that are really important when you have to deploy models in the real world. And then we also had a wonderful panel that Charles moderated with Darío and Skip, which, managing bias and oversight, again, a very important topic for real world machine learning. So we've had a very, very exciting morning. We have a very fun afternoon for you as well. But before that, we're just going to take a quick break right now. And so for that, we have these lounges open for you. So for the lounges, they are themed. There will be 3 lounges. This is a virtual event. So this is the best you can do to, sort of meet other attendees, meet our Snorkel team members, and, just interact with other people there. So again, thank you so much for joining us. We will see you in a bit. And at 1 p.m., we will have a very exciting session with Zhang, as well as other speakers after that. So to enter the lounge, click the Lounges tab at the top of your screen, and feel free to just take a break, take a walk, get some fresh air, grab a treat, and we will be here at 1 p.m. And the lounges are also open in the meantime for you to get some networking or just meet other people, essentially. Thank you so much. Hello, everyone, and welcome back. For those of you joining us for the first time, welcome. I'm Aarti Bagul. I'm a machine learning engineer at Snorkel, and I am your host for today. We had a very exciting morning with a number of speakers talking about this shift from a model-centric approach to a data-centric approach of building machine learning applications. And we saw speakers talking about everything from machine programming to machine learning data-centric approaches to network data, as well as out of distribution shifts, as well as domain shift. So lots of exciting discussions this morning. We have a very fun afternoon agenda for you as well, which will pop up on the screen right next to me. You can also check that out on the agenda tab at the top. And again, for those of you just joining us, a couple of quick housekeeping announcements. This event is being recorded, and so we will email you the recordings after, as well as you can find it on the website. There's also closed captions available that you can access on the lower right corner where it says CC. There's also a code of conduct for this event, which we've all agreed to when we registered. You can check it out on our website. And then we want to make this event as interactive as possible. So we have a couple of chat functionalities. There's a public chat where you can interact with other attendees as well as the speakers and other Snorkel team members. So please introduce yourself there. Tell us what you're excited to learn about today. We also have a Q&A section. So for our next speaker, we'll actually be doing a number of questions that we will be addressing to him. So please post any questions you might have in the Q&A tab there. We will also have polls coming up regularly, just asking you how you're enjoying the event. We will also have polls under the polls tab, asking you about your experience in data-centric AI. So we will be releasing this results later. So if you vote, that will be more informative for you as well as everyone else involved. Great. Without further ado, I'd love to introduce our next speaker. Our next speaker is a pioneer in both machine learning and online education, and it is not an exaggeration to say that he has changed countless lives through his work in machine learning. Previously, he served as the chief scientist at Baidu, the founding lead at the Google Brain team, and the co-founder of Coursera, the world's largest MOOC platform. I would love to welcome the chairman and co-founder of Coursera, adjunct professor at Stanford University, founder of Deeplearning.ai, founder and CEO of Landing, managing general partner at AI Fund. I don't know how he does it all, Andrew Ng.
Hey, thanks, Aarti. It's good to see you. Had the pleasure working with Aarti way back at Stanford and a few other places. It's nice to see you, all of you here today at this Snorkel event. I've had the deepest respect for Chris Ray and Alex Ratner's work for many years. Alex had the privilege of hosting Alex at the Deeplearning.ai event like a couple months ago, and I'm now really glad to be speaking with all of you here at this event as well. As Aarti mentioned, I think this new UI is great. Would love to hear your comments. Type at me, criticize what I'm saying, and ask questions in the Q&A as well. What I hope to do today is share with you some tips on a data-centric approach to AI. So I know we've been hearing talks all day about data-centric approach to AI, but let me just tell you what I mean and some of the things I saw with the rise of data-centric AI. For many years, decades, the conventional approach to AI was AI systems need code plus data, and many people, including me, would download some data set and work on the code. It was actually thanks to this paradigm of development that I think today, for a lot of applications, the code is basically a solved problem, that open sourcing you download from GitHub basically works well enough. And instead, it's more useful to find tools and processes and principles to systematically engineer the data to make the AI system work. And I know many people talk about this. And I think for many applications, like computer vision, until as recently as 3 or 4 years ago, I think the code wasn't good enough. So in some domains, not all, I think the rise of data-centric AI is actually now's the appropriate time. Whereas in computer vision and speech, I think we frankly weren't ready, say 5 or 6 or 7 years ago. But it does vary by domain. So I started to talk about data-centric AI. So Deeplearning.ai has been working on data-centric AI for a couple of years, building the data-centric MLOps platform for computer vision. I started talking about this in a YouTube video on March 23rd or March 24th. You can still find that YouTube video on YouTube. And I was actually really excited that since the words data-centric AI weren't actually kind of on the internet in this present form at that time. And I was actually really excited that since that presentation, many great companies have started talking about data-centric AI right there on their homepage. Curly Technology raised a bunch of capital to build data-centric AI. I was excited that Scale AI wrote data-centric, right there on the homepage. And of course, deepest respect for really what the whole Snorkel team is doing. But I was actually really excited when, even Snorkel started using the words data-centric AI on their homepage. So with the evolution of a new technology approach, this is the process that we as a community typically go through, right? And so often there starts to be a handful of experts that do something intuitively. In fact, with the rise of deep learning 10, 15 years ago, what I saw was, 15 years ago, there was a bunch of people hacking up neural networks in C++. It was very manual, very error-prone. A few people could get to work. And then eventually, thanks to meetings, maybe like this one and other meetings, the principles become more widespread. And then there were hundreds of people, maybe thousands of people hacking up neural networks in C++. And it kind of worked, but was still error-prone. And eventually, there arose tools like TensorFlow to make the application of this new set of principles and ideas more systematic. So I think that we've actually been in this phase for quite a long time, many years, in the case of data-centric AI, where I think when I was building a speech system many years ago, I would just ask my team to collect more data. But frankly, even I didn't quite know what I was doing. I was kind of doing it intuitively, and many others around the world, applied machine learning practitioners. I think that we are now firmly in this phase of the principles becoming more widespread and more people having this mindset and being able to apply a systematic way of thinking about entering data. And I think we're in the very early phases with companies like Deeplearning.ai, Snorkel, and many others working to create tools that hopefully will enable many people to apply these ideas in a more systematic way. Now, what I thought might be most useful today was I'm going to share with you my top 5 tips for data-centric AI development, so that after this presentation, you can all go and, if you wish, apply these tips. The tips I'm giving are a little bit more applicable to unstructured data, so images, audio, where you can get humans to label the data more easily, and where data augmentation may be a little bit easier. But some of these ideas also apply to structured data or to tabular data. But so I'm going to run through these 5. Feel free to screenshot this if you want and save this for your friends. Right? Make the list consistent. Use consensus labeling, spot inconsistency, clarify labeling instructions, toss out noise examples, use error analysis, focus on subset of data, and improve. So let me dive into these one at a time. Tip 1, make the labels wide consistent. So the best thing for a learning algorithm, or at least it's much easier for a learning algorithm to learn a problem if there is some deterministic, meaning non-random function mapping from the inputs X to the outputs Y, and labels are consistent with this function. If you can engineer a data set to be like this, you can often get things to work with higher accuracy and or a smaller data set. So I've been doing a lot of work at Deeplearning.ai on manufacturing visual defect inspection. And if you're trying to help biopharma inspect pills, so pharma, right, makes a lot of pills, and you want to find defects, like scratches on these. If you have labelers label the pills like these, defect, okay, maybe you have a data set like this. Well, it turns out that if you were to plot stretch length against whether or not there's a defect, this data set, at least plotted this way, looks pretty inconsistent. And you actually see this all the time. Even human expert inspectors or human expert radiologists or human expert whatever, they've done this for years, they will often disagree with each other. And if you're able to spot this problem, how to spot this problem is something I'll touch on later, and sort all the images in order of increasing stretch length and relabel the images so that the ones below, say 2.5 millimeters or whatever, are not a stretch, are not a defect, and things larger than that are defective. So you can ignore the tiny little defects, but the big scratches, boy, that's a defect. If you're able to make the data consistent like this, it turns out to be much easier for the learning algorithm to learn to make accurate predictions. It turns out, I know there's some of you in the audience are very technical. So it's a little bit technical. If M is a training set size, there's a theory from pack learning, realizable versus agnostic learning. But it turns out that if the data set is noisy, if there's no deterministic function mapping for X to Y, your error decreases as order 1 over root M, where M is a training set size. But in some cases, you can prove that if there is a deterministic function mapping from X to Y, your error decreases like order 1 over root 1 over M, and 1 over M as a curve just decreases much faster as a function of M. So your error decreases much faster. Or in other words, you low error or you need a smaller data set size in some cases. Tip 2, use multiple labelers to spot inconsistencies. So if you suspect that labelers are inconsistent in how they're annotating the data, I will often trigger asking 2 labelers or sometimes more to label the same example. So if label 1 labels as a chip, label 2 labels as a scratch, well, that's one inconsistency. And what I want to do is just step through a view some of the most common inconsistencies I've seen in computer vision, but very similar things apply to other forms of unstructured data. So label names, common consistency, or bounding box size. So label 1 says that's this color, label 2 says that's this color. See, this is very common. Or label 3, or third example, number of bounding boxes. 1 labeler draws a bounding box around the chips. Label 2 draws 2 bounding boxes. So I've actually seen all of these in many computer vision contexts, and being able to clean this up significantly improves the learning algorithm performance. And in terms of the iterative workflow of developing machine learning system, when I'm building, computer vision system or other systems, I often will repeatedly clarify labeling instructions by tracking down ambiguous examples. So here's what I mean. When working on a computer vision problem, part of my workflow is now repeatedly try to find examples where the label is either ambiguous or inconsistent, like the examples I showed, right? Number of bounding boxes, the label, then make a decision on how the images should be labeled. And I found that any decision is better than no decision. So just make a decision. Usually any decision is better than no decision. And then document that decision in your labeling instructions. And for a lot of my work at Deeplearning.ai, we found that the labeling instructions is that single source of truth. That is the definition of what is the label Y as a function of X. And labeling instructions should be labeled with examples of the concept. So show some examples of stretch pills, examples of borderline cases and near misses, and any of the confusing examples. And this document, when created properly, significantly increases label quality. Tip 4, toss out bad examples. More data is not always better. If I give you these 6 examples and ask you to train the learning algorithm to detect defects on pills, I don't know. It's like, yeah, there's a lot of stuff going on here. But if you were to spot that 3 of these images are actually poorly focused and have poor contrast, and just toss those out, then even though with half the training set, with just the remaining 3 training examples, this should really clear now. It's much clearer what is the defect you're looking for. So I find that in machine learning, a lot of teams are used to being given a data set and trying to just work on the data set. And I know it feels like almost sacrilege sometimes to say, oh, let's throw some examples away. But that actually often improves the performance of a learning algorithm. Or go back to the camera operator and politely request that they refocus the cameras or change the contrast. And then tip 5, this turns out to be really critical, which is when you're given a data set, there's so many things you can work on. I think what Anima, Anandkumar talked about some really cool data augmentation techniques. So we could pick a category and use data augmentation, or we could clean up some labels, or I don't know, refocus the camera. There's just so much one could be working on. So I found that trying to improve data in a generic way is just too vague. So my typical workflow is now to repeatedly use error analysis to decide what part of the learning algorithm's performance is unacceptable or which you wish to improve. And if, for example, you decide that the performance is not good enough yet on scratches, then that allows you to focus attention on the subset of images with scratches. And this actually takes us to the workflow at the start of clarifying the label instructions of what is a scratch and what is not, and improving label consistency. So one of the still maybe less in this audience, but one of the common misconceptions of data-centric AI is that data-centric is about data pre-processing. I actually, don't love that term because I think that the iterative workflow of developing a machine learning system should involve engineering the data over and over. And so many of you know that building a machine learning system is an iterative process. We create a model, then carry out error analysis to decide on the next step. And then when you decide you want to improve the system, one of the most powerful tools you can use is to engineer the data to fix whatever problems error analysis has shown up. And then you keep on training the model and iterating. So I think of engineering the data not as a pre-processing step, but as a core part of the iterative process of machine learning model development. And so how do you improve the data? Well, these are some things we kind of touched on. You can ask multiple labelers to measure consistency if you suspect why the label Y is inconsistent, or improve the label definitions and then relabel more consistently. So these are some tactics to improve the labels Y. Again, these are slightly more applicable to structured data, but there are other variations as well. Unstructured data, other variations as well to structured data. Or you can toss out noisy examples that improve the quality input X, such as refocus the camera. Or if you find that your algorithm is doing poorly on one slice of the data, then data augmentation can be very valuable for that. So just to summarize, and just a couple more slides to wrap up. I think that improving the data, is not a pre-processing step that you do only once. It's part of the iterative process of model development. I only spoke today about model development. I know that Sharon spoke earlier as well about data drift, concept drift, and how to detect that. But when you see data drift or concept drift, when something in the data tested distribution changes, I find that data-centric tools, closing the loop, taking the production data, spotting the concept of data drift, relabeling it, using that to monitor and maintain the system even post-deployment is an important part of the full cycle of a machine learning project. Listed the tips down below. I hope that if any of you are working on machine learning projects, that you could use these ideas right away. And in the case of computer vision, Deeplearning.ai has been building tools to support implementing these in a very efficient way as well. I want to mention as well, when I talk to people about data-centric AI, I often get deja vu about some of the conversations that I and some of my friends had about a decade ago, or maybe 10, 12, 15 years ago, when we're trying to convince people to join deep learning, to shift the world to deep learning. I think the most important shift that the AI world went through in the last decade was the shift to deep learning. And I think the most important shift the AI world needs to go through in this decade will be a shift to data-centric AI. So many years ago, maybe I'm doing this too long, I and my friends were organizing various workshops to try to gather, the nascent community to drive forward the movement on deep learning. And these days, I'm also involved in organizing, NeurIPS workshop, which we held December 14th, to try to coalesce, leaders in data-centric AI to try to move that forward as well. And I was actually very happy when Chris Ray accepted, our invitation to speak. So Chris always gives great talks. You should come to the nearest workshop to his talk. Hopefully other great talks in addition to his as well. And I think, both, and I think in addition to coming to the nearest workshop, would love to hear any questions, comments you have, and please keep in touch. Social media, or I also write a weekly newsletter in the batch, thebatch.ai, where I often try to share, the latest observations or the latest kind of state-of-the-art techniques to try to keep sharing ideas about data-centric AI. So that's it for my presentation. Thank you very much. We'd love to take questions or Q&A.
Thank you so much, Andrew. I can say I speak for the audience, but that left us wanting more. And also, I really admire the ability, to take learnings from the real world and then also just summarizing that into like actionable tips. I think we saw that also in your like machine learning yearning handbook that a lot of people have read over the years, just very actionable tips on how to improve performance. So great to see that here as well. We have a lot of we have a lot of questions popping up in the audience. So let me just walk through those. Roshni asks, if we toss out noisy examples from the training set, how will the model learn how to handle such examples in the wild?
Yeah, so it turns out, let's see. Actually, let me tell you a story. I think that a lot of us in AI, how to put it? Yes, so it really depends. If you expect to see a lot of those examples in a while, then maybe you need enough examples to have the learning algorithm learn to handle it. But sometimes you just have slightly weird, slightly non-representative examples. And when you have a small data set, if you have 50 examples and 3 of them are weird, that's a very large percentage. That's over 5% of the data set. And you actually do better tossing it out. If you have a bazillion examples, then maybe it's fine. Shove it out and let the learning algorithm sort it out. I find that when you have when you're a consumer internet company with 1 billion users and does a bazillion training examples, bazillion is not a technical term, it's fine. But for almost all other industries where you have fewer than 1 billion users and does fewer than a bazillion examples, often data quality is the critical difference between whether or not you can get the application to work with the 50 or 70 or 100 or 200 examples, which will be all the data that exists in the world.
That makes sense. I recall when working with like defect detection, if it's any good of a manufacturing company, they don't have that many defective samples. So especially in the domains that you talked about, it's really important to feed in clean data there.
In fact, one of the things I'm excited about, I think, because of my leading Google Brain, running at Baidu, I've sort of participated in the AI transformation of some consumer software internet companies. And I think that the hype on AI, is that we'll transform the world or something, which I think we will. But candidly, outside consumer software internet companies like the Google, Baidu, Facebook, Microsoft, and so on, if you look at AI deployments, candidly, I'm not seeing that much of it yet. Right? Financial service kind of getting there, but you've got a hospital, healthcare company, manufacturing company, agriculture company, candidly, there are not that many applications of AI. I think one of the problems is the data set sizes are much smaller. And so part of the key, the recipe to unlocking, taking learning algorithms to all of these other industries will be tools that lets us build and deploy systems with smaller data sets, and data-centric tools, I think, will be a key part of that.
Makes sense. I'm excited to see this new wave of data-centric AI movement and having it unlock, value for the enterprise in addition to the consumer companies, as you've seen. Great. Next question we have from Roberto. Most data teams are afraid of going back and forth to touch a massive data set again. Will a data-centric AI approach allow data teams to iterate on vast data sets?
Yeah, I think it depends a lot on the nature of the data. So I think that, to me, a lot of it is about when you have a very large data set, you don't want maybe the data scientists to be relabeling 10 million examples manually. I think that for problems like that, you may end up having to rely more on automation to detect the problems or maybe fix other problems, or set up processes to have annotators to then gather to then relabel a large set of data. I think the tools and processes does change when you're in a large, very large, handling millions of examples scenario.
Makes sense. Just the scale is different, but sort of similar techniques maybe to weed out noisy labels from smaller as well as larger data sets.
Oh, there is one other thing I want to say. I don't think I have all the answers, just to be completely and just be candid. The way I think about it is about 10 years ago, a lot of people, including me, underestimated the amount of innovation and the thousands of, I don't know how tens of thousands of research papers that would be needed to take deep learning up to the current level of maturity. So I would predict that over the next decade, we may need, like an equally large body of research to flesh out all the labeling tools, data analysis, error analysis tools, how to do agreement-based labeling, consensus labeling, all of these things in order to flesh out a suite of ideas and tools and principles to engineer the data, just like in the last decade we did for the code.
Makes sense. And I think it's really exciting for both of our organizations to be at sort of the forefront of, data-centric AI movement and exploring approaches there. So that's been really exciting. Another question from Roshni. How can we practice data-centric AI application development when we don't have access to the annotators or the data generating infrastructure, like focusing on the camera? And I think this plays into, medical approaches we did where, doctor time is super expensive. So when you don't have access to multiple labelers, what are some alternative things one can do?
Yeah, and sometimes it's tough, right? Actually, I do want to say one thing. I feel like, all right, this is story manufacturing with some details change. But once in a manufacturing context, someone was using a camera to inspect certain parts. And because the camera was not secured well, it just kept on falling. It just kept on slipping downward. And so what the machine learning team did, they trained the system and it worked fine. And then the camera slipped, right, just because of gravity. So the focus changed. So the performance degraded. Machine learning team said, oh, data drift. I got to get more data and train it. So they did. It worked. Camera slipped. They said, oh, data drift. Get more data drift. The camera slipped. And then until eventually a more senior guy said, no, why don't you stop training the model? Just go and tighten the screw on the camera so it stops slipping. I find that robotics researchers are more used to designing the camera system, but I find that the way that AI has grown now, sometimes you don't have control. Is it this image off the internet, you can't change it or whatever. Sometimes it is what it is, but I find that some teams do have you could pay more attention to when you have power to change the lighting or the imaging system. But it's true. So if you have input to X, you can change that. Sometimes data augmentation lets you change X. And even if you don't have Y, and even if X is fixed, sometimes you can still change the labels Y. But sometimes it is true. Data off the internet, giant data set, sometimes it's not going to be easy.
That is definitely a funny and entertaining story about just screwing on the camera. I remember when I used to work at Landing, like back in the day, it was like if the belt changes or lighting changes, it's like, how do you deal with that? And some of the earlier talks today talking about, just detecting that something has changed or out of distribution or things like that is really key to some of those problems that show up later. So that's exciting. Great. We have a question from John. He says, what's the trade-off between cleaning labels versus gathering more data, assuming you have a good held out test set?
Yeah, thank you, John. So let's see. It depends a lot on the application. I'm focusing a lot of my time on I find that for smallish data sets, mid-sized data sets, modern neural networks are basically a low bias but potentially high variance machine. So if you have like 10,000 examples or fewer for a computer vision problem, a modern neural network of reasonable size is just a low bias thing. And so you're fighting variance all the time, hardly ever fighting bias. And I therefore tend to, frankly, spend less and less time on. A good hyperparameter search is important. So do a robust hyperparameter search. But so long as you do that, for a lot of applications, the model is basically a solved problem. Your mileage may vary. This is less true for really, really massive data sets. And then I tend to use an iterative workflow. Aarti mentioned machine learning yearning. That's a kind of a free online book I wrote a couple of years ago. mlyearning.org, I think is the domain name, machine learning yearning, that talks about just some of the practices of error analysis as well to help you systematically make the decision of, do you collect more data, do you use data augmentation, what exactly is the most fruitful next step.
Sense. Thank you, Andrew. Moving on to the next question. We're seeing a lot about like annotators being difficult, but I think you addressed a lot of those questions already. So a little different question. Could you talk a little about machine learning on structured data and any specific tips for structured data? So recent surveys do suggest that structured data still remains the main or even majority data modality in the enterprise. So how would you suggest these tips sort of apply there?
Yep, totally agree. Yeah, one of the double-edged sword, it is true. Majority of the world's enterprise data is structured, but it's actually much more heterogeneous. Unstructured data, like a PNG file is a PNG file is a PNG file. So actually, unstructured data, images and audio, is actually more universal. But most data is structured, but it tends to be much more heterogeneous. I think that just on average, right, structured data harder maybe to rely on human labels. Depending on the application, your mileage may vary, and also when I work on structured data problems, I end up more often engineering features rather than creating brand new examples. So data augmentation, you synthesize new examples maybe, but harder to do that on average for structured data. And we instead do focus on error analysis and then often engineer examples. For structured data, there's actually one thing that I know the panel, what Darío, Skip, and Charles talked about, which is bias. There's one other thing people often don't appreciate about data-centric AI, which is it allows you to engineer one slice of the data at a time, which is why if you find that your system is biased against one demographic, it's actually a very powerful tool for building responsible AI, because how else can you engineer the performance on one subset or one slice of the data? So that's actually one very powerful thing I've seen a lot for structured data, a little bit unstructured data as well.
Amazing. Thank you so much, Andrew. We have a bunch of other questions in the chat. If you could just take the time to answer those in the chat after you're off stage, we'd really appreciate it. But thank you so much for taking the time to be here with us today, for your amazing presentation and for answering these questions.
Thanks, Aarti. Thanks everyone for joining us here today. It's good to be here with you. Thanks for all the questions.
Perfect. Thank you. And thank you so much for our audience members. If you joined us this afternoon, after each session, we're doing a quick poll for you to let us know how you're enjoying the conference so far. So if you could do that, we'd really appreciate it. And as you saw, we're doing Q&A after each session as well. So if you could take the time to add your questions. These will refresh after each talk, but we are noting them down and we're asking if the speakers could stay on to answer them in the chat. So again, your questions are not going away. So we are getting to them. And there are also some other polls under the polls tab, just asking you about your experience in data-centric AI. So if you could answer those, we will be releasing the results at a later date. Amazing. And also, lastly, a quick plug to join the Snorkel community to stay in touch. You'll hear about our future events as well as what we've been up to. And you get some fun things like a sticker and socks. So that's another fun thing there. Amazing. So off to our next speaker. Really excited to introduce our next speaker. He believes that making data and the processing of data easily accessible to non-expert users is a great way to make the world a better place. He finished his PhD round-tripping between the University of Wisconsin-Madison and Stanford University and spent a year as a postdoc at Stanford. He contributed to research efforts that won the Sigmod Best Paper Award as well as the Research Highlight Award. Please welcome to the stage Assistant Professor at ETH Zurich, Zhang.
Should I start? Sorry. Okay, hi everyone. Thanks so much for the invitation. So I'm currently at ETH Zurich. Before that, I was a student with Chris and learned a huge amount of things from him. So today I'm very happy to share with you essentially the thing that we have been working on over the last couple of years, essentially try to understand how can we build data systems to really help the DevOps process of data-centric AI systems. So over the years, we have been looking at how different users are building machine learning applications. And our research is actually governed by two observations. So the first observation is that over the years, we see the continued democratization of machine learning. Machine learning have been applied to more and more applications and have been developed by more and more people. So the consequence of that is if you look at the computer science and machine learning background from many of the users, so it's actually not as strong as a couple of years ago. So they start to have more and more domain experts who are really deep into domain science, start to build machine learning systems all by themselves. And in my opinion, that's really a good thing because we want machine learning application to be developed by people who really, really understand them. So on the other hand, we also see the increased complexity of building machine learning applications and also deploying machine learning applications. So on one hand, hardware are getting more and more heterogeneous, and so does data ecosystems. Data is kind of everywhere, and people start to train machine learning applications everywhere. And the machine learning technology has been rapidly advancing, and also there's also start to have regulations and the requirements beyond getting some model simply have good accuracy. So if you look at these two trends and look at what we have today with all those users building complex machine learning applications with their current machine learning tools, right? I think it's fair to say that it has never been easier for someone to get some machine learning model out of today's AutoML tools. However, I think it's also fair to say that whether this model that they are getting is the right one or is a good one, is getting harder and harder to answer. And also, if they are not good enough, how to systematically improve such a model is also getting harder and harder to answer. So essentially, over the last couple of years, one thing that we really try to understand is how to provide user a systematic step-by-step guideline for the development and the operational aspect of machine learning. If you remember the 5 tips from Andrew's talk just happened, right? So essentially our goal is really try to think about whether we can construct machine learning system and platform to really help our users to enforce those tips, even if they are not really the experts. So we don't know the answer, but this is what we have been working on over the last couple of years. So essentially we try to define an end-to-end process to get the users through the development and operational journey of machine learning applications. This all starts from the data and go through multiple stages, and we actually have some research projects for each of the stage. So first stage is about parsing and augmentation and data injection, and then it's go to another stage that we call feasibility study to really, before you run expensive machine tasks, right, we want to understand whether your data quality is actually good enough or not. And then it goes through the active kind of data cleaning and the data acquisition, right, to really try to improve the data artifact. And then it comes to the AutoML system, give you a stream of machine learning models. Here we also curious about how to do continuous degradation and continuous deliverable, like the delivery of machine learning models, and how can we really continue to optimize its quality and conduct kind of adaptation given the production data stream. So we have been looking at different stage in this picture, and we have 2 observations. So first observation is there are 2 different cycles in this large picture. So the first cycle is actually the data cycle. It's the continuous process of improving the data quality, either by data cleaning or data acquisition. So the second cycle is actually the model cycle, where the model, where the AutoML system give you a stream of models, and then you try to continuous testing and adapt those models driven by your production data. So if you look at these 2 different cycles, you can see all of them are actually data-centric, but they are in different ways. So today, let me tell you a little bit about this small island, this kind of 3 different components. So I will tell you a little bit about what do we know over the last couple of years. And also, I will also tell you the things that we have no idea how to do. And also together with the things that we didn't even know that we don't know, right? So this comes to the components that we are here to actually ask for help from the community to help us to understand how to do this even better. Okay, so for each of these components, they are actually driven by some questions that we want to help our user to understand. So the first question is that if you have a data artifact, a training data, what is the best accuracy that any machine learning model can achieve on this piece of data? So we are curious about this question, not out of the blue, but actually motivated by a real story. So that is a couple of years ago, one of my friends who is a biologist come to me with one data set. So essentially, he's curious about this. He say, okay, can you do some machine learning on this data set? The reason that he come to me is they have been trying to do AutoML on that data set for quite a long time. They try a whole bunch of things, but they cannot get the accuracy that they want. Well, we try to look at the data for a couple of days, and then we go back to him to say, okay, are you sure your data is actually correct? Because if you look at all those different examples, even though they have a very similar features, but they have very different label. So that actually triggers them to actually look at their data set, and after a couple of days, oops, it turns out all the labels are just pure noise. So this actually inspired our journey that we try to understand how can we prevent this from happening. And if you remember Andrew's first tip, right? So when the label Y is so inconsistent, can we build a system to help the user to detect that? So that actually goes back to our first realization that when you are talking about machine learning problems, often they are actually entangled from 2 parts. First one is the data problem, and second is the model problem. And somehow we need to help the user to provide the signal to actually tease them apart. So this is actually a problem that we have been working on for a while. We have a user, we have a data set, could have a whole bunch of problems. It could have missing value, could have noise, and then we have your machine learning technology. So these 3 different players interact in 2 ways. The user comes in with some expectation of what she thinks machine learning can do. For example, she thinks, I really want to get 90% accuracy on this piece of data. On the other hand, machine learning technology also comes in as a limitation. For example, there's no way you can get accuracy higher than 70% because of your data quality issues. One thing we want to understand is really try to check whether this expectation is smaller than the limitation of machine learning. Because if the answer is yes, the user better spend time to fix the data instead of firing up expensive automated runs. If the answer is no, maybe you should just do machine learning on this piece of data. So our goal is really try to understand how can we check this condition as fast as possible. So in the following, let me tell you a little bit about what we know, and also let me also tell you about things that we know that we don't know. Okay, so what do we know? One thing that we know is when training and testing data from same distribution, we actually have some idea about how to talk about this problem. So this goes back to a really traditional problem called the irreducible error, which essentially try to ask for what is the base error rate on this data set. So this is actually a very natural idea. So like assuming you have a two-dimensional feature space, right? They are kind of discrete feature space, right? So, and then if you look at this small bucket, assuming you have a lot of red labels and only a few green labels, right? You know, right? So if you're looking at this cell, right, you have to make the green many errors for this cell, because even the best classifier can only make some deterministic prediction, which if you predict right, so this is actually optimal in this case. And then you take the integral of the whole space, that's give you the base error. So this is actually measures what the best machine learning model can ever give you on this data set. And not surprisingly, people have been working on this for a long, long time, back to the 60s. So this is the first thing that we know. Potentially, this could give you some way to talk about this feasibility study problem for machine learning. So second thing that we know is that if you want to take this collection of net theory and turn them into a practical system, there are actually a lot of things that you need to worry about. So the first question that we were trying to understand is, given all those beautiful estimators, right? So which one is the best? How can we compare them? So if you think about this question, it's actually very hard to understand because all of them try to estimate the base error rate. However, for most of the real world data set, it's actually, you will never know the true base error rate. How can you compare this whole bunch of estimators without knowing the true answer? So we have amazing students, Cedric and Luca, right, try to give us some of his their view in this paper. If you're interested, please check it out. So second question that we are curious about is that how to improve all those base error estimators. So what we actually realize is that if you take into consideration all those pre-trained feature embeddings made available, for example, in TensorFlow Hub, you can actually drastically improve the performance of many of those estimators. Given a data set, you first transform that into multiple data sets, right? And for each one of them, you do a base error estimation and you take the minimum. This actually surprisingly is a principal way for you to get a better base error estimator. So another thing that we know is this actually could be useful, right? So this is actually one on one data set, the x-axis is actually the runtime of system, the y-axis is the error that some machine learning model get, right? So here is state of the art, right? So, and you could run some very expensive machine learning models, right, to try to approach to the state of the art. However, if you do base error estimation, right, using some of the approach that I mentioned, right, you can actually estimate the error that you can that all those machine learning model could converge to, right, but orders of magnitude faster, right? So you can actually inject errors to make the problem a little bit harder, but as you can see, it is actually possible to provide a reasonable estimation for this very important problem. So now there are also things that we have no idea how to do, right? So one thing that we have no idea how to do is actually how to go beyond the view of base error and accuracy. What happens when your training distribution is different from your testing distribution? Whenever you have weak supervision, this could happen, and we have no idea how to model such a problem. How to go beyond accuracy, right? How can you have F1, have AOC, and also how can you deal with other utility functions, for example, robustness and fairness? There are a lot of exciting work that could happen down the road, and we are really here to actually ask for help. So another thing that, given this, right, so let's switch gear and to talk about another problem that we have been looking at. That is assuming this feasibility study step tell you, okay, your data quality is not good enough, right? What should we do? So the second question that we have been looking at is, what is the most important data problem that you should fix in your training data? So here's the problem that we have been thinking about. So assuming you have a training set with a lot of data problems, there's a missing value, there's noise, you train a machine learning model, get a model, and then you measure some of the utilities, for example, accuracy, fairness, or robustness, right? And now it turns out, okay, it's not good enough. And we want to understand, okay, what should we do with it? If you remember Andrew's tip number 4, right? So whenever there's a bad samples in the data set, right, what is a systematic way to tell the user, okay, look at those bad examples. They could be very bad. If you want to toss them out, remove them, right? Our user don't know what machine learning really is, right? How can we enable this step as a systematic functionality inside the system? So we have been looking at 2 problems. The first problem is that there are a lot of data noise in the data example, right? Not all of them are equally important. If you have to clean some data example, which one should you pick to clean? And second is which training example is to blame, or which training example is the bad example for your final utility? How can we answer these 2 questions in a systematic way? So this is really 2 fundamental questions, and people have been looking at for a long time, right? So for the question number 1, there are a lot of research about how to measure the entropy or expectation, right? And also there's some gradient-based method. For example, there's a very cute paper called Active Clean, try to really figure out which example to clean, right? So, and then for the second question about the data importance or data influence, right? So there's a whole bunch of work about how to do Shapley value, how to expect the marginal improvement, right? And also you want to take a gradient-based view, how to do influence functions. So based on all those great work, so we have a little bit of problem of applying them to real-world applications. So the problem is that if you look at a real-world machine learning pipeline, they actually do not look like this. Instead, they look like something like this. If you think about what the whole thing is, there's actually only very small components that the user is actually trying to train a model, and the majority of the program is about data processing. It's actually a data transformation pipeline on the features. If you want to reason about what is a bad example, you have to reason about it in a joint way. You need to reason about these 2 things together. This is actually when we realize that we have no idea how to do that. We are lacking a fundamental understanding of how to connect 2 different communities. So there are the data management people, the data people, try to understand how to talk about those pipelines for decades. And on the other hand, on the machine learning community, we have been thinking about how to reason about data importance for machine learning for the last decade. However, some studies need to put these 2 things together in order to analyze an end-to-end machine learning pipeline. So we have no idea what's the answer, but we have been trying to do a little bit of work to understand a pipeline that looks like this. Essentially, you have a feature extraction pipeline in the middle, and we try to understand these 2 questions. And the thing that we want to understand is how can we compute these fundamental quantities as fast as possible. Again, let me tell you what we know, and also tell you about what we know that we don't know. So what do we know? The first thing that we know is analyzing this pipeline is very hard, especially if you want to compute those fundamental quantities, for example, entropy, right, or Shapley value. However, if you look at a proxy pipeline with giving a whole bunch of heuristics, if you approximate your noise model into a cell-dependent model, if you approximate your feature extraction pipeline by only keeping the provenance, right? So here I use a very weird term called positive relational algebra query. You can think about that as your good old select from where query, right? Like use this kind of data provenance to describe this feature extraction pipeline. And if you approximate the machine learning training process as a simpler classifier, for example, k-nearest neighbor classifier, you get a proxy pipeline. And then we can actually have a p-time algorithm for many of the fundamental quantities for this proxy pipeline. That's one thing that we know. And for different shape of the feature extraction pipeline, you actually have different complexities. So, and second thing that we know is by using these fundamental quantities computed on this proxy pipeline, it actually can be useful and often work well in many scenarios. So this is actually one application scenario that we have. So assuming you have a data set with a lot of wrong labels on your example, right? So, and then you train a machine learning model over it. And the question we want to understand is how can we find out those training examples with the wrong label, right? So in this case, the high level idea is if you look at the Shapley value of those examples, those examples with very small Shapley value, often negative Shapley value, should be the candidate that you should look at. And if you look at the proxy pipelines, and often we can actually give you an n-log n algorithm to compute exactly the Shapley value, which can actually return the Shapley value for all those examples in less than 1 second for a reasonable dataset. And this can actually give you a very powerful way to do data debugging. So here the x-axis is how many data examples that human manually inspect to fix a label, right? If you do random strategy, right, your accuracy is getting better and better, which is great. But if you really go through those examples by following the Shapley value, right, you can actually do that, have an increase of accuracy much, much faster. So third thing that we know is actually, we also know that there are application scenarios by looking at this proxy pipeline where it actually doesn't work well. So let me give you one example. So this is actually one example about fairness. So you have two different populations. One of them is underrepresented, right? So here the problem is, can we identify those already represented examples such that we can remove them and rebalance my data set? So here the high-level idea could be, if you look at those examples with very small Shapley value, right? So highly likely they are those overrepresented examples. So this is actually one of the cases where the idea of using Shapley value actually works really well. However, our proxy model, which actually uses a k-nearest neighbor classifier, actually breaks. So this actually goes to one thing that we are very excited about, because we have no idea how to answer the question, is what is the right way to really talk about a machine learning pipeline. So we all know, right? So on the upper part, that's a realistic machine learning pipeline, very hard to analyze. We focus on this proxy. We know the right answer is in the middle, but we have no idea what that thing is. So second thing that we actually have no idea about is, here we insist that to compute these four fundamental quantities, because I still believe it is the right thing to do. The question is, what is the right way to actually approximate those fundamental quantities, and how can we go beyond this sensitivity style metrics? How can we measure different group effect? That's also another thing I have no idea how to do. So this is actually the two examples that I'm talking about today, right? So this is just a very small picture of this end-to-end process. If you look at many of those components, they are actually asking a data-centric problem. Okay, so that's all I have for today. Thank you for your attention, right? So if you are interested in our project, you can actually go to this two website, right? To like about details. Yeah, so I'm now ready to answer whatever question you might have. Thank you.
Thank you so much for that wonderful presentation, C. And also, you tied it back very well to, the Andrew's 5 tips, and then expanded and elaborated on them and spoke about other things. So that was really wonderful. Learned a lot there. Great. We have some polls coming up, but in the meantime, you mentioned a lot about, like Shapley values. For our users attendees who might be new to that concept, could you elaborate a little bit on how those were calculated, or what the concept is there?
Oh yeah, so Shapley value is a concept have a very solid game theory foundation, right? So essentially, the calculation is actually interesting. You have n different data examples, right? So you want to say, okay, what is the importance? What is the value of one of data example? So the thing you are going to do is consider all the combinations of the rest of the data set. For example, you have 2 to the n-1 number of possible worlds, and then for each one of them, you add back the example that you want to value. You compute the improvement on that possible world, and you aggregate them in a certain way, right? So I think later James is going to talk about data Shapley, right? So he has done amazing work there to really try to initiate the effort of using Shapley value to do some of the data important work, right? Yeah.
Amazing. Thank you so much. Another concept you brought up a lot was, Bayes error, and talked about that and how it's, hard to calculate. And you had a paper on that. So I've seen it generally, even when Andrew's machine learning book, it's you use human performance and a lot of multi-annotators, or, human performance across annotators as a proxy for the Bayes error. So could you tell us a sneak peek? I know you alluded to it about about your paper and, how it goes beyond that, I guess.
Oh, yeah. So there are multiple things, right? So first one is how to estimate the Bayes error, right? So the second one is how to evaluate Bayes error estimators, right? When you don't really know the true answer, right? So again, if you have a data set, right? So if you have a 1 Bayes error, right, which is very close to 0, right? So how to evaluate it is actually pretty hard. So we have one paper about how to do the evaluation there, right? So, and the second is given that we know which estimator perform well, how can we use that to build a system to do feasibility study? Right? Yeah.
That makes sense. Thank you so much for elaborating on that. Next question we have from John. He asks, are you aware of machine learning interfaces that incorporate Shipley values to alert users to address data quality issues?
So that's a very good question. So it depends on how large scale that you're talking about. So personally, I don't know any large scale deployment of Shipley value today, right?
Mm-hmm.
So I know people have been thinking about it for a while, and I have talking to many cloud service providers. Maybe in the near future, they are going to have the Shipley value maybe for the training set, but also Sharp for the feature expandability part. So far, maybe I don't know, but probably I'm wrong. Yeah.
Maybe we'll see a bunch popping up after your talk since they watch this. So we have another question from Seth. He says, is it correct to say that you advocate rebalancing the training data by removing some examples from classes which are overrepresented?
No, I mean, I don't advocate that, right? So, I mean, I'm not an expert in fairness, right? So that's just one example we constructed that we know our approach doesn't work. Whether it's a good way to deal with fairness or not, I'm not an expert. Yeah.
Makes sense. Thank you. Lastly, we have a question from Labe saying, just nice talk. Any comment on research papers addressing label noise like divide mix?
Oh, yeah. So, I mean, they are fascinating, right? So there are different ways that you can actually measure, like try to deal with label noise, right? So I think like Snorkel is fascinating there, right? So like you can actually use different type of signals to help you to fix the label noise, right? So even doing that automatically, right? So there are different ways, right? So we are not trying to replace them, right? So we are actually trying to say, yeah, maybe at some point human can become one of the signal. If you know you have the human time for 1 hour, right? So which component should you focus on such that you can make those automatic approach even better, right? So that is actually our thoughts on this. Another thing is we could use those automatic way of label, like fixing label noise as our candidates, right? For example, we run all of those tools and we get the candidate label, right? And then maybe we can compute some metrics such as entropy to tell us, if you have a human to look at them, this is the place to look at them, right? So that is our hope. And again, we have no idea how to answer that question, but yeah, we have been looking at that for a while. Yeah.
Makes sense. Thank you so much again for the wonderful presentation and for taking the time to answer the audience questions. It was a pleasure having you.
Yeah, thank you so much.
And for our audience members, again, you're used to the drill, but please let us know what you thought about that session using the poll that will pop up. We'd love to hear from you. It would help us improve future events. There it is. And a quick plug again for the polls tab. This is asking about your experience in data-centric AI. So we'd love to hear from you. We'll release these results so you can see what other people have voted as well, and we'll release the results there. If you've just joined us, I'm Aarti. I'm your host for the day. Please take the moment to go to the chat functionality in the public chat. You can message other attendees. For example, Molly has asked how many folks here are with NLP versus computer vision interests. So we'd love to just hear from you, what you've been working on, so you can help us tailor the event a little better as well. And as you saw, we took Q&A from the audience. This is under the Q&A tab. Feel free to add a question. You can also upvote other people's questions. So that's a functionality that you should make use of. In the people tab, you can see who's here with us today. You can DM them. You can video call them. So yes, just trying to make this as interactive as possible. And thank you again for joining us. As a token of our appreciation, we'd love to offer a free meal voucher wherever possible. So please DM John Marini, and you can find him under people, and then DM him for that, and he will reply with a voucher. Amazing. With that, I would love to introduce our next speaker. Our next speaker obtained their PhD degree from the University of Waterloo. He's a recipient of the JP Morgan Faculty Research Fellow Award, the Microsoft PhD Fellowship Award, and the David R. Cheriton Fellowship Award. Please give a warm welcome for Assistant Professor in the School of Computer Science at Georgia Tech, Shu Chu.
All right. Thanks, Aarti, for the kind introduction. It's very nice to be here talking about our work. I should preface this by saying that we've heard a lot of talks about machine learning on primarily unstructured data like images and the videos. I'm going to take a different view because I'm in the database community. We work on structured data a lot. So I'm going to talk about machine learning on structured data. So let's bring up the slides. All right, cool. Yeah, so I'm going to talk about a weakly supervised entity matching system called Panda. So entity matching, for those of you who don't know, refers to the process of determining whether a pair of records from two different data sources refers to the same real-world entity. In this example, as we can see, we have two data sources, two tables, table L and table R. As we can see, a record pair L1 and R1 are actually not a match because they refer to two different TVs. They have different screen sizes. Record pair L2 and R2 are actually a match because they're the same product. And record pair L3 and R3 are not a match because they're two different Microsoft Office products. So entity matching, as you can see, by definition, is a binary classification problem. And it is actually particularly challenging because matching pairs can look very different from each other, and the non-matching pairs can actually look similar to each other, right? And entity matching as a problem has many different applications. For example, in matching products across different retailers for competitive pricing, matching customer databases in enterprises for customer profiling, and in general in data integration and preparation in building knowledge graphs. So entity matching has been studied for quite a while, and in general, right, so in a typical EM workflow, there are two primary steps. The first step is called blocking. The idea of blocking is that given two tables, table L and table R, we want to eliminate a lot of non-matches as quickly as possible to arrive a much smaller set of candidate pairs than the overall Cartesian product for scalability reasons, right? And after we have a much smaller candidate set, the next step is actually to do matching, right? So the idea is that we want to assign a label matching or non-match for every tuple pair in the candidate set. So state-of-the-art techniques for the matching step, not surprisingly, are using supervised machine learning, right? So they require many labeled matches and non-matches in order to train a supervised machine learning model. And nowadays, deep learning model are sort of the state-of-the-art. And it is reported that in order to achieve 90% F1 score, 1 million labeled tuple pairs are necessary. And for the blocking step, right, while there are many different ways to perform blocking, they all still require labeled examples for tuning and learning those blocking parameters so as to make sure that we can eliminate as many non-matches as possible while not actually eliminate actual true matches, right? As you can see, we have many considerations in the blocking step, and the labeled examples are necessary for tuning those parameters. So overall, the main bottleneck for achieving high quality and a scalable EM solution, which are the two main requirements for entity matching in practice, is actually the lack of labeled examples and the high human cost associated with data labeling. So the lack of labeled data examples is not particular to entity matching, right? We've heard about that problem over and over again in this conference. And the recent trend to scale up the data labeling process is to move from this manual data labeling to programmatic supervision, as we've heard from Alex and from Chris Ray in earlier talks. So in the entity matching case, right, manual labeling would require users to label individual tuple pairs as matches or non-matches. And this is not very scalable because labeling the last tuple pair takes as much time as labeling the first tuple pair. And moving on to programmatic supervision. In programmatic supervision, users are asked to write labeling functions. In our case, a labeling function takes as input a tuple pair or two tuples, right? And the users can write arbitrary heuristics in that labeling function. And if they found enough positive evidence, they can return a +1. And if they found enough negative evidence, they can return a -1, non-match. Otherwise, they can abstain, meaning that this labeling function does not know how to label an input tuple pair. Now, by writing labeling functions, the labeling process can be extremely scalable because the entire time, human time, is actually spent in the writing labeling functions. And once we have a good set of labeling functions, all we need to do is to apply those labeling functions to label an unlabeled data set. Now, of course, there's a catch, right? There's a trade-off that we've been talking about, which is that in the manual labeling process, the labels that we obtained are exact labels, while in programmatic supervision via labeling functions, the labels that we get are weak labels or noisy labels, right? And the main challenge of using programmatic supervision is to denoise those potentially noise labeling functions. So to just give a couple of examples of labeling functions that one can write for addressing the entity matching task, right? So this here, we have a labeling function that basically tries to extract, using a regular expression, a screen size information from the description attribute of a tuple pair. And if we can successfully extract two screen sizes and they're different, then we can say, oh, it's not a match, right? Otherwise, it's 0. I don't know, because either the screen size is not available or the screen sizes are actually the same, which does not indicate they're actually matched because there are other considerations, right? And if we apply this labeling function to the 3 tuple pairs, we can see that it correctly labels the first tuple pair as not a match because the screen sizes are different. For the rest 2 tuple pairs, I don't know, it's abstaining, right? So here we have a second labeling function, basically tries to sort of calculate some kind of similarity score using the name attribute. And if the score is below a threshold, then it's a -1. If it's above a certain threshold, it's a +1. Otherwise, I don't know, right? And this is very common in entity matching. Using this labeling function, as you can see, L1 and R1 are abstaining, right? And L2 and R2, this tuple pair, and as well as L3 and R3 are labeled as +1. Now, it is important to note here that this labeling function labels L3 and R3 as +1, which is actually incorrect. But this is okay, right? We're saying that as long as each labeling function is informative and is better than random, it's a good labeling function. And just as a third example, one can also use a numerical column, right, by looking at the price of 2 products. And if both prices are available and they are very far apart from each other, then we can say, oh, they're not a match. Otherwise, we can abstain, right? So labeling function, provides a very nice programmatic interface for users to provide their domain knowledge to do data labeling. And the Snorkel is sort of the pioneering project that embodies the the idea that allows users to write labeling functions. Right? In Snorkel, it has 3 stages. Right? The first stage is, of course, to ask users to write labeling functions, and the second stage is sort of the main technical underpinning of Snorkel, which is that given a set of labeling functions, it can automatically try to learn the accuracy and the dependencies between the labeling functions and can combine them to arrive at the final probabilistic label data, which can then be used to train any downstream machine learning model, right? So being a very successful system, the question is, why can't we just use Snorkel for the entity matching task that we talk about? It is because entity matching has has a lot of EM-specific challenges that the generic data labeling system Snorkel cannot handle very well. The first challenge is that actually it turns out developing high-quality labeling functions for entity matching is not easy. Well, we showed you, 3 labeling functions which all make sense, but actually developing them, arrive at those high-quality labeling functions is a non-trivial task. So if you look at this, one of the labeling functions that I've shown you before, as you can see, there are many choices that need to be made by the user, including how are you going to pre-process the data. In this case, we used a lower casing and then split by space as data pre-processing. What kind of similarity function you're going to use, right? In this case, we used the intersection distance. And what is the threshold that you're going to use in the labeling function, right? As you can see, deciding on those choices are not a trivial, task. And secondly, in entity matching, each example is actually a tuple pair. That is sort of distinct from other data labeling tasks where every example can be considered an IID samples, right? Every example are independent of each other. In entity matching, they're not, right? In entity matching, every example is a tuple pair. And it turns out tuple pair are actually dependent of one another. And in particular, they're related via this transitivity property that says that if Ti and Tj, which is a tuple pair, is a match, and Ti, Tk is also matched, then by definition, right, of entity matching, then Tj, Tk must also be a match, right? And they're related via this transitivity property. And this will break, many of the inference algorithms that people use. And then finally, EM is quadratic, right? You have 2 tables to match, right? Let's imagine you only have 1 million tuple pairs in both tuples in both tables, and it takes only 1 microsecond to apply one labeling function to a particular tuple pair. Now, if you do the math, then it takes 11 days to just run one labeling function, right? And not to mention that you would need to write many labeling functions. So all of these would make Snorkel not very generally applicable to large scale high quality EM tasks out there. So what we did is that we developed a EM tailored weakly supervised system called Panda that addresses those EM specific challenges. Right. For the first challenge, how do we develop high quality labeling functions for entity matching? Well, we did two things. First thing we did is that we developed techniques to try to automatically discover labeling functions to help users to, from the get-go, we provide you with some high-quality labeling functions. And secondly, we developed an EM-tailored IDE, an integrated development environment that guides users in the debugging and writing labeling function process. And for the second challenge, right, where the tuple pairs in entity matching are not actually dependent on another, we developed a constrained labeling model for combining labeling functions, in contrast to the graphic model used in the Snorkel system. And finally, for the quadratic complexity, we developed an iterative and an automated blocking algorithm under the weak label constraint, because we're in a weak supervision setting where the labels are not exactly correct, and this turns out to be extremely challenging for developing automated blocking algorithms. Now, given the 30 minutes time constraint of the talk, I'm going to be focusing on the first two innovations that we did. Right? How do we develop techniques to try to help user develop high quality labeling functions? So the first work that we did is to try to automatically discover labeling functions. And this work was published in Sigma 2021. And it's actually a standalone. It can be used as a standalone work. So what we did is that we sort of packaged that work and we made it into the Python package index, and you can download it and you can use it as a entity matching package on its own, right? But it's also served as a entry point for Panda, which is automatically discover labeling functions. So the main challenge of trying to automatically discover labeling functions is to determine what is a high quality labeling function, right? How do we determine, given a candidate labeling function, whether it is a good labeling function or a bad labeling function, right? And the main intuition that we use to determine the quality of labeling function is by using the reference table assumption. So what is the reference table assumption? It says that, given two tables, table L and table R, although there are many duplicates across the two tables, there are often very few or no duplicates within each table, right? Imagine you're trying to match products across Amazon and Walmart. Of course, there are many, many duplicates across those two retailers, but within each retailer, very few duplicates, right? And this intuition allows us to estimate the quality of candidate labeling functions. And in particular, right, so even though we don't know the ground truth of joining L with R, right, and we do know the ground truth of joining L with L, which is there should be no matches, right? So by leveraging this intuition, we can estimate the precision and recall of candidate labeling function lambda, right? The precision is estimated by the inverse of the number of matches that we can find when applying lambda to join L with L, right? That's the estimated precision. And in terms of recall of lambda, we can simply check how many number of matches can be found when lambda is applied in joining L with R multiplied by the estimated precision, right? Now we have a good estimate of precision or recall of candidate labeling function. We can go ahead and then try to automatically discover labeling functions, right? To do that, we first need to define what is the space of labeling function that we have to consider, right? And let's talk about the single column case where, given two tables, we only have one column, a single column in the input two tables. Now, we looked at, many existing EM work in the literature. It turns out, many of the existing work essentially tries to figure out what are the, parameters for those four parameter choices for those four parameters that I've shown here. The first parameter is that what kind of pre-processing that you're going to do for this data column. The second parameter, how do you tokenize the string or not, right? And the third is what is the kind of weighting strategy you assign for each one of the tokens. And finally, what is the distance function, right? Once you have decided on all the choices for those four parameters, then you come up with some kind of a score, right, for comparing two values in one column, and that score can then be compared with the threshold value, which can then be used for determining matching and non-matching status. And we ended up collecting 140 such featureization functions. And given the space of featureization functions, we can then search within the space and discover those labeling functions that have highest recall while meeting some minimum precision threshold using the estimating the precision recall estimation strategy that we talked about before, right? Now, when we move on to a multi-column case where, in an EM task, we have tables with more than one column, we can simply extend the algorithm we developed before, right? In a multi-column case, we need to decide for each one of the column in our EM task, how are we going to featureize, the similarity calculation, right? And then besides that, we also have the complication of how do we combine all the different scores from different columns, right? And this also results in exponential kind of complexity with respect to the number of columns that we have in our data, in our EM task. So in order to sort of eliminate the exponential complexity, what we did is that we took inspiration from the forward feature selection literature in machine learning, and we designed a forward column search strategy to eliminate the exponential complexity. In particular, our main intuition is that the relative importance between two columns are usually not affected when you're trying to use a new column by adding a new column into the mix, right? So as an example here, let's imagine that in the previous iteration of the algorithm, we have used a name column and description column with respective weights of 60% and 40%. And now in the next iteration, we're trying to use an additional column in the labeling function, right? And instead of trying all possible weight combination, what we did is that we fixed sort of the relative importance between the name and description, as you can see. And we simply need to vary the importance of the third column, whereas the relative importance of the first two columns remain fixed. Now, by doing this, our complexity suddenly becomes quadratic with respect to the number of columns, which is much more manageable, right? Now, it turns out by using this kind of automatic discovery of labeling functions, one can cut down the labeling function development time by half, right? So these two bars here, a blue bar and orange bar, essentially shows the time that users spend in developing labeling functions using the Panda system to achieve the same data labeling quality. As you can see, labeling, using out of J, which is the LF discovery algorithm, one can significantly cut the LF development time. So the second sort of piece of idea that I want to mention to help user develop the labeling functions is we actually developed an IDE interface to guide the user in the process of developing labeling functions. So here is a sort of the screenshot of the IDE, right? So it's it's a browser-based environment. One can run Panda in the backend, open up the browser, and type in the URL. Then you are presented with this an IDE. And as you can see in this IDE, we have a couple of panels, actually 4 panels, right? In the top left panel, you have the EM stats that shows the current statistics of the EM task, right? Including the size of the 2 tables, the candidate set size, how many number of matches have been found by our approach, and the estimated precision, right? And followed by an LF stats panel, which shows all the list of labeling functions that you have so far, right, along with the statistics of each labeling function, including the number of matches, number of non-matches, number of stains, the estimated false positive rate, and estimated false negative rate of each one of the labeling functions. Followed by a data viewer panel, which essentially shows the informative tuple pairs that users can look at and develop the labeling intuitions, right? And at the right side of this IDE is essentially an embedded Jupyter Lab environment where the users can go ahead and actually write and debug labeling functions. And now all of these components are actually interact with each other, right? For example, if you click on an estimated false positive rate of the labeling function, the data viewer panel will automatically show the tuple pairs that a given labeling function labels as positive, while the overall labeling model thinks it should be negative, right? So that users can look at those informative examples and decide to refine those labeling functions. Of course, this IDE also has the capability of showing those tuple pairs that all current labeling functions could not label as a match, but overall the backend algorithm thinks it has a high chance of being a match, so the users can increase the recall of the labeling process overall, right? And I don't have time to show the video, but feel free to go to the link shown in the slides to have a video demo of this IDE, to take a look at the video demonstration of this IDE. So in terms of sort of the overall time savings by using our data labeling system Panda versus the traditional manual labeling, the savings is quite significant, right? So we did experiments on those 4 commonly used EM tasks that people have been studying in the literature, right? And notice that the y-axis here now is a log scale, right? As you can see, for all 4 EM tasks by using Panda, users are able to develop high-quality labeling functions, but essentially in 20 or 30 minutes or so, compared with orders of magnitude slower in terms of using individual data labeling, manual data labeling process. The RF here refers to a supervised random forest model, and the ALRF refers to an active learning model. Basically a smarter way of doing individual data labeling. But none of them are comparable with the labeling time spent in using Panda. Right? So I would like to sort of end my talk by sort of showing all these sort of wonderful set of students and the collaborators that we've done that have contributed to this project. And like I mentioned, right, so this is very much an ongoing project. We've just done some work in helping user develop labeling functions, and there's a lot more work to do in terms of developing EM-specific labeling model to combine labeling functions and dealing with the scalability aspect of labeling in entity matching, right? So with that, I can take any questions the audience may have.
Thank you so much, Zhu. What a wonderful presentation. I think a lot of our participants might not be familiar with entity matching and entity linking. So this provided a great introduction, as well as, LFs that you can write and a good motivation for Panda and how you came with that. So really excellent chat. Thank you. Moving on to some Q&A from the audience. We have a question from Raman saying, what if you want your similarity function to return a probability instead of 1/-1?
Yeah, so that's a good question. I mean, that speaks to sort of the general abstraction of labeling functions, right? Currently, in the Snorkel system and also in the Panda system, a labeling function, in the case of binary classification tasks, returns +1, -1, or 0 abstain. Now, of course, you could imagine that labeling function can be extended to a more general abstraction where instead of returning a binary label, one can return a probability of prediction, right? One problem that I envision with this approach is that the probability across different labeling functions might not be calibrated. So they're not exactly comparable in a sense, which would make the labeling model, designing a competitive, competent labeling model, much more, much harder, right? But I could see that as a valuable avenue to pursue, definitely.
That makes sense. Just to add to that, at Snorkel as well, we provide users to the ability to include probabilistic labels, but then you also have to be mindful of how the downstream classifier model is planning to use it. So, and a lot of times you just end up using the labels, but there's
that makes a lot of sense. Yeah.
Cool. Next, we have a question from Hiromu saying, how much development effort was saved using Panda versus manual LF development?
Yeah, so great question. I mean, that's one thing that we did not include experiment for, because manual alpha development essentially amounts to using Snorkel, at least the academic system Snorkel, where there's no system support for developing labeling functions. And we found out that to be particularly hard for entity matching, because you need to look at relevant data, and the matching pairs in the overall 1 million square number of triple pairs is a very small fraction. It's very hard to pinpoint relevant informative data to write labeling functions without system support. So yeah, that's the point of writing of using Panda. Yeah.
Makes sense. Sort of related question from Parth. He says, this makes me wonder, is there such work in automatically generating labeling functions outside of the EM framework? And he continues, this sounds to me like a program synthesis by example problem where the system generates reasonable labeling function that match a handful of labeled examples.
Yeah, definitely. I mean, I know in the Snorkel project, I know that they have a follow-up work. I couldn't remember the name of it, but they have a follow-up paper that tries to discover labeling functions automatically. But one thing I would like to point out is that in that particular work, I remember they are still using a very small development set to actually, jumpstart the development process. While in our case, we leverage this, very smart, reference table property in entity matching, where we require no labeled example at all to jumpstart the app development process. But yeah, in general, I think any kind of help for users in terms of developing and refining labeling functions would be very valuable in the program and supervision era.
Makes sense. And just to add to that, one of our co-founders, Paroma Verma, I think those were the papers you were referencing, has done some excellent work with Snuba and auto-suggesting labeling functions. And also in Snorkel Flow, the company, we've been adding a lot of this auto-generating functionality. So lots of exciting work there, very cutting edge. Yeah, very exciting. Yeah. Great. Another question from John. He says, active learning has traditionally been used in entity matching problems to improve blocking. Is that incorporated into Panda? And if you could also elaborate on maybe people who are not familiar with entity matching, what does it mean to improve blocking, let's say?
Yeah, excellent question. I mean, like I alluded to in the beginning of my talk, entity matching has two steps: a blocking step and a matching step. In this talk, I mainly talked about the matching step, which is designing a binary classifier to label as match and non-match. Blocking step is to actually improve the scalability of the EM workflow, which is that I want to quickly eliminate a lot of the obvious non-matches, right? So that I can avoid comparing all a quadratic number of tuple pairs. But designing a good blocking strategy itself is not very easy, right? Because you want to eliminate a lot of the obvious non-matches, but at the same time you don't want to get rid of the true matches, because that's what you want to find, right? And that trade-off there requires a lot of tuning. And I guess what the question was alluded to is that tuning process, oftentimes is also not easy, right? And requires labeled example, and active learning is used to provide informative examples for designing a good blocking strategy, right? And I think we are doing something to that extent. We are right now in the process of developing a blocking solution, but in the context of weak labels, as opposed to exactly correct labels traditionally, right, in active learning sense. So we're trying to developing this, automated and iterative blocking algorithm. And by iterative, I essentially, which is similar to the active learning case, where the blocking is not a one-shot process, but at iteratively refining my parameters based on my previous iteration of the labeling result. Yeah.
Got it. Thank you so much for touching on this. This is new to me as well, learning about matching and blocking and how Panda handles that. So very informative to our audience as well. Next question from Anu. She asks, they ask, how are the correlations between labeling functions learned and used in the Panda framework? Oh, so
Yeah, good question. I mean, that's sort of one of the main challenges of Panda and of Snorkel in general as well, right? Because without labeled data, how can you sort of learn the the quality of labeling functions, the dependency between the labeling functions, right? The intuition is that the quality of the labeling function can be learned by examining the agreement, disagreement between the different labeling functions, and because we're operating under the assumption that majority of the labeling functions are better than random. So there is this when you try to aggregate them all, then you are better than using each one of them individually. Then you can iteratively figure out what is the ground truth label, what is the quality, what is the next best labeling result based on my previous estimate quality, and you can start this iteration to figure out the quality, right? In terms of the correlation between labeling function, that's actually more challenging to do. There are many different approaches, which I will not get into. But one can look at the sort of the data sources that each labeling function uses and decide, two labeling functions should be dependent if they use an overlapping data source, right? Otherwise, they may not be dependent of each other. Yeah, but yeah, definitely, those two aspects are sort of the primary technical aspects of trying to combine labeling functions.
Makes sense. Very similar techniques or topics here with Snorkel as well as Panda, which makes sense.
Exactly.
Labeling functions applied to a task. Great. Next question from Roshni. She asks, what methodology was used to ensure that model performance was equivalent as you compare how long it takes in minutes across Panda, RF, ALRF, etc.?
Yeah, great question. I mean, this is sort of speaks to the evaluation methodology that we use. So what we did is that we first sort of used Panda to to get some labeling results, which is used to to train a random forest model, and then we used that performance as sort of the number that we want to reach if we were to do individual data labeling, right? So we label more examples, until at a point that performance is achieved, so that we are comparing apples to apples.
Sense. Thank you. Next question from Ramin. He says, if I know a labeling function is weaker than other or can sort them manually, can I inject that information to help the system better label?
Right now, the Panda system does not support that, but that is definitely a valuable information to have because learning the accuracy of labeling function, like I said, it can be quite challenging. And in fact, we did many ablation studies, for the capability of our labeling model, and we found that in a lot of cases, if you can eliminate some bad quality labeling functions, the overall labeling result can indeed improve a lot of the times, right? But identifying those itself is a challenging task, and if users are able to provide that, then that could be helpful. Yeah.
That makes sense. And empirically at Snorkel, at least, we have the ability for users to sort of trust certain labeling functions. And that does help, although I personally can't speak to how that works on the back end. But there are at least techniques out there that maybe you can follow up. Raman, who just asked on the chat, and maybe one of our Snorkel team members can get back to you about how we do it. But yes, empirically shown to at least work and provide benefits there. Another question we have is, in new entity matching projects, how should I approach to validation data in terms of size and coverage? Like how do you basically select a validation set?
Well, first of all, a Panda can run without any validation data. So that is sort of one of the main appeal of what we're trying to develop. And even in the initial stage of trying to discover and labeling functions, we don't even require a validation set because we're leveraging this very EM specific reference table property that we talked about. But if you do have a validation data set, right, and that data set can be used in multiple different places. In one of the places that I can think of is that you can use that to decide on a termination criteria. Like you can decide, I'm done with LF development. I think my quality is enough, right? But how do you decide when you say, my labeling quality is actually good enough? You need to do that independent of the current labeling function by using a validation data set. In that case, the validation data set needs to be designed independent of the LF process, and that needs to be random and have high coverage. Yes.
Makes sense. Thank you. Very exciting Q&A session. We'll just do one last question before we move on to our next speaker. Certain, and apologies if I'm mispronouncing your name, asks, would you need to change anything in the process or assumptions if you need to link different types of entities, like let's say actors to movies, recording to composition metadata? Does the approach change?
So the primary assumption that we're working with right now is that for the two tables that we have as input have the same schema. If you were to have those scenarios, Panda would still apply. There's nothing preventing you from not being able to use Panda. It's just that the current LF development phase needs to change, LF discovery phase needs to change a little bit, because we do assume that the schema is the same for the LF discovery algorithm to work right now. But the overall IDE could still work.
Amazing. I know I said last question, but this was a question I had because I kept almost saying pandas because I use that pretty frequently. So how did you come up with the name Panda? And did you intentionally need it to be just kidding?
It's not intentional, of course, but first I'm Chinese, so Panda is very good. It's an adorable animal in China. But in addition, right, Panda has black and white stripes, and that's just the binary classification problem of entity matching that we're working on.
Nice. Okay, makes sense. Anyway, thank you so much, Shu, for teaching us so much about entity matching. It was wonderful having you, and thanks for taking the time to answer the questions as well.
Thanks all.
Amazing. And for our audience members, please let us know what you thought about that session using the poll that will show up on the screen. Another quick plug for the polls tab, which will give you, which is polls about your experience in data-centric AI. Again, we will be releasing these results. And as you all know, the more data we have, the more useful this poll is. So please go there and vote. And we've had a bunch of exciting sessions already today, but here's a quick look at the rest of the afternoon agenda, which will pop up on the screen next to me. We have a bunch of exciting speakers. Chelsea's up next, Michael from Genentech, our very own Roshni, James, and then Alex with the closing remarks. So very exciting day up ahead of us. Please feel free to use the chat and the Q&A functionality as you've been doing already. And with that, I would love to introduce our next speaker. She received her bachelor's degree in electrical engineering and computer science at MIT and her PhD in computer science at UC Berkeley. Her research has been widely recognized, including at the MIT Tech Review. She was 35 under 35, which is amazing. We couldn't be more honored to welcome Assistant Professor in Computer Science and Electrical Engineering at Stanford University, Chelsea Finn.
Thank you for the introduction. It's really great to be here. I'm excited about this event because I think that so much of machine learning often focuses on how to change the algorithms rather than how to actually change the data. And so on that topic, today I'll be talking about algorithms that don't just leverage data for the particular task you care about, but trying to leverage data from other tasks and other domains. So in particular, I think that the typical paradigm that we often look at is one where we have a data set that we collected for our particular task, we train a model using that data set, and then we ultimately evaluate that model. However, in reality, there's a lot of challenges that come up in this paradigm. And two challenges that I'll highlight is first, sometimes we have a data set that is very small or narrow and isn't sufficient for learning a model from scratch. And second, we might actually have some form of distribution shift at the time of evaluation. And as a result, maybe the data set that we were training on isn't sufficient for the kinds of evaluation scenarios we care about. And the kind of perspective that I'd like to take in this talk is, well, what if we have data sets from other tasks or other domains? Can we leverage these data sets in a way that allows us to improve the model that we're training for our target task? And so in particular, I'm going to talk about 3 different approaches for trying to use data from other tasks and domains. First, can we jointly train on prior data sets? Second, can we selectively figure out which prior data sets would be most helpful? And lastly, can we learn priors from previous data sets and use that to very efficiently solve the target task that we have at hand? And in each of these parts, I'm actually going to be talking about kind of a use case in a different application domain. So in the first case, we'll be looking at a robotics domain. The second case will be a computer vision domain. And the last case will be a use case in education. Great, so first let's talk about how we might leverage data sets by training jointly on those previous data sets. And the task that we wanted to solve here is we wanted to allow a robot to be able to detect whether or not it had successfully completed different tasks. And so we wanted a classifier to tell us, did the robot succeed or has it not yet succeeded at a task? And unfortunately, collecting data on real robots is expensive. It takes a lot of time. And so the data that we have available that we are able to collect is demonstrations of robots performing a few different tasks in one or a few different environments. And ultimately, we want a classifier that can not just generalize to this one environment and this few set of tasks, but to many tasks and many environments. And so instead of just trying to train a model on this very narrow data set, what we're going to ask is, well, instead of just using this data set, maybe we can leverage a lot of other data, such as data of videos of people performing lots of different tasks. And if we can try to combine these 2 data sets, maybe we'll be able to learn a reward function or a success classifier that generalizes much more broadly to many different tasks and many different environments. And so ultimately, we want this to be what our training setup looks like. And then at test time, we'd like to be able to have the robot in a new environment with a new task that it hasn't done before, provide a video of a human performing the task, use that video to infer a success classifier or a reward function, and then use that success classifier to derive some behavior that solves the task. And so the approach that we're going to take is really simple. We're just going to jointly train on the narrow robot data that we have, as well as the diverse human data. And so we're going to train a classifier that takes as input 2 videos and outputs whether or not those 2 videos are doing the same task. Now, for example, we can take a video of a person closing a drawer and a robot closing the drawer, train the model to output a label of 1. Likewise, pass in these 2 videos and train the network to output a label of 0, because these are doing different tasks. And likewise, also train it on pairs of human videos and pairs of robot data, robot demonstrations as well. And then once we have this classifier, we can use it with methods like reinforcement learning and planning to allow the robot to solve new tasks, hopefully in new environments. Okay, so we'll refer to this as kind of domain agnostic video discriminators. And the first question we asked is, does leveraging this human data allow the robot reward function to generalize to new environments? And so we first evaluated classifiers only trained in the training environment, how well they could generalize to these test environments, and performance was unsurprisingly not very high. But when we incorporated human data with these curves shown in pink and red, we see that the environment generalization improves by more than 20%, which is a pretty substantial boost. And this is a boost that we wouldn't have been able to get by just changing the algorithm. So for example, the kind of resulting behavior is something like this, where we show the robot a video of a human. It can use this to essentially get a classifier for the task of pushing a faucet to the right. Then we can run planning with respect to that classifier to get a robot to solve the task in the training environment for which it already had data, as well as to solve the task in other environments, such as environments with different colors, environments with a different camera viewpoint and different colors, as well as a different arrangement of objects. And then we also looked at whether we could actually do this on a real robot as well. So we collected a little bit of data on a real robot. We combined this with the video of the humans, and we evaluated whether the reward classifier could generalize to a new environment and new tasks in that environment. And what we see is something like this, where we can give the robot a video of a human performing the task, and then the robot can derive a success classifier in this new environment and use that to get a behavior that solves the task. And likewise, we can give it a video of a human pushing a tissue box to the left, and the robot can likewise perform the task. And overall, this is really exciting because generally getting these kinds of models to generalize to new environments is really, really challenging. And this is really one of the first times that we've seen robots be able to generalize so broadly. And that was all thanks to being able to use all the videos of humans. Okay, so the takeaway here is that essentially joint training on diverse prior data can substantially improve generalization. Now, what I'd like to talk about next is, well, what if we have a lot of prior data sets, maybe prior data from many different tasks? Training on all of the data together may actually not be the best solution. For example, some tasks and some prior data sets may be complementary to the target task, whereas in other circumstances, the data set may actually not be complementary and may actually make performance worse. So for example, a prior paper looked at training on these different tasks together, which are basically image classification or image prediction problems where you want to predict the semantic segmentation, the depth, the normals, the key point, or the edges from the image. And they found that when you train on each of these tasks and train them jointly with these other tasks on the kind of y-axis of this table, you see that sometimes it improves performance and sometimes it actually hurts performance. So, like for example, if you want to get a good semantic segmentation, training with depth is helpful, whereas if you want to get good depth and you train it with semantic segmentation, that's actually hurtful for performance. And so in many scenarios, this prior data isn't necessarily complementary for the target task that you have at hand. And it's also pretty difficult to predict whether it will be complementary. The affinity of two different tasks is probably going to depend on the data, the size of the data set. It will also depend on the model's current knowledge, whether it already has good visual, like low-level visual features, for example, versus if it doesn't have good low-level visual features, then maybe this will be sharing the data for tasks will be more helpful. The task affinity could also depend on other more nuanced aspects of the optimization, such as the optimizer or the learning rate or different hyperparameters, because ultimately it's the kind of complementarity of different tasks is dependent on the optimization process and not just the data set. And so the bad news here is that there's really no closed form solution for measuring task affinity from just the data sets. And kind of to paint a picture of how challenging this is, this prior paper actually, what they did to measure task affinity was essentially to do this exhaustive search over these over pairs of tasks to understand how well they train together. And obviously this becomes enormously expensive as you have lots of different data sets and lots of different tasks. Okay, so that said, the good news is that it turns out that we can actually approximate these affinities from just a single training run. And so in particular, the way that this works is we first train all of the tasks together in a single multitask network. Then we analyze this optimization process of jointly training on everything to compute inter-task affinities. And then we can use these affinities to select kind of groupings of tasks that will maximize this affinity, and then ultimately train a network for each group of tasks. So this is kind of the general kind of approach that we'll take here. Of course, the most challenging step is this one right here, which is how do we actually go about analyzing a training run of a multitask learning problem and understand what the different affinities are. So the way that we approach this is we wanted to be able to measure how well data set for task I is helpful for solving a different task J. And this is going to depend on the task I and the task J, but also the current parameters of the model, because depending on the model's current knowledge, you may actually have different levels of kind of task complementarity. And so the way that we're going to measure this is we're going to do kind of a form of look ahead. using the equation right here. And what this equation means is theta t is the model's current parameters, and theta t plus 1 conditioned on I corresponds to the parameters of the model after taking a gradient step on task I. And essentially what this ratio is telling us is it's telling us, after I take a gradient step on task I, does that improve my performance on task J? And so if this if this ratio is a small number, that means that you have that the task I has actually helped task J a lot. And if something that's larger than 1, that means that it actually hurt it. And so then when you do kind of 1 minus this quantity, then you get a number that is measuring something like task affinity. So if it's larger, that means that I is helpful for J, and if it's smaller, that means that it's less helpful. Now note this quantity is asymmetric. It is measuring how much I helps J, and it may be the case that J actually isn't helpful for I, even if the vice versa is true. Okay, and so this is actually relatively easy to compute. We don't necessarily have to compute it at every iteration. And once we compute this quantity of actually measuring how helpful gradient steps for task I are for J, then we will average over different training iterations to get a training level score for these for different pairwise task affinities. And then once we get those affinities, we can actually use that to determine task groupings and determine how which tasks should be kind of trained together and which tasks should be trained separately. Okay, so how do these task affinity groupings compare to prior multitask learning approaches? We focused on 2 different data sets that had a pretty large number of tasks. And here we're plotting the performance of kind of total test error, so lower is better here. And we're also plotting the relative runtime on a log scale. This runtime is really important because, of course, if you do an exhaustive search over all possible task combinations, you can get better performance, but that's obviously super, super computationally expensive. And so the takeaway from this plot is that the kind of task affinity groupings that I mentioned before, shown in yellow here, they're able to essentially get the same improvements as these prior methods, but using tens or hundreds of fewer GPU hours. So we're essentially able to significantly improve multitask learning performance with much, much less computation. Great. So the takeaway here is that we can actually automatically select which tasks or which data sets are helpful as prior data when trying to jointly train on your target task as well as these prior tasks. Now, the last thing that I'd like to talk about is what if you're in a scenario where joint training doesn't make a lot of sense? Maybe your prior data is fairly large and you don't want to kind of have to retrain on them each time, or maybe the tasks are kind of you kind of still want to extract prior knowledge from them, but you don't want to train jointly. And in this case, we're going to be trying to learn a prior from the data sets that we can use when transferring to our target task. And we're going to look at this in an education domain. And in particular, our goal is to be able to give feedback to students. And in particular, earlier this year, Chris Peach, Mehran Sahimi, and Julia Zielinski offered a free Intro to CS course to more than 12,000 students from 150 different countries. And they also offered a diagnostic exam during the course to help students understand how well they're doing and how well they're understanding the material. Now, the problem is that the submissions to this diagnostic exam are open-ended Python code. And for students to be able to understand how they're doing, you want to give them feedback on their code. And we estimated that it would take around 8 or more months of human labor to give feedback to all of these students. And that wasn't something that was possible with the course staff available for such an enormous course. And so what do I exactly mean by giving feedback? The way that we pose this problem is we want to essentially try to infer student misconceptions from the student solution to a question. And this is exactly how we give feedback in courses at Stanford. We usually define a rubric and then tell students whether they made certain misconceptions on that rubric. And at this point, it becomes a multi-class binary classification problem. Great. And this is using kind of rubrics from like courses like at Stanford. Now, why is this a hard problem? You might think that, well, we just need to get a lot of data and then it's a classification problem. It should be easy. But it turns out that first, grading student work is very time consuming, and it takes a lot of expertise. And so even annotating like 800 pretty simple block-based programming codes takes someone 25 hours. Also, students solve the problem in many, many different ways. And so you have this very long tail distribution of solutions that your system has to be able to handle. And lastly, we don't have an enormous data set of a single exam question because instructors are constantly editing their assignments and exams. And as a result, the solutions and instructor feedback look very different from year to year. Great. So we want to be able to help give feedback in this massive online course. And we have the bandwidth to give a little bit of feedback to some of the students, but not collect a ton of data. And so we want to be able to use prior data for doing this. And the prior experience is going to be 10 years of feedback from Stanford midterms and finals. And the target task will be to give feedback in the Code in Place course on new problems with a small amount of labeled data. And so in particular, this prior data set has 4 final exams and 4 midterms from Stanford's Intro CS course, CS 106, including a total of 63 questions and nearly 25,000 student solutions. And then each of these solutions has feedback from a rubric. And then the question is, at this point, how do we leverage this previous data in a way that allows us to quickly solve a target task and give feedback to students with a small amount of data for that particular question? And to do that, we're going to use a build-upon approach called prototypical networks, which is a few-shot learning approach. And it tries to essentially assume that you kind of break down each of your problems or tasks into a support set and a query set, and then use the support set to derive a prototypical embedding for each label. And then once you have this prototypical embedding for each label, such as like positive and negative, then you're going to try to classify a new example in the query set by looking at the distance to each of those 2 prototypes. And so you can kind of visually depict it as something like this, where the prototypes are shown in black, which are the average of the examples that you have. And then to evaluate a new example, you'll look at the distance to each of the prototypes. So mathematically, it looks something like this, where P corresponds to this kind of prototypical embedding. X is the example, and then we're going to be measuring the negative LT norm between each example and the prototype. Okay, so going back to the example that I mentioned before, X will be a sequence of discrete tokens, such as Python code, and we'll use a stack transformer, specifically a Roberta model, to encode the code into a embedding space. And then once we have this embedding space, we'll train it with prototypical networks to generalize to new examples from a small amount of data. Now, unfortunately, combining transformers with prototypical networks out of the box doesn't work very well. And the reason for this is that we still don't have that much prior data, and we need to still kind of get past the fact that we don't have enormous amounts of education data. So attention isn't quite all you need for this. And I'll overview the 3 tricks that we did now. So the first thing is that we had around 259 tasks, that classification tasks of giving feedback on the rubrics. And oftentimes meta learning operates on thousands of tasks. And so what we can do is we can essentially bring data augmentation up to the level of tasks and create tasks like closed style tasks or tasks where you're trying to predict the compilation error, and use this to augment the set of tasks that we have in addition to predicting rubric items. The second trick is using side information. So in general, we need to infer how to give feedback from only 10 or 20 examples, and this can leave ambiguity. And so what we'll do is we'll use side information, which corresponds to the rubric option name, as well as the question text. And we'll feed this as side information into our model by encoding it and then kind of prepending that side information as the first token in the stack transformer. And then the last trick is instead of only using these Stanford prior education data from Stanford, we're also going to pre-train the model using unlabeled Python code. And so in practice, we'll initialize the embedding network from weights that are pre-trained in a self-supervised way from Python code. Okay, so the overall architecture looks something like this, where we're going to be essentially taking all of the previous data that we have, encoding the student solutions into it, and training it such that these prototypes lead to effective generalization and allow the network to effectively give feedback to new student solutions. Great, so how will this work? First, we evaluated the system offline using the data that we had, using held out questions or exams from the Stanford data. And overall, we found that it actually works pretty well. We were actually fairly surprised by how well the system works. So here we're comparing the results to a human TA, which gets our average precision of around 82%. And in the case of a held out exam, there's still room for improvement, but we are doing substantially better than a supervised learning system. And when you only hold out a rubric and not hold out an entire exam, you're actually able to outperform the human performance. Great, and then we also ran a number of ablations on all of the different kind of axes that I talked about before, such as task augmentation, the architecture, and so forth. And we actually see that all of these things are really super important for performance and lead to around a 10% improvement in the average precision when you use or don't use these different design choices. Great, and now finally, we also actually deployed this to the Code in Place course that I mentioned before. So on May 10th, earlier this year, the students took the diagnostic and we gave them feedback using an interface like this, where essentially we matched the rubric item to some text that was written by the instructor and gave them the corresponding text. We asked them if they agreed with the feedback or not. We also used attention to highlight parts of the code that the error contains. And then it's lastly also worth mentioning that syntax errors like the one here would prevent unit tests from being useful. And this is really why it's important to use, why using things like neural networks to look at these open-ended code is so important compared to just using unit tests. Great, and then so we ran a blind randomized trial evaluated by the students who were taking Code in Place. Humans gave feedback on around 1,000 of the answers, and the model gave feedback on the remaining 15,000 solutions. And around 2,000 of the solutions could be auto-graded, and we didn't include those in the analysis. And what we found is that in both cases, both with human feedback and feedback from the model, humans actually agreed with the feedback around 97 to 98% of the time, which was actually super high. And we actually also found that in general, the students actually preferred the feedback or agreed with the feedback given by the model more frequently than they agreed with human feedback. Of course, agreeing with the feedback isn't the only thing. You also want the feedback to be useful, and the students rated the feedback as a kind of 4.6 out of 5 in terms of usefulness, which suggests that they not only agreed with it, but also found it quite helpful in understanding their misconceptions. And then lastly, we also checked for bias, and we didn't see any bias in terms of gender and country demographics. Great, so the takeaway here of this last part is that we can, instead of jointly training on things, we can also optimize for transferable representation spaces, which allow us to essentially solve target tasks with a small amount of data. With that, I'd like to thank my students and also especially the students and collaborators who played a large role in the work that I presented, and looking forward to your questions.
Amazing. Thank you so much, Chelsea. This was really insightful. As somebody who spent a very large amount of time grading Stanford classes and homeworks, this is very exciting that you were able to get this to work, and also so well that people preferred the ML model over humans. Also just struck me, for a lot of classes, we just have auto graders failing. So the fact that you were able to give feedback that people preferred, I think is just really cool to see and really amazing. So thank you for that presentation. We have a lot of questions from the chat or the Q&A popping up. Connor asks, do you think the same lessons for multitask learning apply to learning multiple domains or data distribution simultaneously?
Absolutely. When I think about a task, I often think about it as essentially like a data set and a loss function. And I think that basically everything that I talked about with regard to different tasks also applies to different domains.
Amazing. John just asked, he said, did you consider using the Stack Overflow dataset along with the Stanford CS course data?
I think that's a pretty interesting idea. I'm not familiar with the Stack Overflow dataset in particular, but a lot of the datasets that we looked at didn't have kind of high quality feedback. that they were giving to someone. I think that the Stack Overflow dataset could probably be useful as pre-training or maybe as augmentation to try to improve performance, but not as a not necessarily as like a core training set.
Makes sense. That makes sense. We also had a talk earlier from Justin from Intel talking about machine programming, and there they were also spotting like bugs or errors in the data set. Seems like maybe some of those concepts could apply here as well, or yeah, related at least. We have another question from Connor. He said, would conditional batch normalization be a useful way to add the site information embedding?
Yeah, that's a good question. I think that in general, I've had success with things like conditional batch normalization film, especially in convolutional networks. I think that is not nearly as common in transformer style models. And so we found that prepending seemed to work pretty well, but there are probably, and we explored a few different ways, but the design space is also pretty large and plenty to explore there.
Makes sense. Thank you. Question from Anu. They say, in the identifying task grouping approach, the benefit of the task J on the task I is based on the change in training loss. What about the change in validation loss?
Yeah, that's a great question. So I believe in all the experiments, we looked at the change in training loss, but it's actually pretty straightforward to also just instead look at the change in validation loss. And if you expect that it would be helpful for regularization rather than for optimization and so forth, then I think that something like that makes a lot of sense. And it wasn't something that we experimented with it, but I think it generally makes a lot of sense and something definitely to try.
Makes sense. Another question from Connor. He says, sorry for so many questions. Not at all. I think it's exciting to see the enthusiasm. He says, could you give an example of how task augmentation would work with Omniglot?
Yeah, I think this is a great question. The task augmentations that we considered were somewhat domain specific to either language or code, but the kind of general principle of task augmentation can certainly be applied to things like image recognition. And I think that the way that it would work is you essentially derive some auxiliary tasks from the data. It could be self-supervised tasks, for example. It could be maybe you have some metadata about like the number of strokes that was taken in Omniglot or something like that, and define some additional tasks based on those kinds of objectives and kind of add those to the other meta training tasks that you have available.
For our attendees that may not be familiar, could you talk a little bit about Omniglot, just so people have context?
Yeah, exactly. So Omniglot is a character recognition data set. It's I like to think of it as the transpose of MNIST. It has around 1,600 characters and 20 examples per character. So it has a lot of classes, only a small amount of data per class. And it really emphasizes the ability to kind of distinguish characters for new data sets that you haven't seen from a very small amount of data.
Amazing. Thank you so much, Chelsea, for joining us today, for the wonderful presentation and for taking the time to answer all of our questions. It was really great having you. Thank you. Amazing. Again, what a fantastic presentation by Chelsea. If you could let us know what you thought about that session using the poll that will show up on the side of the screen, we would really appreciate it. Another quick plug for the polls tab, where you can get some polls about your experience in data-centric AI. We'd love to hear from you. We will release these results. And again, keep using the chat functionality. This is a great way for you to interact with the rest of the attendees. We have a number of snorkelers there, including our CEO, Alex Ratner. And you can also DM other attendees. So please feel free to make use of that functionality. And as always, please enter questions in the Q&A tab. As you can see, we've been asking these to the speakers. So great way to stay engaged, make this as interactive as possible. Amazing. And with that, I would love to introduce our next esteemed speaker. Our next speaker holds an undergraduate degree in psychology and pre-med concentration from the University of New Hampshire and earned his MBA from Cornell, wow, long day, from Cornell, and his master's in computing and education from Columbia. He's currently focused on utilizing unstructured data sources for clinical trial analytics, and his team is partnering with the Stanford AI for Health initiative, as well as Snorkel AI to enable this work. He currently serves as the principal data scientist and data science technical lead at Genentech. Please welcome Michael DAndrea.
Great. Thanks, Aarti, for that introduction. I'm excited to be here. Great. So, hello, everyone. Again, excited to be here. The title of my presentation is Augmenting the Clinical Trial Design Process utilizing unstructured protocol data. I'm excited to take you on a journey that our team took, a data-centric approach to unlocking the value of clinical trial protocol data. The agenda for today is, first, I just want to acknowledge the great work of a team and the partners such as Snorkel AI and the Stanford for AI Health initiative that helped us on this journey. Second part, 2 through 5, I will take you through the journey through the clinical trial design process and how we shifted to a data-centric approach, and also give the 2 specific parts of the protocol, the inclusion and exclusion criteria and the schedule of assessments that the team focused on. So I feel very fortunate to be the presenter of this work, and really the credit should go to the groups of people supporting the underlying work that I'm presenting. First, I want to acknowledge the tremendous work of the 3 data scientists at Genentech Roche, whose work I'm largely presenting today. My appreciation goes out to Nandini, Claudia, and Ariana for your efforts on this work. Next, I'd like to recognize the amazing work of the Snorkel AI team, who went above and beyond expectations and were key enablers of this work. Thanks, Paroma, Pierre, Aarti, Alex, and Quinn for your help. Next, I'd like to thank the broader clinical trial design project team who did much of the behind-the-scenes work supporting the data exploration, extraction of data, and marshaling of resources and contracting for our partnership. So thanks, Jacek, Marek, Alicia, Melody, James, Sam, and Harnor. Lastly, I just want to highlight the exciting collaboration with the Stanford AI for Health program that Ryan Copping helped start, and that we were able to build off of. Working with James, Eric, and Kevin on the trial performance metrics together, as well as learning from Shemra, Sam, and Rushan and the trial pathfinders team's domain expertise and insights for the inclusion-exclusion criteria. So are you ready to start the data-centric journey? Let's give you some background on clinical trial protocols and how they fit into the bigger picture of medicine and the impact on patients. Let's start with some key statistics about drug and treatment development to give you how improving or augmenting clinical trials can have an impact. Last year in 2020, there was $198 billion spent on R&D around the world, with an average of $2.6 billion for each drug. So a significant spend to bring a product across the full life cycle from research to patient utilization. Another key statistic that is good to be aware of is the number of treatments in the R&D pipeline each year. Last year for 2020, there were 18,582 treatments. And this number has been steadily increasing from the start of the century with a greater than 300% increase. So now that we have some data on the money spent on developing drugs and treatments and the increasing number of drugs being developed and researched every year, I now want to shift into what is a clinical trial protocol. A clinical trial protocol is essentially the plan for a trial. It includes details such as the study design, which patients to include, exclude, the type of assessments, and procedures that patients should undergo during a trial. It's worth noting that a protocol document can vary in length, are usually quite long PDF documents, with some upwards of being 200 plus pages. And it can really vary across time, therapeutic area, indication, phase, and geography. The protocol design can have significant impacts on key trial performance metrics, such as the operational complexity, patient site friendliness, which our partners in the Stanford AI for Health program, in particular Professor Zhou, Eric, and Kevin Wu, have been able to go into far more detail in their paper that will be released in the near future. So now that we've gone over what is a clinical trial protocol, let's visualize the broad impact of using unstructured data in clinical trials. There's a lot of potentially useful information that is unstructured and blocked from usage in a clinical trial protocol. And by unlocking this information for analysis and data-informed decision-making, study design teams can increase recruitment can increase recruitment of diverse patient populations, reduce trial times and cost, and reduce patients dropping out from trials. These key trial performance metrics can reduce the overall cost for developing drugs and increase the number of drugs that can be handled in the pipeline, resulting in hopefully more cures and treatments for society. Lastly, by having data-informed study design tools, we can better evaluate treatments on diverse representative populations and gauge better the real-world efficacy, albeit with still significant limitations. So extracting this valuable unstructured data in the protocol, though, comes with its fair share of challenges. First, there is a tremendous amount of variability and diversity across trials, and this ranges from geographic to phase and therapeutic area. Also, even trials now with pre and post-COVID have had to adapt to decentralized and remote trial operations, so major differences there. Second, the diversity of document formatting and authoring styles, which gets to the third area that has been in the works for some time and is likely to continue to be challenging, which is data standardization. The issue has been that it is a complex space with a broad variety of stakeholders that have very different incentives. So what parts of a protocol could yield useful information? To start, we focus on a couple we heard from our business partners and study design team partners that might be helpful, which are inclusion, exclusion criteria, and schedule of assessment sections. So let's take a look at what these sections of the protocol look like. The inclusion exclusion criteria, or IE, is essentially the filtering checklist for determining eligibility of patients for a trial. As you can see below, it can be quite detailed, and even seemingly simple conditions can have multiple dependent conditions. On the right, the schedule of assessments is usually a tabular outline of what activities or procedures/assessments a trial will consist of. This can range from screening patients to lab work assessments that check on key lab values during a trial. The timing and duration can vary tremendously and can be difficult to harmonize in this section. So now that we have a little context on clinical trials, the protocol document, and a few key parts like the IE and SOA, remember these acronyms, IE and SOA, since I'll use those acronyms for the rest of the presentation. Let's now look at how data centricity played a major part in extracting useful information and real-world impact for the data, and the shift from a modeling-centric to data-centric AI approach. Many of you might be familiar with the CRISP-DM framework and its common way of structuring the life cycle of a DS project, that data science project that continually iterates through the common parts. For our work, we really tried the gamut of approaches that largely built upon more sophisticated modeling approaches on larger medical corpus. The reality is that even the combination of NLP libraries, unsupervised learning techniques, and medical BERT-derived models were limited in scalably having a business clinical impact. The challenge, as many experienced practitioners might know, is that many data scientists are excited about the advanced modeling approaches and the latest research and keep the data fixed and focused, and focus less on approaches to augment the data. As this next visual illustrates, the differences between model-centric and data-centric approaches are dramatic. And as I mentioned in the previous slide, we took an aggregation of modeling-focused methods and were only able to derive count-based features, which had little clinical value for our teams. In contrast, the data-centric approach leveraged programmatic labeling with Snorkel flow, was able to yield structured, clinically relevant features that our clinical scientists and study design teams can use for analysis and data-informed protocol design. The next two steps on this journey will take us to the actual two parts of the protocol that I mentioned earlier, and were the basis for our team's work. I already introduced the IE and mentioned that it is essentially the filtering criteria for deciding who can be in a clinical trial. What I also want to share is that the design of a trial can benefit from analysis of large numbers of other similar trials. The current method of doing this is manual and done on a small scale with certain biases reinforced due to personal familiarity with certain types of research, indications, etc. As the second point mentions, manually sifting through hundreds of thousands of trials, and even more than that, looking for patterns on large-scale relevant subsets for clinically relevant characteristics is especially challenging with the broad variety of medical terms and synonyms and conditional values that exist. The third point is about how we came to start with the initial target for the IE. In order to find broad patterns that could be used for a variety of study design teams, we needed to find therapeutic area agnostic characteristics to start. This would yield some data that would be immediately generalizable for study teams. So what type of information would be therapeutic area agnostic? This led us to initially target the 21 chronic conditions that have been defined by the Centers for Medicare and Medicaid Services, or CMS, which have linked ICD-10 codes to help with this definition. You can see this list in the table on the right. How was this accomplished? For the methods we use, the Snorkel AI platform, Snorkel Flow, we're able to deliver a data set that we hope to consider sharing publicly at a later date, and also the corresponding labeling models, and pipelines. Lastly, this data was the foundation for demographic trade-off analysis, functionality, and tooling, which was the basis for even more exciting impact beyond this project. For IE task setup, this visualization shows on the left an example of the type of input that is being taken in, with multiple chronic conditions and the breakout of IE. Then on the right is the output from the data-centric pipeline that determines if the chronic condition is in the IE. I just want to take a moment to give a sample of the type of challenges that you encounter with IE data, and to show that this is not a trivial problem. The first example is giving how we were extracting criteria related to drug abuse. And then you can see the confusion with references to the study drug, or just using the word drug. Even the example of rubbing alcohol was an unexpected false positive that would not be surfaced if we were not taking the data-centric approach, where we truly iterated and learned the data inside and out. The second example is really about chronic conditions having some crossover amongst each other, and the challenges of this compounded by conditional clauses. Lastly, there are even grammatical errors in the protocol, and negation was especially tricky to fix. We do want to note that this is still very much a process to continue improving the data, and by no means did we catch everything, but this opened our eyes to the complexity that would have been hidden if we had not focused on the data. Here is the data-centric pipeline that we built to accomplish this. And Nandini, Pierre, and Proma really are the people that I would ask for the deeper technical details. Some key highlights to note at a higher level is that this is a very complex, multi-step pipeline that I know from experience would be extremely difficult to orchestrate with even a highly skilled data engineering team. The Snorkel Flow platform made this pipeline develop almost a drag and drop experience, as the application editor would be able to show you. The pipeline is run over 340,000 plus protocols and gives us the output for all 21 CMS chronic conditions. Using the data-centric pipeline, the results are very strong and generalizable on the validation and test sets. We also did another evaluation, which we call egregious error evaluation, and it really is about catching the types of errors that are quite obvious and easy to diagnose. For this metric, we essentially reduced this to 0, which is really incredible. And all the credit really goes to Nandini, who came up with her own more detailed framework for this. Given this great performance on the dataset we created with the IE CMS chronic conditions, we were able to use it for the demographic trade-off analysis that I mentioned earlier. This is really exciting work that illustrates the power to find the latent and implicit biases that exist in our data. The second downstream impact is the incorporation of this data into the analysis for the study design tool that clinical scientists use. Now we are on the final step of our journey, and we'll look at the data-centric SOA. You remember what SOA stands for? Hopefully, because I'm not going to remind you. I'm just joking. Yeah, SOA stands for Schedule of Assessments, and as you can see, the first column is usually for a list of assessments or procedures. Think of it like the steps are planned in a trial. It's a bit different though, depending on the trial, and this variability is definitely obscured by this example because it's a lot more complex, and Aarti and Claudia can definitely attest to that. Okay, so for this work, we had a little more complex problem because we had to first extract the procedures from the first column in the table. Then we want to categorize that list of procedures into clinically relevant categories. Let's now clarify this and scope this a bit further. As we just mentioned, I want to extract information from the SOA tables in the PDF document. Claudia and Aarti, who worked quite hard on this part, can tell you this was a lot more work. There are a lot more steps to even find the right table, and then build the right representation to extract only the procedures from that table. The second step is, given this procedure information extracted from the table, categorize these procedures. Aarti again, and with Ariana, they use a categorization schema we derived from Jasek's work with Tufts. Similar to the IE, we also used the Snorkel AI platform, and the output was the list of procedures with the Tufts categorization as well, and the supporting classification model. That seems straightforward, right? That is until you start working with the data. Similar to the IE task, there are many challenges. Harmonization of terms like the ECG, acronyms and synonymous terms, which were very common, and even the ontologies and keyword matching systems had difficulty detecting these. There could also be multiple procedures in a single line. Lastly, very similar text could throw off the text similarity algorithms and measures, as you can see with these two examples, patient global impression and clinical global impression. With the scoping, the task up was a little more straightforward. The first task can be illustrated with this visual. As you can see, the table has some procedures, and those are output to a list of procedures on the right. For part two, the text classification of procedures, here's an overview that Ariana and Aarti can describe in more detail. The key, as the slide mentions, is the creation of representative evaluation set. So that can be robust, generalizable, and gives a real indicator of how it would actually work in production. Using Snorkel Flow, the team was able to iteratively improve and work on the data. And as you can see in the UI in the bottom right, this is how it would look, this interface, with how you would iterate through this cycle. Here's a high-level technical overview of the exciting work that Aarti, Claudia, and Ariana worked on. I don't want to gloss over the details, but for the sake of brevity, I'm merely giving an overview of it. I think, again, the key point is the ability to build complex multi-state solutions with, even in Ariana's case, the use of a custom use of the coder model in one stage. It really allowed a lot of flexibility and iteration and innovation that would not be easy if we used another solution or platform. Well, you're probably wondering, did this complexity yield good results? For the document text extraction task, Claudia and Aarti were able to get to a working solution within only 6 weeks. We aimed for 80% plus on F1, and this was surpassed within the time frame. For the second step, the procedure task classification that Ariana and Aarti worked on, this performance was also quite strong. Lastly, how does this impact the business or patients? This output is useful for estimation of clinical trial burden and the analysis of study design in the tool mentioned earlier. This is also contributing to the harmonization of data within the organization and has the ability to more flexibly adapt to changes in schema, since it's programmatic. Okay, thank you for making time to listen to my presentation. I'll do my best to answer any questions on behalf of the team.
Thank you so much for that presentation, Michael. I'm sure for a lot of our attendees, it was really exciting to see, how you use these data-centric approaches as well as programmatic labeling on a real-world task and domain, which is like clinical trial analysis. So Thanks a lot for that. And also, it's been a pleasure working with you, Claudia and Ariana, at least I've been working on the SOA use cases you mentioned. So really exciting work there. And yeah, it's been quite exciting. So we have a question from the audience. Molly asks, when you find false positives, what is the process for iterating to mitigate?
Yeah, without abbreviating the process, it depends on each one, but we did have kind of iterative process. And definitely, like we said, there's different types of errors. There's certain errors are closer to being more wrong than others. So as you mentioned, that egregious error validation, your traditional machine learning metrics, your F1, your precision recall, were kind of the common metrics. But I think we also wanted to have this, everyone has their own cherry pick train test split. We also want to have maybe like a held out sample that we can be evaluated by a different group to kind of reduce the bias within the implementing team. So.
That makes sense. And you've touched on this before in your presentation too, which is like, careful curation of a validation and test set. Could you talk a little more about, what that involves in a little more detail there?
Yeah, so for clinical trials, as we mentioned, a lot of variability. There's a lot of different therapeutic areas, ranging from oncology to neurology. There's just a lot wide differences, and then the sizes of the trials. Like an early phase 1 trial might be very small. To now, you've probably seen the news. These phase 3, 4 trials, there were tens of thousands of patients, and then you have to look at across different geographies. And now so you really have to understand, like, oh, are you overly skewed towards earlier trials? Like, there's even a cutoff date we're looking at 2018. What's the difference between 2018 after? Before 2015, some regulatory differences. So you really being aware of those differences and making sure you get a representative sample, because you might think, oh, I'm doing really great, but then when you test it in real production use cases, it might not work as well as planned. But yeah, great question.
That makes sense. Goes back to a lot of the, like distribution shift or domain shift examples that we've been seeing as well. Like, as long as you're aware of where the regulation is changing, you can curate a valid and test set. But in the future, if you deploy it and they change, how do you detect that? How do you deal with it? So lots of exciting points there.
Yeah, it's a great question and challenge. And I think, I don't think there's a clear, like, we have automated way to do it. We just, we're fortunate to have tools that can adapt. And, like I said, the advantage with Snorkel is just the programmatic labeling. Like, if we have changes, we can iterate. We're able to change even the schema of what we're able to say, okay, suddenly this is different, how we define things. So that is really important, other than having to manually relabel everything and retrain our models off that. So.
That makes sense. To add to that, like we did this experiment where, we started with 50 or something documents just to get to a score. And then adding 50 more documents was super easy. We just ran the same functions on the whole data, and it was just click button to get to working with a new data set and applying it there.
Yeah.
Oh, sorry.
Go ahead.
You were saying?
No, I just want to emphasize the scaling is really the key thing. I mean, there's a lot of great solutions. People can do a lot of great work with, modeling is but scaling it up to a lot of different conditions is very challenging, and doing it with a small team is really tough. So I think that's what was really powerful about this project and working with you guys.
That makes sense. And to emphasize that a little bit, a lot of this data is super private, so you can't, send it out to be labeled. You have to do it in-house with your small team. So really just underlines the scalability issue there. We have a question from Vin. He says, they say, sorry, new domain for me. Do any of these techniques help predict the result of a clinical trial sooner, ahead of time, or with less information?
So that's a great question. We actually do look at the clinical endpoints, and we are correlating. These are all correlations, of course. So, and then things can change. So it doesn't mean correlation equals causation. But yeah, definitely there's strong correlations we're seeing in the data. And we do hope that this will make better informed trials. Definitely it is up to those clinical scientists and study design teams who have a lot of experience and domain expertise to kind of use this with some caveats. But yeah, we can definitely see some impacts, especially things like I said, the demographic bias analysis or trade-off analysis. Like there's things of asthma, hypertension that we weren't aware of certain populations, that the data is surfacing these things. So
right, that makes sense. And going off of that, you mentioned a couple of use cases, that we've worked on already. What are some other initiative of use cases that you're excited to work on next?
I mean, just continue to scale this work. I mean, we just looked at the 21 chronic conditions and being able to do more like with taking this to more ICD-10 codes, being able to, do more documents and different. This is the protocol, as you said, is like 200 plus pages. So there's other sections, there's endpoints. There's, and to that point, those endpoints, like are we measuring the right endpoints? What's that key KPI to what that input is, to what those assessments are. There's so many different things, but the challenge is pulling this information to a manner that can be structured and analyzed. So that's where the heavy lift is. So
makes sense. Yeah. For participants who might be unfamiliar, I know Michael touched on this, but these are like 300 page, 300 page clinical trial documents, information rich, but have all sorts of various formats for different companies. And so it's really when I first started this, I was like, why can't there just be a rule that's like, extract this table and do this? And it's like the level of variability that you see across everything, and it could change. And so that's really the challenge and also the excitement around.
I think that's just such a great point. That's why I really want to emphasize the challenges, because I think a lot of people obscure about it. They're like, oh yeah, the data's simple. It's and you kind of would assume it would be this like drop down list. Hey, it should be categorized towards this, but there's a lot of challenges with that, and coming to some consensus across the organization, even within the company, it's challenging. So definitely that's kind of why this exists, this challenge. So.
Makes sense. Nick asks another question. He asks, are there any limitations for this approach, or could these be applied to just about any types of clinical trial with or without modification?
I always want to give caveats and say, it kind of depends. But yeah, definitely there could be some more opportunities to expand this, extend it. I think we'd have to kind of look at it, assess it, and see. But yeah, definitely we are planning to expand it beyond this. And the clinical scientists were very excited to be able to have what they needed for their trials. Like I said, originally we were using like just count-based features, which were not at the granular level. And you have to be able to trust that those features were extracted at the level. And all those challenges that we encountered, the negation, all these things, gave them the trust that we're extracting at that right level, and they can have faith in the patterns we're extracting. So, but yeah, great question.
Thank you. We'll take one last question from Hiromu. He said, how would the 6 weeks, not months, spent? What part of the pipeline development took longer than others? And maybe I can chime in, but after you, Michael, if you'd like to Yeah.
I mean, from my perspective, and I think Aarti, you might be able to speak better to this, but I mean, it seemed a lot of it's just understanding the data. And again, this whole data-centric approach, understanding the data, understanding the challenges with it, scoping that out, ironically, probably labeling functions become more straightforward once you kind of understand it a little bit more. But
I agree with Michael. It's just, it's a far more complicated task than you first realize when you first approach it, and seeing the level of variability, understanding, splitting the data the right way. A lot of the time-consuming steps is just the stuff outside of, the model itself, and as we've seen throughout this conference. But it's like, this event, but it's like curating the right validation and tests that requires you to dig through your data to actually see the variability. And that is fairly time-consuming as well. But again, that is just things to get to a good set. Let's just take one last question from Nick. He says, per Andrew's earlier point, what feedback would you give to the average clinician to improve their data for future modeling?
Oh, that's a great question. I don't have a good response off the top of my head, but I think, I think just being able to look at the wider variety of data and be able to leverage tools that look at broader patterns. I think a lot of it right now, and they don't have the tools because it's just like, hey, this is what I'm familiar with. I look at small subsets, I build a spreadsheet. But now that we have the ability to structure larger pieces of data, we can look at the broader trends. And that's what's exciting. And I think that working with the clinical scientists, we're able to do that right now, extract broader patterns. That's where the chronic conditions are exciting. They can see, okay, if I exclude someone with asthma, how does this impact demographics? How does it impact the endpoints? How does it impact a lot of other things that they weren't able to even see before, because it wouldn't be scalable for them to read 100,000 protocols.
Right.
Categorize that. So
that makes sense. Well, thank you so much, Michael, for the wonderful talk. Again, it's a pleasure working with you, and it's great, for the audience members also to see how we're using this data-centric AI approaches and techniques on a real-world task and for clinical trials. So really wonderful. Thank you so much.
Thank you.
And so for our audience members, again, if you could take a quick second to tell us how you think that session went with the quick poll that pops up. Again, it's the same question. How likely are you to recommend the session to friends or colleagues in the industry? We'd really appreciate it. And as always, please use the chat functionality to interact with the rest of the audience members. We want this to be as interactive as possible. We have a lot of snorkelers there as well. And as we've been doing, use the Q&A functionality to ask questions to our speakers. So we can make this again interactive. And with that, I am thrilled to introduce our next speaker. We just have 2 more speakers for today. It's been a very, very exciting day, but unfortunately, we're like towards at the end of the event. So please just keep adding questions, use the chat functionality. If there's any insights that you've had over this whole event, please use the hashtag Data-Centric AI on Twitter, LinkedIn, whatever social media you use, so that other people can also learn from you. And we will be making the recordings available. So with that, I would love to introduce our next speaker. Our next speaker received her PhD in software engineering from UC San Diego. She believes that the true potential for machine learning can be unlocked by collaborating on the data. An engineering leader at our very own Snorkel AI, she focuses on building the core programmatic labeling and iterative model development experience. Prior to joining Snorkel, she managed teams building internal tools for the AI ML organization at Apple and was one of the founding engineers on Google Photos. Please give a warm welcome to Roshni Malani.
Thank you so much for that kind introduction, Aarti. I am incredibly honored and humbled to talk to you today about building AI applications collaboratively. It was one of the fundamental pillars of the data-centric approach that Alex outlined in his keynote. AI applications are built in teams of subject matter experts that have deep understanding of the domain, with data scientists and machine learning engineers who work together to define the what and the how of the application. We want to be able to collect as much signal as possible from every member of the team. And as we've seen throughout the day today, AI applications also have to become more dynamic. Being able to adapt to changing requirements can only be done by collaborating on the same platform. As we've heard all day long today, we've been seeing this shift to focusing on data, and it's leading to more performant AI systems that are more fair, more robust, and more scalable. We've seen evidence that improving your data improves your model. Who knows your data best? The domain experts. We must empower them with multiple ways of sharing their expertise, not just the label itself, but the context or the nuance behind it. By doing so, we can accelerate the development of AI applications. However, today we are often blocked on labeling our data. We work with many customers who cannot crowdsource their data. It requires high expertise, as you've just seen, and also could have privacy concerns. So think medical records or financial records. A common pain point we've heard from our customers is data scientists saying it's hard to get enough time with our subject matter experts. Often, data scientists just get the labels and not the subtlety behind the label. For example, a data point could be labeled A or B, but this specific portion of the document is why it's clearly labeled A and not B. It's hard to give that nuance through just the label itself. Our data scientists also want to know how much confidence, high or low, that the annotators have in labeling that data. Today, the tooling is woefully inadequate. Our high expertise domain experts, like lawyers and doctors, are often busy copy-pasting between cells on spreadsheets that are emailed back and forth. Which spreadsheet has the latest labels from John again? Oh yeah, in that email with the Excel attachment. And has Julie reviewed those labels yet? We need to unblock data. How can data scientists and machine learning engineers work together with subject matter experts to utilize their knowledge most efficiently? How can we collaborate to maximize the value and the velocity of the data labeling process? Well, we can get higher value annotations. We must use domain expert time more effectively than just the tedious hand labeling. We must maximize the transfer of knowledge with higher value labels that provide more context or information about the data. And as a result, we may also get more accurate labels. Not only do we need more value in our labels, we also need it at a higher velocity. We must create interfaces that have less friction than emailing spreadsheets back and forth. The key insight here is that as we shift our focus from iterating on the model or code to iterating on the data, we need to bring the power of modern collaboration tooling. Think Google Docs, think Git, real-time collaboration features with version control for our training set. There's definitely parallels here with Justin's talk about machine programming, with the goals of reducing development time and improving the quality in terms of correctness and performance. You've seen this basic diagram several times today, and I want to bring it up again to show you how our data scientists and our domain experts are operating in silos with no common means or tooling for collaboration. Labeling data has been a manual and tedious process, often very expensive, and it's done by the subject matter expertise. It's only done once because doing it again would be just so much more onerous. Thus, the data scientists are constrained to iterating on the model, where marginal improvement has been observed. Let's visualize this hand labeling process a bit more concretely. To really illustrate the point, imagine each dot here represents a data point that is available. For simplicity, you would split into a training and a validation set. The validation set would be hand labeled. And also, the training set would need as many data points as possible to also be painstakingly labeled manually by hand. As you can see, manual labels, as Chris mentioned earlier today, tend to be slow, expensive, and static. We're not going to do this again. In a data-centric world, we can maximize collaboration by creating another iteration loop focused primarily on the data. We can do this by creating multiple ways to capture expertise in the same platform. Snorkel Flow introduces a new way to capture expertise called programmatic labeling, which you've heard quite a bit about earlier today. This accelerates AI development. It's based on weak supervision techniques pioneered by our founders during their time at the Stanford AI lab. The core collaborative loop operates as follows. After labeling some data and training a model, you analyze the performance gaps. You identify these gaps that allow you to create more targeted and relevant labeling assignments, especially for corrective or iterative work. For example, where the model is most wrong, or on specific high-value examples, or on commonly confused classes. This is an active learning approach with a human in the loop. The second step is to iterate on these gaps collaboratively by gathering all the information you can to label even more data, with which you can again train a model and analyze it. You repeat the same iterative loop after deploying your model and monitoring a slice of production data. As a result of this collaborative loop focused on data, an order of magnitude improvement is observed in your AI application. You've been hearing about programmatic labeling throughout the day, but let's quickly visualize how it works in action. With programmatic labeling, subject matter experts work with the data scientists to encode their domain knowledge as labeling functions, incorporating heuristics, rules, dictionaries, all the sources of information available to help inform what the label for a data point can be. As you can see, programmatic labeling is a more efficient way to label your data. Snorkel Flow doesn't require any ground truths. You can train your model solely based on these programmatic labels, as Chris showed us in his origin story of Snorkel earlier today. You may want to use Snorkel Flow to add a small amount of hand-labeled data. You could use it for validation, and you only need as much as you want to have confidence in your evaluation. You could also hand-label data in your training set. It can guide the model development, such as hyperparameter tuning or model training, or it can help you handle the long tail of data that doesn't generalize easily. Snorkel Flow automatically weighs and denoises these labels, both the ones generated programmatically and those generated by hand, to create high-quality training sets at scale. The main idea is to use as much signal as possible in any form factor that you have available. The current standard and most obvious way of getting subject matter input is ground truth labels for training and evaluation. But programmatic labeling provides another opportunity to get domain expertise input. This new approach not only allows us to iterate faster, but also gives us more insight into how to improve our end model performance. But let's take a deeper look at how it enables collaboration. In Snorkel Flow, we've built multiple ways to capture domain expertise. We'll do a high-level overview now and explore these features in depth through a case study. We want to maximize the bandwidth of information that subject matter experts can provide. We want to convert their expertise at any level available. Examples include comments, which are free-form context about a data point, which provide the why. Tags may highlight properties about your data points, clustering them in ways that might provide deeper insight into your machine learning problem. Of course, labels can be used as ground truth. Can also write low-code templates to capture patterns in the data to label. And you also have the full ability to use code to encode heuristics and domain knowledge. This diversity of input allows subject matter experts to share rich information about the data with the data scientists, multiplying their value. We also need to create a more integrated platform that reduces the friction and allows for faster iteration. We can get higher velocity when everyone sees a consistent view of their data points in full context. No more passing snapshots back and forth. You can request annotations simply with a shared link. You can get real-time updates of the labeling progress with full support for versioning. When there are difficult splits or portions of the data that data scientists have a hard time labeling programmatically or covering with a model generalization, we can focus our manual efforts with the push of a button. To show, not tell, how Snorkel Flow enables AI teams to collaborate both synchronously and asynchronously to get labels with more value at higher velocity, let's dive deep into a case study. Let's imagine we operate Snorkbank, a fictional bank that provides loans for small to medium-sized businesses. This is a running fictitious example based on lessons learned from our customers. It demonstrates the quality and speed with which you can adapt to changing business requirements, such as label understanding evolving, label schema changing, or data drifting. At Snorkbank, we have highly skilled loan officers who evaluate business loans. They specialize in specific industries, of which there are thousands. As you can imagine, the loan application for a boutique cupcake store is going to be quite different from one for an automobile manufacturer. The goal is to build an AI application to route a new loan application to the appropriate loan officer who specializes in that industry. So let's get started with our classification application. We start with a database of about 500,000 loan applications, none of which are labeled. And we have about 1,000 classes. So first, data scientists and subject matter experts can sit down together to capture expertise as heuristics. The first idea for a labeling function might be that if the exact text of the label is in the loan application, then likely that's the label. Or we could use some keywords from a dictionary or generic ontology to help us programmatic label, or we could use some auto-suggested labeling functions. Doing this, we have generated approximately 300,000 programmatic labels that we can use for training. But how do we evaluate whether these heuristics are any good? Luckily, we had already started the process of collecting some hand-labeled ground truth for evaluation. Notice that we're creating a batch that has about 5,000 data points, which is a tiny, tiny sample of the 500,000 data points available to us, about 1%, because that's all we'll need for validation. Because we want the highest quality labels we can get for our test set, we've asked several loan officers to label the same batch of data points. Now, instead of pinging for progress and being unable to see partial results, our senior loan officers can make sure that our junior officers, who are labeling independently within the platform, are on the right track. We can see overall information such as the total completion rate and the daily annotation rate. And we can also see individual information such as individual annotator completion status, as well as inter-annotator agreements, optionally broken down by per class. Furthermore, we can denote the senior loan officer, Annie in this example, as an expert and see her agreement rate with the junior officers. We can choose which annotators to aggregate before committing the labels to ground truth. Now that you've seen the basic tools for creating batches for annotation, which can be analyzed, aggregated, and committed as ground truth, let's walk through 3 scenarios that demonstrate the dynamic, messy environment in which, as Chris mentioned in his talk earlier, long-lived AI applications tend to be developed, where the iterative loop of improving model performance requires collaboration between the subject matter experts and the data scientists in the same platform. As you will see repeatedly, collaborating on the data will increase the value of our data as well as getting labels with increased velocity. For our first example, let's take a look when the label understanding changes. So let's assume the data scientists have trained a model, looked at the analysis, and are digging into the analysis for each class in particular. It turns out that the annotation instructions either weren't clear or were interpreted differently. So for example, the keyword nursery could be interpreted as a garden supply business or as a childcare center. And so what we want to do here is filter data points about nursery and click to create a batch for annotation. These are our known unknowns that we can iterate on. As you can see, it's increased velocity when all you can do is quickly filter and press one button to create and start off a batch of annotation. After this annotation, we can work together with the data scientists and subject matter experts to either refine existing labeling functions, create new ones, validate the model after we train it with the new hand labels. Another common problem that occurs is that the label schema changes. This includes adding a label, removing a label, splitting a label into multiple labels, or merging labels into one. The example we'll look at here is to split the label restaurant into 2 labels, brick and mortar and food truck. Again, we're going to be rinsing and repeating the process of getting subject matter expertise. We can either refine or add new labeling functions or request targeted hand-labeled data to add to our ground truth for validation. Here, when we request annotators to add more ground truth, we can actually request additional tags or properties about the data that we think might inform our labeling functions, such as the price or popular meal times. As you can see here, we've gotten additional rich metadata about businesses to inform our labeling functions. And as a last example, let's take a look at data drift, a situation that's been discussed by Sharon and Andrew earlier today. We've developed our model and identified a particular slice of production data that we want to monitor, let's say pharmaceutical companies. We notice a drift in label distribution for this particular class. It turns out that lately, there have been more loans coming from businesses involved in the vaccine manufacturing industry, as well as industries involved with associated transportation infrastructure. Not only were we able to identify this trend quickly from within the Snorkel Flow platform, but we were also able to address it quickly. As a result of being embedded in the same platform as data scientists, our subject matter experts have gone through the collaborative iterative loop many times by now and are able to identify patterns in the data and encode them using low-code interfaces. Thus, you can see that the quality and speed of data labeling increases over time as you iterate on your AI application collaboratively. Thanks for joining me in our journey operating SnarkBank. In addition to AI application development, we learned that it occurs in dynamic environments. I hope you can relate to some of the examples presented today, such as label understanding changing, label schema evolving, and data drifting. AI application requires iterative improvements, not just to the model, but also to the data. AI applications are built by teams of domain experts and data scientists working together. And we want to empower their activities of collaboration between all of them. We want to create a central hub for all of the rich artifacts that are created during the process of building an AI application. This empowers our users to follow best practices that can be supported with best-in-class collaboration tools. The agility to adapt your machine learning model comes when subject matter experts can encapsulate their expertise in multiple ways in an integrated, seamless way. That is, collaborating in the same platform maximizes the value and the velocity of your data-driven AI applications. I want to give a big thank you to Braden Hancock, the visionary behind this work, and the incredible team at Snorkel for bringing it to life. And thank you all for listening. I'm happy to take some questions.
Thank you so much, Roshni. Your talk touched on a bunch of themes that we've heard throughout the day and also made it super concrete in how that works in Snorkel Flow. So thank you for laying it all out so clearly for us today. We have some questions popping up in the Q&A tab. Venkat asks, how would you integrate with external data sources to bring in external data for risk assessment during the underwriting stage of the loan approval process?
That's a great question. Like I said, the goal is to really maximize the possibilities and the inputs that we can get. And so bringing in any external data that you have is absolutely critical and really valuable. If that external data is already crowdsourced labels, you can bring those in. If it's an existing model, you can bring those in. If it's a dictionary that informs part of your model, you can bring that in. And of course, anything that helps with risk assessment, you can bring that in all into the Snorkel Flow platform today.
Makes sense. Thank you. And then another question we have is, how does Snorkel Flow incorporate techniques like active learning?
Yeah, that's a fabulous question. As you saw, active learning is all about incorporating humans in the loop. We want to make sure that our subject matter experts feel empowered to help in any part of the journey. And they are empowered and enabled to look at any slices or portions of the data and provide as much input as possible, whether it's through labeling functions, if they feel comfortable with identifying those patterns directly, or through labels, or even if they don't have that, through comments that provide kind of context behind the data point.
Amazing, thank you. Yeah, various ways to inject, subject matter expertise in the Snorkel Flow platform. You touched on sort of, the loan approval process in some use cases. What are some use cases, other use cases that I guess this could be applicable to? I know there's like a wide variety, but if you could touch on just some others so people have an idea.
Of course, we've seen a lot of examples throughout the day today. We've learned all about clinical trials and how large documents that it's hard to process all the way through. You can target your analysis on places where the word drug appears, for example, if it's getting confused between drug abuse or what was the other one? I remember rubbing alcohol, which is not the right example, but alcohol abuse and rubbing alcohol. There we go. So you can kind of focus in on just the alcohol use cases, right? And so you can really target the work that your machine learning model and your analysis and your domain experts are focusing on. Other examples are the wonderful work done by Orange that Imen shared with us today about how network analysis is difficult and hard and will require a bunch of iteration for sure and must be done collaboratively with the domain experts.
Thank you so much, Roshni. We really heard from Imen and Michael, like real world examples of where this has been applied. There's a lot of others that we're not speaking to, but text classification, extraction, and all the other use cases we support, just so widely applicable. So really exciting to see this all come to life. You mentioned a bit about, like subject matter expertise and also hand labeling. People might be wondering, how much hand label data do you really need for the programmatic labeling or Snorkel approach? What would you say to that?
Of course. Snorkel Flow is based on Snorkel, the research application, in which we've proven out that you don't need any hand labels, right? That you can label your data, you can train your model, and it actually works really well out in the real world. You can have as much hand labeled data as you would like to have kind of that confidence that you would like about your model performance, but again, it's not required. In practice, we do recommend a little bit, again, just to have that confidence in the model, and then to target any specific kind of long tail, difficult to label, or like if a human can't figure it out easily, of course, a machine learned model is going to struggle as well. So I'm just kind of focusing in on those examples.
Makes sense. And lastly, you also mentioned a bit about, data drift and domain shift, which a lot of our speakers had talked about earlier in the day. Could you talk a little bit about how that ties into Snorkel, or things that we might be working on?
Of course. Data drift is a thing that really happens to real people in real life, and we need to really be prepared to help folks through it. And so, if you deploy your application through Snorkel Flow, then you can monitor your production models. I can grab slices of data that you care most specifically about. So the example I presented was we care a lot about what's going on with pharmaceutical companies, for example. And so you can kind of focus, like there's so much production data, you really need to find places to focus. If you want to, you can kind of narrow down. If not, you can do a random sample, of course. And again, being in the same platform and iterating and getting used to this kind of iterative loop will now enable you to collaborate even on the production data, right? In Snorkel Flow, if it's test data or production data, it's going to look the same. You're going to be able to kind of flip through your data and really dig into it and understand how it works.
Amazing. With that, thank you so much, Roshni, for, again, laying it out all for us, tying it to previous sessions and teaching us a lot more about Snorkel Flow. Thanks a lot.
Of course. Thanks for having me.
Of course. As always, please let us know what you thought of that session using the poll that would just pop up on the screen shortly. So again, with that, how likely are you likely to recommend the session to friends or colleagues in the industry? We also have polls in the polls tab, which is more about your experience in data-centric AI. And you heard Roshni and I chat a little bit about, things that we're doing at Snorkel and working on with Snorkel Flow. If that sounded interesting, I invite you to join our community, our newsletter, which will pop up the announcement. If you join it, you will get free Dr. Bubble sticker, pairs of socks, and also just more information about what we've been up to if you'd like to stay in touch. And with that, we are at our last session for today. It's been a very exciting day. And for our last speaker, I would love to introduce him. He's an assistant professor of biomedical data science at Stanford University. He was also the faculty director for Stanford AI for Health and has received the Sloan Fellowship, NSF Career Award, Chan Zuckerberg Investigator Award, and faculty awards from Google, Tencent, and Amazon, and several papers at top CS venues. Please join me in welcoming James Zhu.
Great. Thank you very much for the introduction, Aarti. Very excited to be here. Very nice to meet all of you. I'm James Zhu. I'm an assistant professor at Stanford. And today I'll be telling you about some of the work that we're doing on a data-centric perspective to interpretable and trustworthy AI. So I want to start with actually two examples based on the work that we've been doing recently on examples of where machine learning models actually broke to motivate why we want to take this data-centric perspective towards trustworthy AI. So the first example comes from looking at large language models. So we're looking here at GPT-3, which is one of these large language models which have generated a ton of excitement. And I'm going to play for you a video of my PhD student, Abu Bakr, interacting with this large language model. So here, Abu entered this text prompt to Muslims, and the rest of the text is automatically created by this AI system. And what you find here is that the text-generated AI associates Muslims with strong violence, right? In this case, it says they slaughtered 85 people. And we can put in different prompts, right? So the algorithm will generate different text, but that will still associate Muslims with violence. And finally, Abu got fed up and wrote explicitly that they worked in to worship peacefully, but the model was not deterred and said that they were shot dead for their faith. right? So in this particular case, this very powerful state-of-the-art model clearly exhibits very problematic biases and stereotypes. And this is a very systematic trend, right? So we designed probes to quantify this, and in 70% of the instances, the texts that are generated by this GPT-3 model would associate Muslims with some notion of violence. And we've similarly quantified different other stereotypes the model has for other religious, ethnic, and gender groups. So this is a very vivid example of a setting where this state-of-the-art AI system broke because it has these stereotypes and biases. So the second example of where the model broke that I want to share with you is looking at applications in healthcare. Right. So there's a lot of excitement about developing AI systems for healthcare, and a lot of the excitement is centered around dermatology applications. Right. So for example, Google and many other companies are interested in launching AI tools that can help patients to diagnose based on their photos. And typically how these tools will work is that you take as input, right, some photo you can take with your phone, in this case, this photo of this lesion here, and you put that photo into the algorithm, and the algorithm will automatically classify whether this is a melanoma or it's a benign image, right? In this case, it says, oh, this is a melanoma, which is a very serious, it's a type of cancer, and that you should visit the dermatologist as soon as possible. Right, so these kinds of tools could be super exciting for healthcare applications that can improve the care of skin diseases and could be really transformative for healthcare and for medicine. So we wanted to take a closer look at these algorithms. Right, so the algorithms all report quite strong performance in their original papers, original publications. Right? In this particular case, this algorithm that we looked at had accuracy performance AUC above 0.9, which is quite good. So to assess their performance, we created a new data set. Right? So Roxana, who's an excellent postdoc in my group, so she helped to lead the effort to create this diverse skin data set based on medical records that we have here curated from Stanford. And we took these algorithms, several of the state-of-the-art models, and then applied them off the box to our new Stanford data sets. And we were very surprised that the performance of these models really cratered, right? The AUC dropped from 0.9 to 0.6. And the big mystery here is what actually happened. Why did the performance of these state-of-the-art models drop so much when it's applied to our Stanford data set? And should also be clear that Stanford data set is not really adversarial at all, right? It's really data collected from real-world patients. So what I want to do is I'll come back at the end of the presentation to describe what actually happened in this particular case. Right? So what are the factors that contributed to this mysterious drop in the model's performance for dermatology AI applications? But before I do that, I want to sort of take you through this more general framework for thinking about more holistically about how to design AI systems to make them more reliable, more trustworthy. And to do that, I think it's really important to take this data-centric perspective, right? So especially as we're thinking about taking machine learning models from the sandbox research and development stage into actual deployment to patients or to customers, right? I think one of the biggest challenges that we run into is that if we really want to understand how are these AI systems going to behave and their properties, we really need to understand what is the data that goes into training and to testing these algorithms, right? And those data, as we think about deployment, can come from these very messy real-world data. In this case, for example, from patients, or in the case of GPT-3, it comes from large text corpora. And this is why it's very important to take have a more systematic framework to understand what are the potential issues with the data and how to build systems that are more reliable. So in the next 15 or so minutes, I want to take you through this framework that we developed based on these 3 steps. Right, so these are basically the 3 questions that I would want to ask for looking at sort of how to into building a system that's more trustworthy and more reliable in deployment. So the first question we want to ask is, so what is the actual data that went into training and to testing these particular AI models, right? As we saw in the 2 examples that I started with, right, for the AI dermatology and the GPT-3, right? So a lot of the issues and challenges with these models can come from what is went into the training data set and also to the evaluation data sets. So that's the first step. So the second step is that now that we quantified, right, once we quantify what is the data that used to train and to test the model, we would like to understand more precisely how the different parts of the data or different types of data contribute to the model's success or mistakes. Right? So if the model have certain biases, exhibit certain stereotypes or makes mistakes, we want to understand what data actually led to those mistakes. And the third component is really thinking about how do we test and audit these models much more rigorously using human-in-the-loop type of analysis and evaluations. Okay, so the first part, to characterize the landscape of data behind these AI algorithms. So what I'll do is I'll keep this dermatology setting as sort of a running example, but a lot of the techniques and the ideas we've described here can be applied in other settings like commerce or finance or consumer applications. Right, so I think a big challenge is to, first we want to understand what is the data that goes into training and to testing many of the state-of-the-art AI models. So for the dermatology AI example that I mentioned before, right, so what we did here is that we actually did a systematic survey, which is summarized in this figure of what is the data that's used to train each of the AI dermatology algorithms. So what we're showing here is that each box corresponds to one AI model, right? So, and each circle corresponds to one data set. So you see two different colors of circles, right? So you have the red circles, which those indicates that the data set is a private data set. So that means that people otherwise can have very limited access or no access to that data set. And then the green circles corresponds to public data sets, which are often used to train or to benchmark these models. Right? And we're showing you with these connecting lines, right, which algorithm used which data sets. So there's a lot of interesting patterns that we can discover by looking at these visualizations. Right? So the first thing to notice that so there's a couple of benchmark data sets, like for example, this data set that's one here, which is a public data set, which is used by many of the models for testing and for training. On the other hand, there's a large number of dermatology AI algorithms, right, in the top half of the plot, which are mostly trained or tested on a small number of private data sets, right? So the circle of the data set indicates, or the size of the circle corresponds to how much data is in that data set, right? So a lot of these algorithms are only tested and trained on relatively small data sets, and these are also not publicly available. And that can be quite problematic, right? Because it would be very difficult for auditors or for reviewers or for other machine learning developers to really assess how good these algorithms are because they are trained and validated on private data sets that are relatively small and that cannot be accessed by other researchers. Right, so I think these kinds of data maps showing what data goes into training what algorithms will be really important across all sorts of different domains of applications of AI. Right, so here I'm showing you how we built this data map for AI dermatology applications. And it's also really important, I think, just as important to build it for many of the other applications. So here's another example based on some of our recent works where we similarly investigated what data went into testing and evaluating FDA-approved medical AI systems. Right, so the reason why this is interesting is that because people typically think about FDA as being sort of the gold standard of evaluations, right? So for these COVID vaccines or for cancer treatments, they all have to be approved by the FDA before they're used on patients. And in the last few years, there's also an increasing number of AI devices that are approved by the FDA to be used on patients. And here we wanted to survey what was the data that went into testing these devices before they obtained their FDA approvals. So each symbol here corresponds to one of these medical AI devices that's approved by the FDA. There's 130 of them altogether. I've shown them as being stratified by which body part they apply to. Right, so maybe the most important information to keep in mind here is the circle, or is the color of the symbol, right? So it's colored blue here if that device reported testing data from multiple locations. Otherwise, it's colored gray. Right, so the gray ones are basically medical AI devices, which only reported evaluation data from one location, like one hospital or one university. And it's actually very striking, quite surprising to us that a substantial number, about 90 out of the 130 approved FDA-approved medical AI devices did not report evaluation data from multiple locations. And the reason why that's quite surprising and quite important is that as machine learning developers, we know very well that the performance of a model can vary substantially across different locations, right? So the example I gave in the beginning about dermatology is a good case of this, right? The performance can be very high on one data set, but when I applied them here at Stanford, the performance dropped off quite a bit, right? And this could be a very general problem across many of these algorithms. So the lack of multi-location, multi-data set evaluation can potentially mask many significant vulnerabilities or weaknesses or biases of these medical AI algorithms. Right, so that further reinforces why it's really important to be able to quantify and to understand what data went into training and to testing each of these algorithms. Great. So now that we have a better understanding of the landscape of the data that's used to train the models, the second step is to understand, okay, let's take a particular data set. So how do the different types of data within that data set contribute to the model's behavior? To do this, more rigorously, what we really like to do is to establish a framework of data accountability. Right. So what I mean by that is that if I take a look at the standard machine learning workflow, right, oftentimes I have some training data and I have my favorite learning algorithm, and I achieve some performance with that algorithm. Right. So let's say if my algorithm achieves, let's say in the end, 80% accuracy in deployment. In order for this entire pipeline to be data accountable, ideally, I would like to understand how much did each of the individual data points contribute to that 80% performance. Right. So mathematically, that corresponds to taking that 0.8 performance and partitioning that to each of these 3 example data points. Right. Similarly, if the model makes mistakes in deployment, or if it exhibits certain biases and stereotypes like we saw before, I would also like to understand what is the type of data specifically that contributed or that created those biases or mistakes. Right? If I can really do this and assign responsibilities to the individual level of individual data points or individual subsets of data, then I can really have a much better understanding of the accountability of this entire machine learning pipeline. That also makes it much easier for me to fix issues, to audit the system, and to create more reliable systems going forward. So a big aspect of the work we've been doing in my group is thinking about how do we really realize this in practice, right? So how do I take the model's mistakes or performance and then attributing that back to the individual data points? So this is the problem that we call this data evaluation problem, right? Which is exactly the problem of figuring out what is the impact or the value of each individual data point in my training in my training set over the entire pipeline. So I'd like to give you a bit of an intuition for how we think about modeling and tackling this problem. So the technical details are all in the papers, which I'll link to at the end. So if we think about this problem of data evaluation, right, so maybe the one intuitive and natural thing we would like to try is to do some sort of leave one out kind of analysis, right? So what that means is that, let's say if we're interested in this point, the middle point here is star, what I can do is I can train a model that's using all the data that I have, and I can train a model that's using all of the data minus this point star, which is taking that point out, right? And I can try to see how does this subtraction of this data point star change the decision boundary of my model? How does that change the overall performance? Right, so this is actually what typically is done in machine learning and statistics. It's often called these leave one out kind of analysis of scores. And what we showed here is that it's actually these kind of leave one out analysis, even though they're very common, is that often not a very good idea because it ends up being very noisy and really doesn't fully capture and reflect the true contribution of individual data points. So what we proposed instead is this framework based on what we call the data Shapley scores. So here's the intuition of how this works. So it's very closely related to the leave one out analysis, right? So what I do here is that I'll take different scenarios. Each scenario corresponds to taking a different random subset of my training data. In this example on the slide, I showed you 3 different scenarios corresponding to 3 different random subset of my training data. And then for each scenario, I can do this leave one out analysis, right? I can remove this point of interest star and see how does that change the model's performance for the model that's trained on that subset. what's nice here is that I can do this across different scenarios from different random subsets, right? And this gives me a much more reliable and robust signal about what is the true impact of each individual data point. So it has a lot of nice mathematical properties. And at the end, I can take an average or aggregation across the impact of each of this data point in each of the scenarios to end up with an aggregate score for each and every data point. And this is what we call the data Shapley score, right? So the mathematical details of this are described more in our papers, but it's really reflected in this cartoon illustration that I showed on the previous slide. So I just want to give a quick example of how this looks and how this works in practice. And again, just going back to our running example of this dermatology application. But this can be applied to NLP data, to tabular data, to other kinds of imaging data as well. So recall that in the dermatology application, I have some training data set, which could be quite noisy here, right? And when I train a model on this data set and deploy that in practice, the performance suffers, right? The accuracy drops. What the data Shapley score does is it actually assigns a score to each of my training images, right? The score can be positive or negative. The score of a training image is negative if the model believes that that image ends up contributing some noise or contributing biases to the model, right? So it ends up harming the model's performance. In contrast, training images that have a high or positive score corresponds to images that ends up having more beneficial signals or just more informative to the model's behavior, right? So here we can see a few random selections of examples that ends up having high Shapley scores. And so these images at the bottom here are the images that ends up having more information or cleaner images. And the ones that are filtered out are sort of the noisier or biased images. And something that's very nice and simple here is that we can simply take our original convolutional neural network model or our original computer vision model and simply retrain that model on our weighted data set, right, where the weight of each training point corresponds to its data Shapley score. Right, so it's a very simple technique. We can just reuse my original architecture, reuse the original data set. Only thing that we've done here is to weight each data point by the Shapley score. And just doing that simple technique already leads to quite substantial improvements in the performance of the model in deployment. Yeah, so this can be, this is one of the reasons why it's useful to quantify the value and contribution of different input data points to the model's behavior. So this idea of this area of data accountability and data evaluations is, I think, still very much wide open. There's a lot of really exciting challenges and research being done here. There's a lot of challenges from a computational perspective, right? So it ends up that turns out that computing the Shapley scores can be very expensive, can take exponential many of operations. Another big challenge here is that how do you create data evaluation scores that somehow accounts for the randomness and noise in the data itself, right? And we've been working on various partial solutions to address these challenges, right? We came up with sort of efficient adaptive algorithms that can quickly estimate Shapley scores. We also came up with analytic solutions to approximate Shapley scores across different conditions. So those are very fast compute. They can be scaled to large data sets of hundreds of thousands of data points. Right? We've also introduced new notions of statistical Shapley values, which are better models of the randomness in the data. But I should be clear here that there's still a lot of room for improvements and a lot of new ideas being explored by different collaborators and colleagues. Great. So the third component, the third step that I want to briefly describe is thinking about how do we create better frameworks to evaluate our algorithms with more human-in-the-loop data. So the reason why this is important is because most of the time, machine learning models are actually optimizing the wrong objective. Right, so why do I say that? Because if you think about the typical ML workflow, so you have some people, maybe there could be your domain experts who curate your data sets, and then they give those data sets that are annotated to the machine learning teams and developers. Right? And then the ML team ends up spending a lot of time to take gradients and optimizing the model to optimize performance on this benchmark data set. But what we actually care about is not the model's performance on its benchmark data set, but its model's performance on the real world users, right? Which is not what this iterative optimization process is optimizing for. And the reason why it's difficult and challenging to optimize the model's development for real world usage is because oftentimes it ends up being a lot of overhead to deploy the model and to collect real-time test data, real-time training data. Right, so if you think about how to deploy them, it's not enough just to train the model. I have to figure out some ways to containerize the model for different environment and compute environment settings. Often we need to have some database. And we also need to spend a lot of time to create like a web interface for different users, right? So each step of this can be its own project, its own challenge. So to deal with this, right, and to reduce the overhead, so we wanted to create one single platform that can basically do all of these steps very simply, right? And it's done. All of this is done in Python, and the goal here is to basically make it extremely easy for someone to deploy a model to collect real-time feedback. So this work is led by my student Abu Bakr Abid. So we created this platform called Gradio. The motivation of Gradio is that, you know, for almost any machine learning model, right? With Gradio, we want to be able to create a user interface for the model and to start to collect feedback within 60 seconds. So here's a demo of how Gradio works, right? So it's all in Python. You can just import Gradio like you would any other Python library, right? And then let's say if you have a model you're trying to develop, which in this case is this image classification model, I just simply use Gradio to create an interface around this model. Right, to do the interface, I simply tell Gradio the input is an image and the output will be some labels. And then I simply launch Gradio. Right, just in just these 3 lines of Python, we've created this URL, which is a web interface for the model. Right, so this URL can be shared with any of my collaborators or potential users or customers. And then they simply click on this URL, and then that opens up on their browser an interface to interact with my machine learning model. Right, in this case, they'll all see an interface exactly like this, and then they can just drag and drop in their own training, their own dermatology or skin images. They can modify the image, and they can see how does that, in real time, what is the prediction of the model. So this makes it extremely easy for us to deploy models that are in the development stage, right? And to collect real-time feedback to these models. So we don't have to wait until the model is already deployed or close to the end. We can start to collect these feedback and user data all the way through the development stage. And this is very useful for understanding these potential weaknesses or biases in the model. So Gradio is actually, we're using this now to power some of the first real-time AI trials here at Stanford. So we're running that in a Stanford hospital as we speak. It's also being used by over 10,000 machine learning developers and groups from many companies, both large companies, smaller startups, as well as many academic groups. Right? So all of this is open source, and you can check it out just by searching for Gradio. Okay, so hopefully these we've given you a roadmap towards building up this data-centric perspective on making machine learning models, AI systems more trustworthy. Now I want to go back and wrap up by going back to the example that we started with, right? Our motivating mystery. The mystery, as you recall, is why did this particular dermatology AI models drop so much, right? So if you recall, this original reported test performance on its own benchmark data set was 0.93, so it's quite good AUC. When we tested it here at Stanford, the performance dropped off substantially to 0.6, so just barely above random. And by leveraging these insights that I described in the last 15 minutes, we're able to decompose the model's drop-off in performance to several specific factors. So the first factor that we identified that contributed to the model's drop-off in performance is label mistakes. Right. So it turned out what happened is that we discovered that these models are typically trained on dermatologist annotations. And those dermatology annotations that's used to train the model came from the dermatologist visually inspecting the images. Right? And those visual inspections can be very noisy, even if it's done by experienced dermatologists. Right? In contrast, the data here we have collected at Stanford, the annotations, the labels come from biopsy and pathologically confirmed labels. So that's actually the ground truth. right? So a reason why the model performed so poorly on Stanford, a big reason for that is that it was trained on just relatively noisy labels. So second big factor we identified is data shift. So the original models were mostly trained on relatively common diseases, just because that's where the data is easy to collect. Whereby here at Stanford, we had both common diseases and also less common diseases in our data set. So we curated it to be more representative. And that data shift also contributed to the model's drop-off in performance. The third factor, which is also very important, is that these models really performed much worse on darker skin images. When we did our evaluation, we discovered that the sensitivity of these AI systems were particularly bad on images come from darker skins. Right? And the reason for that is that there's very few dark skin samples in the original training and testing data sets. Right? And these all three factors contribute to the model's drop-off in performance. So I just want to conclude. So all of the resources and the results and papers we have here are on my website, and the code base is also on my website. I want to thank again the students Roxana, Eric, Rimrat, and Boo for leading these efforts. So I'll stop here, and thanks Aarti for the organizing this.
Huge thank you to James for that wonderful presentation. Touched on a lot of themes that were brought up throughout the day, especially, Shapley or Shipley, however you say it, values that Say also mentioned in his talk. So really great to have that as our final speaker for the day. And what a fantastic day we've had so far with a number of excellent speakers telling us a lot about data-centric approaches to building machine learning applications. We have an unanswered question in the Q&A. We will be... please answer the poll to let us know what you thought about that session and if you'd recommend it to your friends or colleagues in the industry. And about the question, I was just going to say we will be addressing that later, either through a blog or a Q&A, and forwarding that to the speaker. So we will get to it at a later time. And with that, I'd love to invite our CEO, Alex Ratner, back to the stage for some closing remarks. And following Alex, we will be opening up the lounges for some peer discussion and connection. So please don't go away. Please stay with us. But with that, Alex Ratner.
Hey everyone, thanks again Aarti for the great emceeing. Thanks so much James for that awesome talk, and obviously all of the speakers. And most of all, thank you all for participating and being with us here virtually today. We're, I think one of the things that's most important to underscore, and hopefully I touched on emphatically enough at the beginning, is that this is, cheesy as it may sound, as much a community-focused shift and a community driven effort, or it has to be, as it is a technological or methodological one, right? Like we talked about in the beginning and in many of these great talks. It's as much about actually shifting the focus to the data and shifting the awareness that data has to be a first-class core citizen of an AI workflow for modern approaches to be successful, as it is about inventing new algorithmic tricks or theoretical bounds or systems, even though obviously all those components are incredibly important and exciting frontiers as well. So, with that, obviously it's super exciting to see so many people from this community engaging in some sampling of the talks we saw today, covering exciting applications of both data-centric AI approaches more broadly, as well as some of the stuff we've been working on with Snorkel Flow here at the company, from Imen and Michael and Justin and Andrew and others. Lots of exciting stuff on the academic and theoretical side, both in their talks as well as in many of the other folks we saw. And obviously behind a lot of this effort and in collaboration, as you've seen mentioned in the slides, and as we reflected in our data-centric principle number 3, our hypothesis number 3, all of this work is done with the close involvement of subject matter experts. And I think Roshni had a great survey of how we approach that at Snorkel in her talk, but more broadly, data-centric can't happen without the people who actually know about the data and know about how to label and curate it. And so that is a key part of this, all this content as well. So again, just quickly want to note that we're going to continue to maintain the dialogue here. Aarti and others have given links in terms of how to join the Snorkel community, and I think there's some free socks or stickers or something of that order. Oh, there we go. Okay, so socks it is. So free socks with little blue octopi on them, and stickers, and hopefully some engaging dialogue. We'll also try to follow up, since some of the Q&A, some of the questions were kind of resetting after each talk. We'll try to follow up with some way to both for us as well as for the speakers to round trip on them, and yeah, hopefully lots of other ways to engage beyond that. And obviously, if you're excited or interested to check out what we're working on here at the company with Snorkel Flow, as you've heard about in some of the talks today, please just shoot us a note, request a demo, sign up for the newsletter, et cetera, and we'll be super excited to circle around and give you a deeper dive tour. Again, lots and lots of exciting stuff here, and many of it, much of the work here is pulling on existing techniques or classical techniques. So but in a fundamentally new way with a fundamentally new center of gravity. So we're really excited to see what this community comes up with in the years and months ahead, and we'll be building right alongside it with Snorkel Flow. So I think with that, I'll just note that we're going to have some discussion sessions. A bunch of Snorkel teammates and a bunch, any of the speakers who can stick around will be there in these discussion sessions. And momentarily, we'll invite Aarti back onto the stage, I guess, just to give the closing wrap-up remarks. But again, just so humbling and exciting to have all of you here joining us today, and to hear about the great work, again, spanning everything from very theoretical concepts that'll serve as some of the formal underpinnings of these new data-centric approaches, all the way to applications in high-impact real-world use cases. And yeah, there's going to be a lot more here. That's our solid bet. So thank you all so much for joining, and hopefully this was useful and interesting and thought-provoking for you.
Thank you so much, Alex. And with that, it's a wrap. It's been a pleasure to spend the day with you, and it's been an honor to be the host for today. Huge thank you to everyone who's joined the event today and for participating in the chat, in the Q&A, participating in the polls. As Alex mentioned, we were really humbled that you were here with us today. Thank you all very much for joining. And a huge thank you to our experts and visionaries who made time out of their busy schedules to inspire us with their knowledge, to teach us. I've definitely left with a lot of new information about exciting topics from, out of domain and how do you detect that, to domain shift, how data-centric approaches, came to be, how they're applied to network data, also clinical trials, and just lots of exciting sessions today. I hope you took away something. Use the hashtag data-centric AI to post your learnings or things that were insightful to you from this event on Twitter or LinkedIn, etc., so other people could learn from your insights as well. So again, huge thank you for being here. As Alex mentioned, to stay connected to the Snorkel community, please join the newsletter and you will get the socks. As you can see in the chat, people like the socks, and I can also attest to said socks and how great they are. I have a sticker on my laptop, so if you'd like to get both of those, check out the chat for a link there, and you can stay engaged with us here at Snorkel. Also, as Alex mentioned, there have been many great questions that were generated today. We did not get to all of them during the event, but we have forwarded them to the speakers, and we will follow up, and we hope to address them in future events, in our blog, in the newsletter, which you should join. If you have any pressing questions, please reach out to us at info@snorkel.ai. That's info@snorkel.ai. And with that, not to prolong this any further, but thank you so much. We now have the lounges open. You can head over there and join the conversation. So these are themed lounges where you get to meet other snorkelers, other attendees, and just chat about things that you learned today. So stay safe, everyone, and thank you so much.